Hello there, everyone, and thanks so much for tuning in to this event that I'm calling the Minnow Brook Logic Programming Seminar. The talks you're about to see come from an event that I hosted in late May of 2025. Now, for the past few years, my collaborators and I have been working on building high-performance Datalog engines. Now, Datalog is not quite logic programming, and it's sort of full spectrum, and the seminar certainly reflects that. I really invited a cross-section of folks that I felt like were relevant to the kind of modern Datalog implementation community. And so it was so great to have an awesome collection of folks out to brainstorm and talk about the future of logic programming and Datalog specifically. And we really appreciate the funding from Syracuse University's Department of Electrical Engineering and Computer Science, without whom the event could not have happened. Now, I won't hold things up any longer. There's some really awesome talks, and so I'm really eager to show them to you, and I hope you enjoy the show. Thanks.
First talk, no pressure. All right, so some of you in the room have already heard this talk. I apologize. I will go further into the talk this time, hopefully. So I'm a database person. I think that puts me a little bit in the minority in the room. But when I talk about compilers, like I'm talking about kind of this broad swath of things. I'm not just talking about the compilers themselves, but also program analysis tools and optimizers and other fun stuff like that. And broadly, I'm talking about tools that take a big chunk of code, they do some interesting stuff, and then they produce a result. And hopefully I'm at least given the subject of the workshop, hopefully I'm kind of preaching to the choir here when I say this is basically a database, right? You have code, that's your data, and then you pose a query over the data and you get some interesting result. Maybe that's a new version of the code, maybe that's a program analysis result, maybe it is a different AST. Obviously, there's been a ton of work in this space, and trying to frame compilers in terms of some common underlying language, namely Datalog. This is a really nice, great opportunity for the communities to come together, and you can pretty much take any sort of typically you'd express logic in a compiler program analysis tool as some sort of match pattern or production rule, and those translate very neatly to standard Datalog. Okay, do I need to motivate this idea any further? No? Cool. Man, y'all are quiet.
I think we don't. I think the answer is no.
Okay, thank you. Thank you. All right. Cool. So I want to make sure everyone's talking the same language. So I'm going to say a little bit about my perspective on this problem, kind of give you my terminology, and then I want to talk about two specific projects, Tree Toaster and Draupnir. Tree Toaster from Sigmod 2020, which is far longer ago than I hoped. Getting old. And then Draupnir is a project I'm working on right now with Arlen. Okay, so let's talk about, when I say a compiler in Datalog, what does that mean to me? So I have some sort of program, in this case, a simple arithmetic formula. You can decompose that into an abstract syntax tree, and then you have a bunch of rules. For example, maybe I want to, everywhere I see A times B plus C times D, and A and C are the same, I want to replace that with B times D. In effect, if I can apply distributivity to simplify my expression, I do that. And the way I would frame this in Datalog is I'd have relations representing every single different type of node in my abstract syntax tree. One relation for plus times all the variables, all the constants. Maybe I have some sort of function application. And then I could frame my rewrite in terms of those relations. So everywhere I see a plus, and I see 2 times underneath the plus, the x, y, and a and c are the same, then that's an opportunity for me to apply my distributivity optimization. Cool? All right. Make that a little more concrete. I have that plus node at the top, ID 1, 2 children, x and y 2 and 3, 2 and 3 right there in the times, and then a couple of other things. Okay, cool. So I want to be able to apply this optimization over and over and over again. A typical optimizing compiler is essentially just looking for optimization opportunities, finding those opportunities, and then applying them. You apply your first rule to the query, you get a better query. You apply your second rule to the query, get a better query, and keep going. Eventually, you need to repeat the entire process from scratch because maybe rule number 3 created a new opportunity for rule number 1. In effect, you want to compute a fixed point. As long as you're changing the abstract syntax tree, you keep finding more and more rules. For every node in the abstract syntax tree, if the rule matches your pattern, you apply the replacement and you keep going. Now, one of my students, actually 2 of my students, for different versions of Apache Spark, instrumented the Spark optimizer and basically tried to figure out how much time it was spending on doing various things. Now, I poke fun at Apache Spark because that's the thing you do, but the same thing appears in only somewhat less extreme form in other optimizers. We also tried GPOrca. But the basic idea is that you look at is it visible, the difference between the two? Okay. So the dark blue bars represent time spent traversing the EAST and trying to figure out if you're done traversing, if you're done making changes. The light blue represents the actual work of generating the new rule, or kind of, you can see about 2/3 of the time is spent kind of just looking for opportunities to do rewrites, kind of in that pseudocode I gave you earlier. It's the kind of for loops on the outside where you're spending most of your time. So Spark tries to get around this. There's a whole bunch of sort of hacks built into Spark that try and get around the fact that it's spending most of its time looking for optimization opportunities. And in fact, from Spark 3.1 to 3.2, there was they introduced a feature where they sort of keep track of what types of nodes exist down a particular subtree, so that if a rewrite rule requires a particular is not applicable, you don't want to bother searching for join rewrite opportunities if there's no join node down a particular subtree. And so they're kind of keeping track of global state, and that required them to basically modify the entire structure of the abstract syntax tree to keep track of this additional state. My understanding is that was somewhere like 3 to 6 months of an engineer's effort. Like, it was a very substantial change to Spark to add that particular feature. And it made a performance improvement, but it required them to start thinking about the abstract syntax tree, not using the local reasoning of individual rewrite rules, but you had to think kind of globally about the structure of the entire abstract syntax tree. And that sort of reasoning makes it much harder to create correct programs. You want to think locally. You want to kind of keep the context for a given rule kind of nice and local. So Datalog obviously makes this sort of reasoning much easier. I'm going to use my example here rather than Spark, just because it's a little more intuitive. But already, if I frame my rewrite rule in terms of Datalog, my fixed point loop already changes a little bit, because now I'm not iterating over the entire abstract syntax tree. I'm just iterating over all of the plus nodes. That's just an immediate impact of the decomposing the abstract syntax tree into these individual relations. But that's sort of a neat benefit. We could potentially do better. Okay, before I go into how we can do better, I want to talk a little bit about how there's a little bit of context that we're missing here. I told you, we compute all of the opportunities for optimization. How do we actually apply those? Well, so the rewrite rule starts with plus sitting on top of 2 times. Every time, every iteration through this loop, we kind of take one of these opportunities for rewrite. We delete the corresponding nodes that we are rewriting out of their corresponding relations, and then we insert a couple of new tuples representing the new nodes. For example, we create this new plus node with a new identifier, and we insert a times node beneath it. The neat thing about this is that every time we apply one of these rewrite opportunities, we're only modifying, kind of by design, a small portion of the abstract syntax tree. And that creates a really nice opportunity for incrementalization. For those of you, do I need to define incremental view maintenance?
Let's say no.
Let's say no? Okay.
Please do.
Oh.
Okay. All right, so I've got a query, and I run my query on the data. I get a result. Cool. Now, I want to run my query on the database plus a couple of small changes, right? I get a new result. But this requires me to do a ton of redundant computation, processing all of the data that I've already seen. And so it's, there might be a way to kind of decouple the things that changed from the stuff that I've already computed. So if I have my original result already computed, there might be some delta query or Q prime that I can derive from Q that tells me how the final result changes. And ideally, in most cases, this Q prime is smaller, faster, better than Q. Cool? Yeah.
So on your last slide, you said you deleted. Is that really true, and does that correct this? Or like, because traditionally in semi-naive evaluation, I think, okay, it's all monotonic and that's all kind of why it works. Once you start deleting stuff, do things fall apart? Is that okay?
So deletions with incremental view maintenance work fine.
Okay.
I think I get a little bit into that a little later, but under there are some tricks you need to play, but it's possible to do incremental view maintenance over negated values if that is effectively what you end up doing, yes.
Okay.
Does that answer your question?
Yes.
And was there another pending question that, no? Okay, cool. It should go unstated, by the way. I'm going to talk. I'll occasionally ask for some level of feedback, but please speak up. Don't be shy. Okay, cool. So I'm not going to go into the nitty-gritty details of how this works in general, but broadly you can think of, if you're joining several terms together, you can pretty much think of incremental view maintenance as join distributes over union, so I can kind of pull the things that changed out. Every time I insert a plus node, I have to figure out if that plus node is sitting on top of 2 times nodes that are relevant, and if that's the case, that's how my result changes. It gets a little bit hairy if the same node type appears multiple times in the query, but the same idea is there. So, okay, we've got our original fixed point loop. Instead of doing that fixed point loop, what we could do instead is do one single pass with this type of iteration, pre-compute all of the possible rule matches, and then just iteratively pick one of them off of the queue, process it, and then figure out how how that queue changes over time. And we keep doing that until the queue is empty, and then we're set. Right, so the idea here is that, okay, right. So this is something where we could basically kind of take all of this and shove it into an incremental view maintenance system like, well, for us it was DB Toaster. Presumably we could do differential Dataflow as well, but you know, we plug it in there. So part of the problem we encountered when we did that at first was that these incremental view maintenance systems, DB Toaster certainly maintains a very large amount of intermediate state. And also, the intermediate state that gets maintained has to necessarily have a little bit of extra indirection. So if you go back, I'm not actually storing a pointer to the record, or DB Toaster wouldn't store a pointer directly to each of the child nodes. It stores an identifier, which you then have to dereference to get to the individual node. And the last observation is that most of these pattern matching rules can be checked really, really fast. So if we do a couple of redundant checks, maybe that's actually okay. So the thought here was, well, okay, we've got these abstract syntax trees. Why don't we just use the abstract syntax tree itself as the fundamental representation of the data? We still think about it in terms of individual relations, but now we're actually going to compute directly on the abstract syntax tree. So now, every time I insert a new node, I look over all of my rules, see if that rule matches any of the nodes, and then I add the node to my result set. All right, sometimes somebody calls me on this slide. Yeah?
Altering a particular node could cause another...
Oh wait, you've seen this talk already, so, but, fine.
We've got a plan.
All right, well, right, so if I insert or delete a node and just check that one node specifically, it's way faster, but I can't just check that one node specifically. So let's say, for example, I've got my rewrite here. I remove nodes 1, 2, and 3. I insert nodes 4 and 5. One of the things that a typical database would, incremental view maintenance system would end up doing is when I insert this times node, I have to look through every single other node that could potentially match that node. And what that's getting us is the fact that, well, you know, maybe the node that's sitting on top of it is something that might match my pattern. So that plus node that was already in there might the fact that I'm inserting this times node number 4 might create an opportunity to push use distributivity to push that product even higher up in my tree. So it could potentially modify an ancestor match. But unlike a typical incremental view maintenance system, I can actually bound how far I need to look. I can actually bound which portion of my database could potentially be affected. I might potentially just need to go one level up the tree. If, a little more generally, if I look at all of the rules in my system, I can kind of figure out how far in the tree any of these patterns show up, and then that basically gives me how far I need to search in my abstract syntax tree. It's kind of a fun insight. You figure out which, for all of your rules, how far you need to search, and you can essentially guarantee that you kind of hit the right subset. This turns out to do really nicely with, so we had this sort of synthetic benchmark. At the time, there was not really a ton of kind of systems doing Datalog at scale, at least not that we were aware of. What you're looking at here is, on the x-axis is the amount of time spent searching. The y-axis is the amount of searching for a rewrite, the amount of time needed to fully optimize a very large tree. The y-axis is how much memory we needed, and the yellow dots are basically kind of just iteratively traversing the tree. The black dots are what happens when you just sort of do the naive Datalog thing. You know that you essentially index the abstract syntax tree nodes that have by their type, and then kind of squished here all the way on the left. Up there at the top, you've got DB Toaster running in each of its 2 modes, and then we essentially like Tree Toaster was the system that we built. It kind of uses not much more memory than the typical, than just iterating over the entire abstract syntax tree, but you get this massive performance increase. So kind of the takeaway here is that even though we're storing the abstract syntax tree as an abstract syntax tree, thinking about that as if it were a database can get us much better performance overheads. What time do I need to finish?
So we're giving Max 45 minutes, but the lunch starts at 12:30, yeah?
Okay.
Schedule. Sorry, I don't have the schedule in front of me. I can look at it.
Okay.
He's got another half hour.
So, okay.
Another half hour.
Awesome.
Can I ask
Yeah.
you a question? How much would you say this is a statement about DB Toaster's approach to incremental view maintenance specifically? Because it has some opinions about how it's going to.
Oh, a DB Toaster materializes everything. It's
Right.
full whole hog dynamic programming.
Right. And there are other IBM techniques that don't materialize quite as much. Like they don't pre-materialize a lot of the joins in a multi-way join, which I think DB Toaster does to make lookups incredibly fast.
Yes.
But results potentially in a bunch of wasted work if you didn't need to. Maintaining those is expensive. And I wasn't entirely sure.
So the kind of takeaway, or the insight we had here is that joins are actually super cheap in our case, because the joins are essentially a couple of, assuming you have a parent lookup table for your abstract syntax tree, they're essentially a handful of pointer chases. Kind of the same thing shows up in graph databases. But we're not joining that. Joins are basically cheap, which is not usually the case. And so the materialization, the reason that most, what is it? The Zach Ives approach from, it's like I'm blanking on the specific paper, but like you can take the entire join plan and materialize intermediate steps in the plan, right? But that doesn't actually help you, because that materialization, you insert a node. I can track down maybe the 10 nodes in my immediate vicinity that could potentially contribute to that join, and I'm doing this a join over literally 10 nodes, and that's, I'm not going to get much of a benefit out of materializing literally anything on top of that. And that approach might be a little lower, but it's still going to be more than the entire abstract syntax tree. The abstract syntax tree itself is the index, if that makes sense.
Yeah, no, I understand. I understand the word. I was trying to place it in sort of the context of. I guess a different way to say the thing is there's a broad spectrum of ways to do IBM.
Sure.
And is this a new way fundamentally, or is it a realization?
This is a realization that all of the intermediate state can be reproduced almost for free from the abstract syntax tree itself.
So for example, we can take this potentially offline if you like, but there's definitely ways to do IBM for multi-way joins that require 0 additional memory. Besides
Sure.
the indexes of the base relations. You don't have to materialize anything, you can still get constant time updates to them. And I'm just wondering if this is like, yes, those techniques are much more appropriate in this case, is the conclusion, or possibly those techniques aren't widely known.
I need to think about that a little more, so maybe let's take it offline.
Chase it down and try to figure out if it's, it's the same thing as in and
yeah.
Cool. Or if it's that no one has ever figured this out, no one has ever seen this before. Each existing, delta join approach, for example, doesn't pan out if you try this.
Put another way, what we're essentially recomputing the entire, every time we do a join, we are recomputing everything from scratch. But we can do that really, really cheaply because the abstract syntax tree bounds how far we need to look. Let's maybe take it offline. Right, so we published this back old years ago, and kind of tied it to a couple of other things. So as I said, kind of one of the deep insights from this is that operating directly on the trees is really powerful. It also allows us to do some inlining tricks. If you insert a plus node, that there's no possible way that that's going to match against a rule that requires a times node at the root, for example. So we can play a couple of those games. Darshana is industried. Hopefully we'll finish her thesis, fingers crossed. But what she was working on there was kind of building work using the same sort of trick to, if you have a large number of rules, how do you kind of share some of the work between those rules? And that's sort of still ongoing thing in Tree Toaster. All right, before I move on to aggregation, questions, other concerns? Yes?
You said like that you started with, everything is a compiler, so everything is a database, like all these different compiler classes and stuff. And then you say that you can do this recomputing cheaply because you don't have to look that far, but that seems like that's not true of some more complicated program analyses and stuff.
Fully agreed. If you have aggregation, that is one place where if you have any sort of recursion, that is one place where materialized states, where you benefit from having materialized state. We're leveraging the fact that all of our rewrites are local.
Okay. Even simple things like variable renaming, things like that, probably you need to look further than.
Yeah, you would.
Anything involving basic analyses, things like that, it's all ends up being very non-local. You can, or the way we were looking at this is you can kind of split the difference. You can maintain just enough state for the non-local portions of the rule, and then kind of frame your rewrites as local transformations over the state derived by those non-local. So a thing that wasn't clear to me in the talk is what language you're writing a compiler for?
Our initial target was something like SQL. The evaluation was on, so this was back when we were trying to create a sort of compiler for dynamically built data structures, and so that's an entirely separate story. I won't try and motivate that right now, but
I think it's worth drawing out that the things that a SQL query optimizer does are going to not be entirely overlapping.
I agree.
The things that I think many of the PL people in the room
I fully agree, and I have spent the 5 years since atoning for my sins.
Sorry to contribute to that.
I guess on the other hand, though, I would say all the complexity of that makes it hard to do more basic stuff, and people in PL can kind of miss that, right? That's.
So what do you mean? All the complexity of what?
I think just all the non-locality of things just kind of makes us kind of think like, oh, you can just never do this, efficiently.
Well, so you can maintain the non-local stuff. I guess maybe a way of reframing the insight there is that for the portion of your rules that are local, you can do that incredibly cheaply, and that allows you to isolate the non-local portion, like variable renaming. You maintain this sort of dependency graph, right? And that is expensive, but on top of that, variable 1 and variable 2, A is equal to C. Once you have, A was assigned to C,
or vice versa, that becomes much cheaper. And I sort of hid this, but I define that as a relation, right? And if you can compute that A is equal to C as a relation, then all of the complexity of maintenance is in that maintaining that one relation. You can do that, but that makes the problem harder. Have I addressed your point?
Sure.
All right, cool. All right, so I'm going to make a claim. I hope this is not a claim that anyone finds particularly offensive. But so Datalog is really nice for expressing certain types of logic. So kind of if I want to express reachability, the Datalog has a really nice way of expressing that. If I flow from A to B, I want to know which particular nodes could affect a particular output. And given this sort of connectivity graph, I might want to ask a couple of meaningful questions. So like, does A flow into a particular sink? Does, how many paths are there that would get me from A to my sink? Except some of those questions are not really elegantly answered in Datalog. So like that, how many paths can I use to get from A to a particular sink? Datalog is sort of fundamentally about Boolean expressions. It's about asking, does this result exist, but less interested in sort of more quantitative properties. There are various forms of Datalog engines that sort of try and work around this, but the sort of typical approach is to explicitly define special relations that represent aggregates. So in Soufflé, I might have sort of a count aggregate relation. And there's a couple of drawbacks to this approach. So for example, if I'm trying to find the number of paths from A to B, I have to kind of define this special paths relation that is separate from what I'm trying to compute. And anytime I want to change my final query result, what I'm changing is not Q. I'm not defining new rules for Q, I'm defining new paths. And somewhere in the entire stack of things, I have to keep track of this, or else my results are going to be wrong. Now I have a whole rant for this. I'm happy to take it offline, but the kind of staring at this problem for a while, I'm reasonably confident that the sort of fundamental limitation that is leading to these problems and others is the fact that Datalog attributes are identified by, Datalog tuples are identified by all of their attributes. If I have this paths element a nil, that uniquely defines a specific tuple, and I might build more stuff onto my path, and that changes the identity of the tuple. You go back, Jim Gray had a paper on called data cubes that made this observation that data is sort of decomposable. You have a data set, typically the data is going to be decomposed into kind of two types of attributes. Ones that actually play a role in the identity, what you call dimensions, and then something that's more kind of a feature or property related to that identity or derived from that identity, what he called a measurement. So the question is, can we kind of frame if we're trying to
build aggregates into a Datalog system, it'd be really useful to have this sort of the same sort of decomposition where, yes.
So is it fair to think of the dimensions as the key and the measurements as the value?
Sure. Yeah.
Okay.
I will make. I'll make this a little more clear in a slide or two. But yeah. The dimensions identify the tuple, and then the measurements are sort of kind of a property. Functional dependency is not fully the right term here, but that general intuition.
Might you have multiple different measurements for the same
Yes.
collection of dimensions? Oh, so it's not.
So, well, I mean, functional dependency from the dimensions to each of the measurements.
Yeah, that's, okay, yes. So the measurement tuple is uniquely determined by the dimension tuple.
Yeah.
Yeah, okay.
Okay, right. So, how do we do this? Well, kind of still going back through the literature, there have been a couple of attempts at doing something along these lines. One that I've heard other people here talking about already, so I'll still give an introduction in case there's anyone who isn't familiar with the idea, but provenance semirings. And the idea here is very similar, except that every single table, instead of being a set or a bag of tuples, is instead a map from tuples, the dimensions or the identity of the tuple, to some sort of annotation. And that annotation, in some sense, captures the value or the measurements. The key insight here was that as part of the schema of this relation, you also attach a little bit of information about how that relation interacts with other relations. So here, the annotation is defined by a semiring. Mathematicians don't know how to name things, mumble mumble. Sorry. But the idea here is that the semiring basically tells us a couple of things about kind of characteristics of that annotation. So I've got a distinguished value representing nothing, a distinguished value representing there is one of these things, and then some properties on how I can combine the combine values using an addition operator, using a multiplication operator. I'm not going to go into too much depth here, but if you know how to add and multiply, you know what a semiring is. Right, what was I saying? So the semiring basically defines, the semiring here is used to define how relational algebra over these relations interacts with the annotations or the measurements. So for example, I can say if I'm unioning R and S and I want to find the measurement for a particular tuple T, I would take the measurement for the tuple T in R and add it to the measurement for the tuple T in S, using whatever addition operator my semiring gives me. Should I keep going? A couple of examples, like I have R and S. So R and S applied to tuple 1, I'd figure out what the annotation is for R applied to 1, or 1, what the annotation is for S applied to 1, 1, and 1 plus 1 is 2. One of the nice things here is that it also, the fact that we have a distinguished 0 value means that we have the relations are defined for all tuples, not just the ones that are explicitly present. Everything else maps to 0. So if I try and join R and S and figure out is 2 present in the result, I take the multiplicity, or I take the annotation of R, which doesn't actually exist, 0 times 1. Effectively, I have 0 copies of the tuple. And it turns out all of this plays really...
Can you explain that, just the upper right, the pi?
Oh, sorry, projection. So I take all the elements of R and I project the annotation. Project the tuple down to a different tuple. What I'm going to do is, here, I'll give you a concrete example. So I want to project all of the attributes away from R. What does that mean? I'm going to essentially take all of my tuples, I'm going to remove all of their identifying characteristics, and now I just have this big glob of tuples sitting in there. And what relational algebra would do if I was trying to, if my annotation represented, for example, the multiplicity. So I've got, what am I projecting? One copy of the tuple 1, one copy of the tuple 3, and if I remove that identifying information, lose the ability to distinguish between 1 and 3, I'm essentially, I have a table of 2 tuples, right? And so I can compute that by taking R of 1 plus R of 2 plus R of 3 plus R of 4 plus blah, 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 blah. And one of the neat properties of semi-rings is that 0 plus anything is the thing, so I only need to keep track of the things in the support of the relation 1 plus 0 plus 1 plus 0 plus 0 plus 0 plus 0 plus 0 is 2.
So the meaning of the T argument here is just that, I guess I'm trying to extrapolate if that were something that wasn't just the empty tuple over that.
So it could be the empty tuple. It could be if I have 2 attributes, maybe I remove one of them.
Okay.
Does that make sense?
Yeah.
You might want to map them in other forms as well. Apply a hash function to the value, for example. Okay, cool. I think I'm getting close to time.
15 minutes.
15, okay. All right, so this provenance semi-rings framework is really nice for a bunch of things, but one of the things I think is really powerful about it is that it decouples the meaning of a tuple from the way that it's represented. I could have a physical representation of a relation that contains the tuple 1 with 1 copy. The tuple 1 contains 3 copies. Fundamentally, this represents the tuple 1 with 4 copies, total of that. But I could equivalently represent it in sort of decomposed form as well as a composed form. And that is really nice for storing things on disk, because if you can process queries directly over that first representation, you can process them in a streaming manner. But side note, okay, so the semi-rings framework points out that if you plug in the natural number semi-ring, you basically get bag relational algebra. You plug in the Boolean semi-ring, you basically get set semantic relational algebra. Now, all of this can encode relational algebra, but doesn't support aggregation, and we would like to do that. So moving a little bit forward, DB Toaster sort of took this basic framework and added this new type of special relation. By that I mean, I can have a relation that sort of takes my attribute values and turns them into annotations. So I've got the attribute A. The tuple A equals 0 maps to the annotation 0. The tuple A equals 1 maps to the annotation 1. The tuple A equals 2 maps to the annotation 2, and so forth. And the neat thing here is once you join that relation with an existing relation, I end up with the aggregate value just kind of sitting in the annotation. Tuple 0 doesn't exist in my relation, also has a multiplicity of 0. Tuple 1 exists with multiplicity 1. Tuple 3 exists with multiplicity 1. 0 multiplies everything else, so we can get rid of that, and we end up with sum of r equals 4. Yeah?
This picture's making me a little nervous because it looks like, if I think about semi-rings with sort of Datalog plus lattices in the standard, like the Flix style way, it's very careful to make sure that the values stay in value space and you never leak them into the keys. where you could sort of ask a non-monotonic question about them. Like
We're going the other way.
well, here we're going the other way where
I'm getting there. I'm getting there. I'm getting there. I'm getting there. Right, so this is nice, it's closed, works really well for sum and product. The fact that sum and product literally correspond to union and join are nice, it's differentiable. Unfortunately, DB Toaster is sort of fundamentally tied to the sum product ring. Min is just not something it can, min and max are just not something it can easily express. But kind of moving a little bit forward in history, there's this paper by Yael Amsterdamer on kind of extending the provenance semirings framework to support aggregates. And her fundamental idea is that you kind of do the same thing DB Toaster does, but now you have sort of a fundamental distinction between the sort of what I'm going to call the existential provenance. Does that tuple contribute to the result, and then some sort of value. And in their case, they take they say, okay, we're allowed to kind of combine those two, but we need an operator that fulfills specific criteria. And they identify the criteria that they're looking for as those of a semi-module. Again, mumble math. And the idea is if you can define this operation for your aggregate, then the output of this operator is effectively a monoid. And that opens up that makes it possible to start reasoning not just about aggregates with nice distributivity properties that connect to union and join, but also other types of aggregates like min and max. What is a monoid? It's just a plus operation. Right. So for example, if I'm trying to a monoid needs some sort of set of elements, an operation over pairwise operation over those sets, and then a sort of default empty value. So I can express min, for example, as the monoid over the integers, where I start from infinity and keep taking the next lower value, infinity, integers plus infinity. Right. Okay. Cool. So.
Can I interrupt? Actually?
Yes.
So I get semirings, of course, and, and the semiring provenance stuff. We read those papers. But so what is the, like, why not just use semirings? Like, what's important about the
so there are two things. The first is that, so let's take min, for example, right? What does it mean to take two tuples annotated by minimum values and join the results together? That makes sense if your operation is, if you're trying to compute a count, but it doesn't make sense to join two. I mean, maybe you have some semantics, some specific semantics you're looking for, like if min times forms a semiring over positive integers, min plus, and then your join operation is kind of adding elements together. But in general, there's no sort of default min semiring, right? So that's where we run into problems. Question? No? Okay. All right. Okay. Cool. And I think I am running out of time. So let me.
6 or 7 minutes.
Okay. So. Okay. If I. And this might be what I think this is what Max was getting at earlier. If you're trying to take values from the tuple and kind of push them into the measurement, that's usually something you can do fairly safely. But more frequently, you want to go in the other direction. You want to take values from the annotation and turn them into part of the identity. So this occurs, for example, if you want to compute an aggregate value and use that aggregate value as part of a join attribute. So let's talk a little bit about how that might be expressed in this sort of annotated relation framework. So fundamentally what we want to do is we want to go from tuple maps to annotation and turn that into just a tuple. So two kind of questions come up there. One, well, what happens if we have just this multiple copies of the tuple? This is one of the fundamental places where we absolutely need to be working in this, what we call coalesced representation of the data. You absolutely need to know exactly the right value, the full value. And a corollary of that is that the coalesced this process of taking values from the annotation and turning them into part of the identity is really, really expensive. So that's kind of observation number one. Observation number two, well, okay, we've got this mapping from A to B. What do we annotate?
A question that I also share.
Yeah.
So why is this so expensive?
I do it all the time, so I'm curious. Like something must hurt for you in the context you're in.
It requires a shuffle. Bluntly, you need to group all of the instances of the tuple together, and shuffling is not something that you can do easily in an external memory system. Does that answer your question?
I have follow-on questions, but I don't think it does require a shuffle, but perhaps we should.
It requires that you use some sort of external memory join or external memory aggregation operation, which I believe more or less boils down to
Linear scans through an LSM tree or something like that.
Yeah. Okay. We'll talk later. So the second thing is, well, okay, we've lifted this value b. Now the resulting tuple has to be annotated with something, and well, what do we annotate it with? We had a couple of choices here. We ended up just picking a unit value because that's fairly easy. Okay. Mumble. We ended up making a couple of changes to relational algebra to support this sort of annotated reasoning about tuples. Most of it is pretty much the same as what you would encounter normally in relational algebra, but there are four changes. So we have a way of taking values and annotations, taking attributes and lowering them into the annotation space, and you need one of these semi-module operators to combine them. We have a way of transforming the annotations directly. There are some constraints on the types of functions that you can use this for safely. And then we have a way of lifting annotations back into the annotation space, and as I said, this is kind of the expensive operation. The final change is that unlike typical formulations of the provenance semirings or the DB Toaster style aggregate calculus, we allow different relations to have different types of annotations. And that means that the join operation has to be annotated with a specific type. Essentially, the join operation has to know how to combine the annotations on both of its inputs. And again, that essentially needs to be one of these semi-module operations. Since the product operation of a semi-ring is a semi-module over the semi-ring itself, this sort of devolves back into provenance semi-rings in the general case.
All right, so I'll leave you on the kind of really cool thing that has sort of popped out of this, which is like if you take the annotations, here we're expressing every relation atom is the tuple where you normally see it, and then the annotation after an equal sign. So Q of H equals E is defined by R, S, R value. Different systems essentially have different limitations on the types of queries that they can express. Where are we? Souffle requires that the annotation that gets passed up here is essentially defined by exactly one of the atoms, the aggregate atom, essentially. All of the other atoms exist, or can exist, more atoms can exist, but they can only serve to ground the relation. DB Toaster, on the other hand, kind of applies this distributive property where E has to be defined as the product of annotations from all of the inputs. And again, there is overlap between these. That annotation could be 0 or 1, and that gets you this sort of grounding behavior. But each of these, the two sets of queries that each of these systems handle is overlapping but distinct. And one of the neat things to come out of this work is that we can take this formulation of the query, we can translate it into this query structure that includes lifts and lowers. You can have that here. But if you do all, you can then essentially frame a number of simple algebraic rewrites over that language that in effect recover, if you sort of optimize out these lift operations, you get back whichever of these evaluation strategies makes sense in the case where it's feasible, and yeah, otherwise, essentially we generalize both the souffle style of grounding atoms and the DB Toaster style of using distributivity. Questions?
I think we asked a lot of questions.
Yeah.
So, you know, yeah. Excellent. Thanks so much. So the next talk is by Max, and he's going to talk about e-graphs.
Indeed, I am. And this is, you know, I want to state some of the same things. Please feel free to interrupt at any time. This is sort of an anytime talk. I'll get through what I get through, and you know, I'm happy to discuss anything offline and so forth. So yes, today I'm going to be giving a little bit of a crash course on eGraphs, and then we'll get to Egglog, which is sort of a combination of this eGraph idea plus Datalog. And this is sort of the idea that got me into Datalog and logic programming. It sort of came by way of this approach, and it's a really neat, rather simple sort of idea that has a lot of the same sort of characteristics as Datalog. And we'll see what that looks like. And you know, Egglog was our journey to sort of combine these. And then at the end, I'd like to talk about sort of, you know, looking back on this whole process of combining eGraphs with Datalog. What are the qualities of this neat idea, eGraphs, that allowed it to be integrated so easily? And I think that's motivated one of the goals that I was talking about at the beginning, like sort of modular logic programming, right? How can we bring other neat ideas, neat tricks into the fold with logic programming in a way that integrates nicely? So let's get started. You know, sort of starting off with some pitch. We have this whole eGraphs community business, so if you like anything that I'm talking about, we've got a Zulip, we've got a workshop, and there's videos, and there's a monthly seminar. It's all on Zoom. You can check it out, egraphs.org. Okay, so what's an eGraph? Maybe you have never heard of it. It is a data structure. So when I say eGraph, it's just it's a graph-like data structure, and it is first used in the verification community. It was invented by Greg Nelson, I think in like 70 something, and it is the data structure for reasoning about equality over uninterpreted functions. And so if you're familiar with SMT solvers, this is sort of the core theory. It's the, I don't know anything about integers or about reals or strings or bit vectors. It's sort of the least you can get away with. All we know is we're making statements about equality, and we're assuming that functions indeed behave like functions in that they map identical inputs to the same output, okay? So the input to this theory of equality with uninterpreted functions, there's a bunch of equations that look like this, right? They equate terms. Here x and y are just constants of, just constant terms. And so we can build up terms using things like constructors, and we can say, hey, these things are equal. And then we might want to later on ask questions, saying, hey, in my theory of equality with uninterpreted functions, if I know this thing, right, do I know this thing, right? Do I know this other thing? And so let's figure it out together, right? If we know f of x plus y happens to equal x, do we happen to know this larger thing, which is like f of x y of y, does that equal x? I don't know. Let's find out. The way you answer this, again, is with the eGraph. It is the data structure for reasoning about these kind of questions. What does an eGraph look like? Well, it looks awfully similar to an abstract syntax tree. You want to get some sharing in here, so you want to use an abstract syntax DAG, if you will. So if we mentioned x multiple times or y multiple times, then we will just point to those things. So those are the solid arrows. So we've represented f of x, y here with this f takes x and y as arguments. And then we have this additional dotted edge that records any of our equations. Right? So here we say our input to our problem here is f of x, y. So this f is equal to x. So we just draw a little dashed line. This is an undirected edge. Right? It's equality, it's symmetric. And then we want to answer the following question, right? Is this big ugly term equal to x? I don't know. Well, to find out, let's put the big ugly term into the eGraph. And to do that, well, like I said, we want to capture all the sharing that we can. So we add f of xy, f of fxy. Well, we already know the fxy is already in here. So let's reuse that. And the second argument to this big F is y. Well, that's already there, so let's reuse that. So all we have to do is add this new F node, hook it up to the right arguments, and we're good to go. And we're trying to figure out, hey, given the axioms of our theory, what our theory is able to prove, is it possible to show that there should be an edge, one of these dotted edges, from this x to this f? Well, we have a couple tools at our disposal. We're reasoning about equivalence. And so we know that it's symmetric and transitive and reflexive. So there's an implicit self loop for all of these nodes. This is undirected, it's symmetric. We can go backwards. And we only have one edge so far, but it is in fact transitive. So if we're allowed to sort of 2-hop or 3-hop, n-hop equality. And crucially, we have this one other trick, which is these are functions. And so we can reason about congruence, right? If we know that our equivalence relation, the dotted edge, says that two things are equal, well then calling a function over those two things should give you equivalent outputs. Okay, so that's the one thing that the eGraph can do for you, right? It can store all these terms in this nice sort of compressed DAG, and it allows you to ask questions about these equality edges. So if this were an E-graph, and indeed it is, then it would very quickly run the congruence closure algorithm, which is an old algorithm. It's very efficient, and add the appropriate edges, right? As soon as we add this f, we should be able to figure out that, hey, well, because, let's see if we can figure this out here. Because it is, we have the same constructor, f, and this is a binary function, so if both of the arguments are equivalent, then the output is equivalent. They both have as right argument y, which again is linked with a self loop, so we're good to go. And their left argument is linked by sort of the only edge that we have here. So indeed, we can link up these two f's with another edge. And I said that we get to use transitivity, right? And so we can take our 2-hop over these edges and say, hey, our original query, that is true, right? So I've basically described for you the eGraph data structure and how you can use it to solve this, these problems over equality of uninterpreted functions. And this is what the data structure was designed for. So sometimes this problem is just called congruence closure. The eGraph is the data structure that was designed for this purpose. It provides a decision procedure for the quantifier free, so there's no quantifiers to be seen here. Conjunctions of equalities for these uninterpreted functions. What about quantifiers? What do we do? So say that one of our inputs was not a grounded equation of terms, but something that's quantified. Say that we know, the user has provided this, that for every x, f of g of x is equal to h of x. Well, the congruence closure algorithm, as we've sort of stated it, is only for ground terms, so it doesn't really offer us anything here. But what we can do is this procedure called e-matching. And all of this, the way and the terminology that I'm presenting to this is just all stolen from the SMT community. So e-matching is a procedure for doing quantifier instantiation. This is used by all of the popular SMT solvers. It's sort of the dumbest possible algorithm for doing quantifier instantiation. So maybe you're lucky and you are in some nice theory where the solver actually does have a decision procedure for whatever quantified formula that you're using. That's great, and the solver is going to do pretty good. If it can't do that, what it's going to do is do e-matching, which is saying, okay, well, we only have decision procedures for the ground parts of this theory, but the user has handed us something that's quantified. And so what are we going to do? We're just going to stamp that thing out and come up with as many ground instances as we can. This is, of course, incomplete. There might be ones that you don't find, and it's also non-terminating, but it does pretty good in certain situations. And so the way that you do this is you look at your quantified axiom. So this is the one from the previous slide. We choose a trigger. Typically, the properties that you want out of this trigger are something that it's a fragment of the formula that covers all of the quantified variables. So here we're just going to choose f of g of x. There's a whole art to selecting the right triggers for quantifier instantiation. If you've ever used an SMT solver, you've maybe gotten bit by this bug. Yes?
Is this something that the solver is doing via heuristics, or?
It will do it via heuristics. There's a lot of papers on those heuristics. You can also do it manually. You can say colon in your some extra syntax in the SMT language will allow you to typically.
SMT lib, you can do this.
Yes, you can manually specify the triggers typically. And of course, the choice of trigger will affect how incomplete your thing is. So proceed with caution. Okay, but now that we have chosen a trigger, what do? Well, let's look for things in the eGraph that look like f of g of x, right, for any x. And then if we find an instance of the trigger, let's add h of x where X is whatever the thing that the trigger was found. And we added an equality edge here, right? Because this is the rest of our formula. If we found f of g of x, well, let's stamp out an h of x in our egraph. And the formula states that these two things should be equal. Let's make them equal. Okay, let's look at an example here. Here's a simple egraph. What is this one storing? Well, we've got f of c, we've got g of a, and we've got g of b. And the g's are equivalent, and the g's themselves are equivalent to c. Okay? And we're going to do e-matching here for this axiom, and the trigger that we've chosen is f of g of x. And so we're looking for instances of f of g of x, and we can see two here. Crucially, this is sort of the big idea in e-matching. When we are looking for patterns in an e-graph, we are allowed to traverse these equality edges for free, right? So if you just look at the dark black arrows, you'll notice that there's no f of g of anything, right? But we are allowed to traverse these equality edges, right? And so we can say, okay, there's f of g of a, so x equals a, that's one sort of substitution this would yield, and likewise we can traverse it twice and get f of g of b. Okay, and so we have found our substitutions, and so the rest, to actually stamp out instances of this formula, we need to add a bunch of h of x's, and here I've already linked them up to the f of g of x. Great. Any questions on this so far? Sort of very mechanical. Yes?
Is the assumption that everything in the graph is grounded?
Yes, egraphs are a data structure for holding grounded terms, right? So everything is grounded, right?
I looked at from the database world, this feels very much like the chase.
Yes, we're going to get there.
Oh, okay.
Yes. Exactly. Okay, so I think that sort of wraps up the intro part of this. So egraphs are a core data structure inside of all the SMT solvers. It's the core data structure, right? You have the egraph in the center. So you have sort of a SAT solver on the outside. You have an egraph in the center. And the egraph is responsible for communicating these equalities between these theories, right? So maybe you have one that can reason about linear arithmetic, one that can reason about strings. How do these two talk to each other? Well, they talk to each other through this theory of uninterpreted functions, right? This is sort of the thing that sits in the middle. Egraphs are the data structure for reasoning about equality, uninterpreted functions, and congruence. And they also give us a way to, a very dumb way, but a very general way to reason about quantified statements. It's incomplete, but we can use this e-matching technique to just sort of stamp out many ground instances of some quantified formula, okay? But we have to do trigger selection. So that all has been done a long time ago. And just more recently, in 2009, Ross Tate and his co-authors came up with this technique called equality saturation, which is a way to basically crib all of that infrastructure from the theorem prover community and use it for program optimization. Right, so it's inspired by the way the egraph is used at SMT solvers, but we're using it for something totally different here. I have the luxury of looking at all this work from a distance now, and so I really think the key idea behind this equality saturation business is to break program optimization, and note the scare quotes around optimization, right? We're not doing mathematical optimization here. There's no, you're not going to get the minimal thing out, right? We're using e-matching under the hood here, so it's incomplete, and so this is program embetterization. You're going to get something hopefully better. We're going to break it into two parts. We're going to use the egraph and e-matching to explore a space of equivalent programs. We're going to use e-matching to sort of implement term rewriting, and we'll see how that looks like in a second. And we're going to build a big, fat egraph. So it's a rather large egraph on your disk, but as we'll see in a moment, that represents an exponentially larger than that, doubly exponentially, in fact, larger than that space of equivalent programs. Okay, so instead of classical rewriting, where the state of a term rewriting system is just the term that I'm working with right now, and when then I rewrite it, I throw out the old thing, and now I have a new term that I'm working with. Our state is this, basically all of the terms that we have ever seen, right? We never lose any information. It's totally monotonic. I mentioned here that we're using the egraph and e-matching, which are of course parts of an SMT solver. One of the things that I'd love to chat with you all offline about is, could we use other parts of an SMT solver, right? There's these other theories that could help us to explore, build up this big space of potentially interesting programs, and that's something to talk about offline. And then the second half of this is now a combinatorial optimization problem. Right? We did this exploration phase where we just are building up this big database, if you will, and in fact it is just a database of programs, and then we want to pick a good one. So we've sort of reduced program optimization to an exploration phase and then a combinatorial optimization problem. This problem can be either very easy or very hard depending on the properties of your cost function, and we'll talk more about that in just a second. So yeah, that's the big idea here, and if you take nothing else away from this talk, a quality saturation is the thing that uses this data structure from SMT solvers and splits up program optimization to an explore and then choose phase. All right, so let's look at an example. Say we are trying to optimize this program, a times 2 divided by 2 in our, some language of simple arithmetic, into a. Right? Again, I'm interested in program optimization, but the same techniques can be used for proving things equivalent here. The typical way you would do this in a compiler is with term rewriting, right? You would use you would come up with some axioms and you would orient them in the correct way. Here are, in fact, the ones that you would need to use, and thankfully I've written them left to right, so you would want to orient them this way, and you turn this into a term rewriting system, you press go, and you can optimize this program. That's great. There's a lot of other axioms over the reals or naturals, whatever domain this is, that are useful in some contexts, but not so useful in others. There's a number of reasons they might be not useful, and we'll encounter some of those in just a moment. So first, what does the sort of happy path of program optimization look like? If someone has given you a slide with exactly which rewrites to apply and in which order, you can do this. So let's just apply them one by one. We do this first rewrite to sort of re-swizzle these multiplication and division. Then we can do cancellation, and then we can do another cancellation here, and we've optimized our program. There's a number of ways in which term rewriting in the classical sense can go wrong. And the thing I want to emphasize here is that these are not dumb rewrites. These are rewrites that in certain contexts could be very powerful or a good idea. So the first one I think is the most interesting. So here I'm applying this first rewrite on the bottom right here. X times 2, say we're going to lower it to a bit shift by 1. Right? This is a good idea. We optimized our program. Hooray. In doing so, we have sort of fallen into a local minimum, right? We have made a locally good decision, right? This is sort of the rewrite that applied that sort of reduced the cost the most, sort of greedily, but we got stuck, right? Now we can no longer see the 2's, or the necessary 2 that would allow us to eventually get our cancellation and do the sort of uber optimization that we were looking for. So that's unfortunate. So in a real term rewriting system, in a compiler, you would have to massage your heuristics to avoid this, or you could backtrack, or you could prove some nice properties like confluence about your term rewriting system to avoid getting into this pickle in the first place. But all of those are either expensive or hard to do. Okay, some other pitfalls is maybe you have a rewrite that can easily get you stuck in a cycle. For traditional term rewriting, if you want to show that it terminates, one way or another, you have to come up with some measure that the rewrite is always decreasing. right? You want to say that, hey, maybe it's cost or some sort of more complicated measure of the terms, and all of my transformations make this number go down. That way I can't get stuck in a cycle. But of course, or typically, a transformation like this is not going to preserve that property, right? Because you can always just apply it to itself, right? This is a problematic rule for those kind of term rewriting systems because you can just apply it to itself and you ended up back where you started, right? And now your term rewriting system is infinite looping. And finally, again, along the same lines, right, if we want to decrease a measure, most of these measures are going to have some relationship to the size of the term. And so rewrites that not only increase the size of the term, but just outright include the left-hand side are very unlikely to decrease that measure, right? They're probably going to increase it. And so this can lead to sort of infinitely blowing up. You're not getting stuck in a loop, but you're getting stuck in a sort of infinite path here. All of these are sort of bad failure cases. You can imagine how for certain programs, these are good ideas. Maybe they help you unlock another optimization, or maybe in the case of the first one, they are just the optimization you're looking for in that situation. So there's this difficult question, when you are optimizing a program, which optimization, which transformation do you apply at which time? There's a lot of literature on how to be smart about this. Maybe you can prove some nice properties like confluence. The equality saturation perspective, again, is sort of the dumbest possible solution here. We're going to apply all of them all of the time. And we're going to make it hurt less than it would otherwise hurt. It can still explode, but there's a lot of situations in which this can still be pretty practical. And eGraphs are going to save the day here. So what does this look like? Let's do the same program optimization problem, but let's do it in eGraphs this time. So we have our same term that we were just looking at. I've drawn it out in an eGraph here. And so please excuse me for sort of switching notations. Sometimes I draw eGraphs with, as an AST with these dashed lines connecting equivalent nodes. And sometimes I use the dashed lines as little boxes that sort of group together the connected component of that equivalence class. So I think for the rest of the talk I'll be using this notation. So the E nodes are the AST nodes. These are the white boxes. And they're grouped into these E classes, which are the dashed boxes. And typically in this notation, we say that an E node, which is just an operator, right, takes as children not another node, but a class. And we'll see why that's important in just a moment. But basically, the essence of it is that, hey, if A and B are equivalent, you shouldn't care which one you take as an argument. Right? The whole point is that we've determined that they are equivalent, and so you just take the class of those two things as an argument. There's no distinction between them. Okay, and now we can define this notion of representation, which is, we've got this funky data structure, which is kind of like an AST, but not really. But we can define this notion of representation saying like, no, if you look and sort of follow the edges and are allowed to choose things within an E class, you can find this AST for real in the eGraph, right? And so it may represent, in fact, we'll see that you can represent a lot of things, in fact, an infinite number of things, in a rather small eGraph. All right, now that we see the eGraph for our input term, let's start doing equality saturation. So let's start exploring alternatives. The first thing that we're going to do here is take our, we're going to first do our potentially dangerous rewrite. This is the one that was a wrong turn a couple slides ago, but we'll see that it all works out in eGraph land. And so how do you apply a rewrite in eGraph land? Well, it's nothing other than using the E-matching technique that is used for quantifier instantiation. We're going to look for instances of the left-hand side. We're going to instantiate the right-hand side accordingly. Then we're going to connect them up, put them in the same E class. So let's look for instances of the left-hand side. There I found one. And let's add, so this instance of the left-hand side is A times 2, so X maps to A. And we add A shift 1, and we make sure that the shift node, the sort of the root of that, goes in the same E-class where the match was found, which is where the times was. Great. Now that sort of embiggened E-class represents two terms, and this notion of representation propagates upwards. So this E-class with the division node, even though it has one node, represents two programs. And you can perhaps sort of see where we're going here. If you have a sort of a ladder of E-classes that are all using the one below it, and there's a bunch of choices in each one, you're representing an exponential number of programs in a linear amount of space. Great, and so the moral of the story here is that we haven't lost the times, it's still right there, right? And so if we just keep going, we can get back on the happy path eventually, right? We haven't lost the crucial times that allows us to do this re-swizzling, and we don't have to follow what's going on with the E-graph here, but we can still do this transformation, and it all works out. And here's me sort of doing the rest of them. The only thing that I would like to call out on this final slide is that, can you see my cursor? Great. This multiplication node, you will see its left child, if we follow, is its own E-class. Okay? So cycles are totally fine, and that means that this E-class represents the terms A times 1, A times 1 times 1, A times 1 times 1, and so on. Right? So we can represent, in fact, an infinite, certain classes of infinite terms in a very small space in an E-graph. Cool? And so this approach called equality saturation gets its name from the fact that if you keep turning this crank, and there are certain nice properties about the rewrites that you're using to do so, you can saturate this E-graph, right? You'll notice that you're turning the crank and nothing is happening, and you've reached a fixed point, right? And now you know all of the equalities that could be derived from the rewrites that you gave it. Now, unfortunately, I think equality saturation is a pretty bad name because in most applications where we found this is interesting, equality saturation, reaching saturation is either technically possible, but very impractical, or outright impossible. You are not theoretically guaranteed to reach this by any means. So, again, it's sort of equality in beginning, right? We're not
saturating up to a bound.
Right, sure. But that's where the term gets its name. And then finally, we're doing program optimization here, and so now we just got this big E-graph. What do we do with it? Well, recall this notion of representation. This E-class that I'm pointing to represents our input term and, well, an infinite set of other terms. And what we would like to be able to say is, hey, give me the smallest element of this E-class, the smallest term that is represented by this E-class according to some cost function. And you can do that with a procedure called extraction. I have some more slides on extraction. Probably not going to be able to reach them. Basically, depending on your cost function, this is either very easy. If it's something AST size, that's very, very easy. If it's something like DAG size, or something where sharing is accounted for, it's much harder. It's NP hard. And there's a lot of juicy problems in the extraction sphere, but I think I'm just going to move on for the sake of time. Okay, let's put it all together. Equality saturation is a procedure for program optimization where you take your initial term and you make that sort of trivial E-graph that just looks exactly like the AST, where every every E node is in its own E-class. Then you start turning the crank. Ideally, you would reach saturation, but sometimes you don't. And then you extract an optimized term. Okay? So one of the things that we've started building on this technique is more than syntactic rewriting, right? There's a lot of applications where you want more than just a syntactic consideration of equivalences. You want to do some sort of semantic interpretation of these terms, right? So consider we are writing a program optimizer that wants to do something like constant folding, right? That'd be an awful lot of syntactic rewrites to put into our system, right? We'd have to have one for every pair of natural numbers. There's a lot of those. There's a lot of program analyses that, of course, want to consider some sort of abstraction. these are basically anything that fits into the sort of the broad envelope of abstract interpretation, right? Of course, we want to have a sort of understanding of the semantics of these things. And so one of the things that we have built on top of this is this notion of, we call them E-class analyses, or these are program analyses modulo equality. We've got a nice uniform interface that works for many of these kind of analyses. And we also have, if you look at the paper, an understanding of what these analyses mean over E-graphs. So let's take a look at what this looks like with an example. Let's do constant folding, everyone's favorite sort of introductory domain for abstract interpretation. So what we're going to do for these E-class analyses is we're going to attach some data to every E-class, right? Here we're doing constant folding, and so we're going to attach, an optional number, right? We're in a very simple sort of constant lattice where we've got all the numbers, and then maybe we don't know. And then as we add E-nodes to the E-graph, we just try to evaluate them. We run our transfer function, if you will. And when things are merged, we just do the lattice operation. In this case, it would be the optional OR. So let's see what this looks like. In the green boxes here, I'm putting our annotation, our abstract interpretation. So we can't say anything about A, we don't know just yet, but of course 2 is 2, and that leads us to say not very much about these other two things. The nice thing about these E-class analyses is that as the E-graph receives new equalities, one thing that it's automatically doing is patching up congruence closure. That's what it means to be an E-graph. It always has to be representing or computing the congruence closure. But along the way, it can also repair, if you will, fix up your abstract interpretation. So say that we learn that all of a sudden that A is equivalent to 2. We merge those two E-classes, and now, in this case, we're sort of recomputing the whole thing, but you can imagine that this is more local on a bigger E-graph. It propagates up, right? All of a sudden, we can now say something interesting about the multiplication because both of its arguments have a constant value, and so on. Yes?
Is it relevant that there was previously an empty green box and then the green box went away? Does that symbolize the fact that that got thrown away and recomputed, or is it just the slides?
That's just the slide,
okay,
right? Basically, when
like this is
when A and 2, when the E-class for A and 2 get merged, you don't have to recompute anything. You just you take the lattice, join of them or whatever. And we instantly get 2. And then we now have a responsibility to recompute our parents, not only for congruence, but for these interpretations. Yes?
This seems like it would interact incredibly badly with widening.
Yes, probably. We've only done very simple abstract interpretations that has proved really useful so far. We should talk about widening. I think that'd be very interesting.
Okay.
Yeah, let's talk about that offline. And it propagates up, yes. Great, and here's basically everything I just said in sort of more formalness. I'll just sort of move on from that. A really nice example of this is with interval arithmetic. So unfortunately, I'm just going to zoom through the sort of introduction to interval arithmetic. Hopefully we sort of know what's going on here. But if you do interval arithmetic modulo equality, so I guess maybe I'll just go back here. One thing that is frustrating about interval arithmetic, that it is very brittle to the exact syntactic representation of the term you are doing interval arithmetic for, right? So say, where's my cursor? I know that x and y are in certain intervals. Here's some term. If I just apply the normal laws, your standard abstract interpretation for these intervals, you'll get that this thing is in this interval. And here, trust me, I did the algebra. This is equivalent to this just via basic algebraic manipulations. You get a different interval. And here you get yet a different interval. That's very frustrating. But if you did this in the E-graph, the intervals have a very natural lattice structure. you get to take the intersection of these things. And so while you're doing your abstract interpretation, you can also be doing eGraph rewriting via simple algebraic laws, and it can be making your intervals more precise, right? In fact, it can be making it more precise than any of these representations. It's not that there's a best one, right? You get to take the intersection. So this has been sort of like the nicest example that we have run into. Okay, given that I only have a couple minutes remaining, I'm going to skip ahead to, well, extraction's cool, there's some fun algorithms there, semi-rings. Beta reduction, partial orders are also cool. All right, let's talk about Datalog. Okay. So, why connect eGraphs and Datalog? Well, the real reason why we sort of sought to connect them is that it felt painfully obvious that they are the same thing. Like the benefits of both of these approaches felt the same, and the actual approach also feels the same, right? You start with a small database and you turn this crank of rules which monotonically look at the database, add more stuff to the database, and you hope you reach a fixed point. In this case, in Datalog, you're guaranteed to reach a fixed point, and hooray, right? They both have a very similar vibe in that way. This is basically all I just said. Another big thing is that in equality saturation, the bottleneck is e-matching, right? I'm looking for instances of these left-hand sides in the eGraph. The eGraph is big and complicated, and that's the thing I'm spending most of my time doing. If I could frame this as a Datalog problem or a databases problem, well, I get to benefit from all of the literature on executing joins efficiently and incremental maintenance for Datalog and all of that good stuff. Right, and just to drive this home, right, e-matching is a backtracking search for substitutions that satisfy a formula with respect to sort of a grounded database. And that sounds a lot like answering a conjunctive query. Thankfully, Oliver's sort of set the stage for me here. The sort of final ingredient here is, well, how do you think about terms inside of a database? And there's a couple of ways to do this, but one very natural way is to just basically flatten everything. So for every kind of operator, where's my cursor? So here for the function symbol plus, it is an arity 2 function, so we're going to have an arity 3 relation, table if you will, where the first two are, of course, the arguments to the plus, and the final is just the final column is just some name for the result, right? So here, this first row corresponds to this plus, right? This is, the row is the plus, and it maps BC to BC, if you will. And then the second row is this plus, it maps A and BC to ABC. Great, and this plus a little extra sauce is what allowed us to implement egglog. Egglog is nothing other than just a datalog plus functions, or ADTs, if you will, which are a somewhat standard datalog extension. And then the only secret sauce that we brought is this notion of extensible equality. So you can just have in the head of your datalog rules an equation, right? You could say that, hey, all of a sudden, A is now equal to B, right? Let's merge these E-classes. I have some examples here, and I'm just going to click on one just to show you that they are real examples. So let's do...
Maybe not the first.
Let's do this one. So this is a live interpreter. You can go play with it. So just to...
You just hit Control plus.
Yeah, several times.
Yes. Great. So let's ignore this data type declaration for a minute. So I have two relations, edge and path. They're both binary relations over nodes. Hopefully this is smelling familiar. I have my usual rules. And let's ignore this make constructor. I have a couple edges, right? And I can run the standard transitive closure stuff. It's just a data log. What I can also do is at the top level or in the head of a rule, either way, I can merge, unify, I can equate two of these values. So here, I'm doing graph reachability. I can say, hey, these two nodes, they're the same, right? So this is like taking in a graph, taking two nodes and munging them together such that all of the in edges are now to this one supernode and all of the out edges are out from the supernode. And if I click run here, you get this, unintelligible graph viz thing, which is showing you the database, but you'll have to.
This is not unintelligible by our standards.
Oh, you can generate arbitrarily big ones here, and they get pretty big pretty fast. But you'll have to take my word for it that indeed, you can find the paths that were not findable before because now these nodes are merged. You can also do. Let me go back here, just to get one more sense of the flavor. Here we're doing something that's more classic equality saturation. We are building up terms in some made up little language. Here are some terms, and we have some rewrites that say, addition is symmetric, and you can distribute and so on. And we can indeed prove that this first expression is equal to the second expression. And it does work. Great. So I'm going to wrap up here in just a minute because I know we want to head to lunch. The moral of the story here is that this is just way better in a lot of ways than our initial implementation of equality saturation. One big reason is that we have a sort of a query system, and so we can do query optimization, and so our e-matching is like 10,000 times faster because we can avoid taking products and actually do joins and things like that. It's especially much more efficient for these certain kind of program transformations that are called multi-patterns. So to give an example of these are basically non-local rewrites in your program. So say we're doing some sort of matrix multiplication kind of application, and here I have a program transformation that's sort of split into two parts. If anywhere in my program I see A times B, and then anywhere else I see A times C, doesn't really matter where, I can sort of together transform them into making one big concatenated matrix, doing one multiplication and then splitting out the result, right? So this is sort of a rewrite rule that has to happen sort of in a coordinated fashion. In the conventional approach to e-matching, this is super inefficient. It basically is taking a bunch of Cartesian products where your bog standard Datalog doesn't have to, and so we can be a lot more efficient here. And we get free incrementality, and it's a lot faster, and da-da-da-da. The one thing that I want to drive home here is that there's this really nice interplay between functions and equality. So say we have f of A equals B and f of C equals D. Well, equality is extensible, right? So maybe the user just outright asserts that A is equal to C, right? We now, because we're implementing an egraph, right? Well, we have to do congruence closure. Well, the thing is, in the databases world, this has a very nice analog. In Egglog, we want certain of our relations to actually have functional dependencies, right? So this F relation, which is a binary relation, actually has a functional dependency from its input to its output, right? And so congruence closure actually sort of falls out from maintaining these functional dependencies, right? If you assert that A equals C, then all of a sudden, these two tuples amount to a functional dependency violation, right? You have equivalent inputs all of a sudden mapping to two outputs, and you have to do something to resolve this. And in Egglog, you have a choice. You can either say your output is some sort of lattice, say min lattice, max lattice, standard sort of Datalog plus lattice's extension, or you can sort of choose to be in the special lattice of terms, which is to say, hey, we need to patch up a functional dependency violation. All of a sudden, f of A, which equals f of C, maps to B and D. How do we choose between these two things? Well, if you're in the special term lattice, you don't have to. You can just say, let's make those two things equivalent as well. And that amounts to congruence closure. So the machinery for, to come back to the chase here, for chasing down these EGDs is exactly the same as for doing congruence closure. And in fact, the implementation of egglog is nothing other than do datalog, do one step, one immediate consequence of datalog, do congruence closure, do datalog, do congruence closure, and then so on. And so I think I'll just wrap up there, but to sort of close on a note closer to my goals here, I think it's awfully interesting that congruence closure is a theory of some general use, and it happens to be the case that it is easily integrate, like honestly is really easy to implement, easily integratable with Datalog in this way. It's very efficient to do this kind of integration, much more efficient than if you actually like sort of reified the equivalence relation as like a binary relation. And so one of the things I'd like to chat with you all is like, what other sort of theories or applications, extensions can you cram into Datalog in this way, right? Run a step of Datalog, do a little bit of stuff, and then keep going. It so happens, and we did a nice little proof, that it works in this case. We don't have a good understanding of the exact properties of this kind of thing that would allow us to easily say other kinds of things would fit into this mold. So I think that'd be a good topic to chat about with you all. So I think I'll leave it there. Thanks for your attention.
So the next talk is going to be by Thomas Gilray and myself. And this is about some work that we've been doing for the past few years, funded by NSF PFAS Planning and Large, on some of our work to build sort of the world's most scalable Datalog solvers, we hope. Well, let us know if there's other ones that we should compare against. So we'll talk about a bunch of them throughout the course of our talk. So I'll hand it off to Tom. He's going to start.
Hi, everybody. So you know Kris, and I'm Thomas Gilray, and I'm at Washington State University now. And Kris and I and some other collaborators have been working for a while to try to find the right price point for expressive data logs that we can also scale up using high-performance computing techniques and really try to extract as much data parallelism out of problems as we can. And so that's been a large part of our vision. This is sort of our lab. So we have kind of a distributed virtual lab that contains each of our individual labs, and our students do lots of collaborations. These are our current PhD students, and our other collaborator, Sarath Kumar, who focuses on high-performance computing mostly, can't be here, but we want to recognize him and our students who have done lots of work on this. We also have a website, apparently, thanks to Kris. And
thanks, ChatGPT. No, it's mostly Jekyll.
And so, so our vision is basically to try to create a more expressive data log, but that hits a good price point for being able to extract lots of performance and data parallelism out of expressive, tricky reasoning problems. And so these include things like more precise context-sensitive program analysis, reasoning over internet-scale graphs, reasoning over large medical knowledge graphs, and other kinds of problems like this. My own background is mostly in developing tunable program analyses using abstract interpretation. So I'll kind of motivate some of the work that we're trying to do using this as kind of a main example. So the idea here is that you can take an operational semantics in a traditional sense, and you can enrich it and have an abstract machine. So you can have other components that are represented using normal mathematical entities, tuples and maps and so forth, however is convenient. And you can kind of build up an interpreter. And so this would be kind of an example of a small step interpreter where we have a transition function f. And so it takes a representation of the program at some point in time, at some point in the execution, and then just takes a single step and says, what does one step of execution look like? So we can inject our program into an initial state and then just iterate this to get an execution trace, right? And the first step for program analysis in abstract interpretation is to basically put this on a lattice, right? So the idea is that we can view the execution trace as sort of a structured set of states that exists on the power set lattice, right? And sort of says, this is the fragment of possible behaviors that we can actually observe occurring, right? So each of these states might include something like a program counter or a current expression, binding environment, maybe a model of the heap and of the stack. And the vision of abstract interpretation, sort of following the Cousseau's calculational approach, is to basically start with the mechanics for a concrete interpreter, and then to be able to combine this with some specification for the kind of abstractions or approximations that you want to use to reason about your program, and that you should basically be able to plug these together and then just automatically, or at least systematically, come up with an abstract interpreter that represents your program analysis, right? So now this is going to basically give you a bounded, finite ability to reason about your program in terms of less precise information about your program. And this abstraction is sort of the critical component here. And so this could be some notion of abstraction and concretization. And if you want to visualize this, as I said, a collecting semantics for your concrete interpreter would basically put behaviors of your program on a lattice. And so if we have some point on a lattice, what we basically want to do is to be able to structurally abstract this and come up with a finite and coarser version of the lattice that represents our original sort of infinite, unbounded, very granular view of the world in simpler terms, but where we have a consistent notion of abstraction and concretization. And so the idea here basically is just that if you abstract some point on this lattice, which represents something that's no more precise than anything in this region, then that gives you something that's no more precise than anything in this region, and there's a notion of consistency for that abstraction. And so if we then apply that abstraction on our abstract machine, right, we can come up with an abstract interpretation of our operational semantics. And so basically that means if we inject our program into some initial state, we can then abstract that initial state to come up with an abstract state that corresponds with it and sort of represents it less precisely. And then if we iterate an abstract transfer function on this, which is now non-deterministic because we've lost precision, but it'll give us a closed finite transition graph that represents sort of an abstract over-approximate model of what the program might do, right? And the key property here that tells us that, that this is actually modeling the behavior of the original program in a sound way is that if we were to line up our original execution trace for some specific concrete inputs, then that would have to be represented by some path through this abstract model of our program. So zooming in, this basically is the fundamental soundness condition that we want to be able to prove. And the idea is that this framework gives us an automatic way to basically set up abstractions and a concrete interpreter, and then to get a soundness proof out of this rather automatically, right? And so basically we just have to prove that for each concrete step and an abstract state that represents the antecedent state, that we have a step in our abstract interpretation which also models that. And so then if that's true inductively, we end up with a sound over approximation of our program overall. And a lot of my past work has kind of gone into how do you tune these kinds of approaches so that you can sort of strike different balances between precision and complexity in a program analysis like this, right? Which is kind of the game you're playing in trying to come up with a good model of a program's behavior. And often it's the case that you can get both more precision and less complexity if you're using the right abstractions, the right tunings, right? And so what you really want is a way to be able to tune the program analysis that you're coming up with however you want while ensuring that it's still correct by construction. And so that's kind of the whole idea of this framework. And to give you a little bit more of a concrete example, and to try to make this a little bit more sophisticated, let's consider something like being able to verify assertions statically in a program. Or maybe these assertions are produced by a contract system, right? So you might have a language with a contract system, and it basically compiles down into something like assertions when you run those macros. So this is an example of a reallocating array class in C++, and you're inserting into the reallocating array, and so you want to make sure, first of all, that some preconditions are met, maybe that the index you're inserting to isn't out of bounds, and that maybe you have enough space for the content that's already in there. And then you have some post conditions. So for example, if you needed to do some reallocation because you already had filled up the amount of space you had allocated, you want to make sure that you still have a content length that is no greater than the buffer length at the very end. And so then if you expand these assertions, these would basically just be conditionals that are checking to see if this property is true dynamically, right? So they're dynamically monitoring the program's behavior. And then if there's a failure, then they just hit an error at runtime, right? And so one thing we can do to this to sort of enrich our program analysis enough to prove these kinds of properties is to add symbolic execution. And so the idea of symbolic execution is that for each of these values, we'd be tracking a symbol, and then we can observe down different paths through our conditionals what must have been true on those paths, right? And so, for example, if we stepped into this error state, then this would say the index we're inserting into gamma is greater than the length of our content, right? And then if we stepped over it, then it would be not of this, right? And so we can sort of produce a formula and then its negation, and then down those two paths, we're going to add that into something called the path condition, right? Which is a big formula that sort of represents what has to be true down that overall path. So you're sort of accumulating these clauses as you traverse the program. And in normal symbolic execution, you're just exploring outwards to find different possible paths, to sort of focus on where there might be errors. But if you combine this with abstract interpretation, you can produce what we've called abstract symbolic execution. And so the idea here is that you have these over-approximate abstract program paths, and you're accumulating over-approximate path conditions for them. And so then you can take these path conditions and then throw them out to a black box SMT solver and see if they're satisfiable or not. Right? And so if some of the path conditions for these states are unsatisfiable, then basically you know that those are not feasible states. And since they were conservative over-approximations of a whole set, possibly an infinite set of concrete execution traces, then for all of those execution traces, you've proven that they're infeasible, right? So if you have enough precision, you can build out enough abstract paths, and you can make your path conditions precise enough that maybe an SMT solver can tell you that this is not satisfiable. And where that's possible, you have unreachable program states, and some of these unreachable program states might be unreachable contract failures. So where you have an unreachable contract failure, you've just statically verified and proven that that contract can't fail. Right? So this is kind of the approach that we've been really interested in taking for program analysis, because it's very general and allows you to kind of fall back on a runtime semantics, but to sort of give the program verification process a kind of gradient that you can gradually ascend towards full verification. But where you can't fully verify things, you can still just residualize these dynamic checks and then maybe issue a static warning saying, well, I had to residualize this check in your program, and so it's being dynamically checked when ideally you'd like it to be statically checked. So implementing these kinds of program analyses is really, really very tricky, right? We can sort of design it on paper, but then implementing it, especially in a high performance way, is a whole other problem, right? So I've largely done prototypes in higher level functional languages, but even then you end up with something like 1,000, 2,000 lines of code for a moderately sophisticated prototype of a program analysis, which also doesn't scale so well, right? Because it's sort of a higher level language with a lot of dynamic checks built in. And a lot of people that I've talked to or collaborated with who build program analyses in Java or C++ can get great performance from that. But it's often a multi-year long process to turn the ideas that they're working on paper into a real mature program analysis that actually runs and scales decently well. And then you still have all the thorny problems of trying to exploit concurrency and parallelism in a very complex low-level code base then, right? So it's less maintainable and so forth. And so obviously that kind of leads us into, the main topic of the seminar, which is logic programming and how we might exploit declarative program analysis to kind of get the best of both worlds here.
So many people have tried to use logic programming, or recently people have been very interested in using logic programming as a way of addressing this kind of an issue. So instead of writing hundreds of thousands of lines of C++ code, you write maybe a few thousand lines of Datalog code or something like that. And this is great if the logic is sort of a natural fit for the problem that you're trying to explore, right? So, but if it's not, then that's not so great because there might be encoding related space or time blow up. And also, even if you've got like a massively parallel engine, you still have these problems that if the problem is in principle sequential and there's not enough available parallel work to do, well then it doesn't really matter if you're using a supercomputer. So if you think about enumerating like a really, really long line graph, at any one point in time, you're not really doing that much work, right? You're just kind of chasing a pointer. But our goal is to try to figure out how do we kind of use the logic programming, kind of modern logic programming facilities to be able to write these high performance program analyses, and that's what we've been kind of looking at for the past few years. So we've been exploring Datalog to do this. So there are a bunch of different logics, right? If you say, so of course, what is logic programming? Well, it's like Prolog and a bunch of other stuff like that. And I really know mostly Datalog. I'm not really a full logic programming person. But just thinking about logics in general, because of course, if you just have all of logic, and logic is a really big space, right? You can have higher order logics, you have first order logics. Well, in our case, we're really focusing on these kind of simple logics along a certain axis. So Datalog is what I would call kind of the canonical recursive problem. So it's p-space complete. You can do things like transitive closure. It's kind of the canonical graph reachability problem. Great for things like context-sensitive data flow analysis. Things like, of course, SQL CTEs can be expressed in Datalog. And then there's also, for example, SAT, and you can do various approaches. If you use SAT, you can do things like bounded model checking and other sorts of problems like that. And then, of course, there's a much larger space that people have explored too, like answer set programming. Some folks here have worked on that. First order logic. I'm not sure if we have many folks who have worked directly on first order logic here, but I think we're all kind of interested in that as well. And of course, proof search, higher order logic. If you allow yourself to be very expressive, of course, you can say a lot more interesting stuff, but it's a lot harder to actually do the proofs. We're really kind of focused on the right side of this graph, or I guess this diagram. So we're starting with Datalog. We're going to talk a good amount about that and how to make Datalog high performance. We're also going to talk a little bit about how to move into a kind of a more expressive direction where you can do things like functional programming and what we call massively parallel structured deduction. And then there is even more expressive Datalog. For example, Datalog exists. We have a restricted subset of that we call Datalog unique exists. The unifying thing that we're going to argue kind of sits at the central, for our purposes, of course, is horn clauses. So, saturated implication that you're just reasoning and running forward. So I'll just kind of fly through this stuff. I gave this talk previously to a more general audience. I think we all kind of know Datalog, but just to kind of re-explain, here's our simple Datalog program. We've got the first rule that just kind of copies edge into path, no recursion or anything going on there. And the second rule that actually takes and builds out the transitive paths, one longer at each point. And then these are clauses, of course. And we have facts that kind of come to us as the input, and those are in something like maybe a CSV file or something like that, some other durable representation. They define the graph. And then we solve Datalog by repeatedly applying the rules. And of course, the exact way you operationalize this can depend a little bit. This looks a lot like, for example, the chase in databases. And the idea is just that at every point in time, until nothing changes, you keep applying all of the rules as long as you possibly can. You add everything that you get as a result of applying a rule to the database, and then you keep going until you can't go anymore. So of course that looks like this. You discover everything in edge, add some edges, and eventually In vanilla Datalog, all programs terminate, of course, just because there's a bounded state space, right? There is a largest graph in the case of graphs, or when you generalize that across relations, there's like a largest program, because the number of atoms is finite, comes from the program. Right, so in general, this is not, if you extend Datalog with other stuff like natural numbers and functions and stuff like that, well then of course this is not true, but in kind of the academic setting of vanilla Datalog, this is got a good point to make. And just to kind of point out, I don't know how many folks, we've had some folks talk about incrementalization, but the approach that we use in Datalog is called semi-naive evaluation, which just means only add something to a set once, the set of tuples once, and then explore its consequences. And then once you've done that once, well, because it's monotonic, you never have to do that again. So just to give a little quick tutorial, at least as far as we understand it, on how to implement a state-of-the-art Datalog engine. What we're going to do is we're going to compile each of the rules into relational algebra, so an optimized join plan. And then that gives you a bunch of kernels. And each of these kernels is something like a join fused with a project select filter operation. And then after you've got that, you want to be able to do efficient range querying via indexing, because you don't want to have to scan relations and then look things up forming Cartesian products in time. You want to be able to efficiently get a set of results associated with a given index, and that allows you to, for example, if we've got, let's look at these two rules here. Here we're, let's say, scanning R and selecting the y's from Q, or here maybe we're scanning X and selecting the y's from the second attribute here. So there we would need two indices, because we want to be able to look up the set of y's for X, and we want to be able to look up the set of y's for this X here. And in general, if you've got lots of rules, you might even be able to optimize and compress these by reusing or, for example, sharing some prefix. So Soufflé does that by using a very cool strategy they have. It's published in a VLDB paper. And then at the end of the day, you represent your relations in some nice data structure, maybe that's, for example, based on hashes or something like that. So there's lots of engines that implement something like this approach. We have an engine that is just kind of a vanilla Datalog engine that's a competitor to Soufflé, let's say. And it is built on Rust macros. So it's built and embedded in Rust. It's called Ascent. And this was the topic of my first PhD student's thesis. The thing that's really nice about this engine is the fact that it's really embeddable, and like you can put any Rust type inside of a tuple. And so let's say you're trying to write an analysis of LLVM. Well, LLVM is huge and the IR is complicated. Parsing the IR is already kind of hard, and there's a Rust crate for that. There's like a nice LLVM crate for Rust. So it's a real pain to have to go take that LLVM crate and just dump a whole bunch of CSV files, and then go read all those CSV files and write a bunch of kind of rules that manipulate them. And then, so in Ascent, you can really just use the LLVM crate from Rust and all of its types for its AST, and then just put those in relations. And that's like a huge ergonomic advancement, even if it's not a very, maybe let's say, intellectually rigorous advancement. It's a real great insight in terms of how to actually make this work for real as like an analysis engineer. There's also a part of Ascent that I won't talk too much about, but we can talk about it offline, called the bring your own data structures approach, that allows writing what's called relation providers, so that if you want to integrate data structures that are not so efficiently implemented just as like sets of tuples, something like union find set or something like that, well, you can build them in using this Biot's approach. And there are some kind of downsides here depending on getting optimal join properties and like worst case optimal joins, for example, that we can discuss offline because it'll get too into the weeds. But just to show an example of where we used Ascent effectively, we teamed up with analysis engineer at Galois, Langston Barrett. He used Ascent to build a 2,500 line analysis of LLVM, like a context-sensitive analysis of LLVM that we ran on some very large programs. So we've got HTTPD here running. That's one context-sensitive analysis enumerating 5.39 billion control flow points. And on 64 cores, that took 9,700 seconds and, let's say, 425 megabytes of RAM.
Sorry, Chris,
yeah.
I just want to feel stupid or whatever. You say for LLVM, you mean for like LLIR?
Yeah, LLVM-IR, right. So basically you take, so in the case of SQLite, SQLite actually has a really nice feature, which is that you can compile it to a single C file, And you can spit it out as LLVMIR, and we analyze that. So this is coming from the world where, and you know, for Galois customers, they're all interested in LLVMIR a bunch. And so it's a bunch of folks who have tons of LLVM bit code, they're interested in analyzing it. That's the setting. So yeah. Just to kind of point some things out, there's optimized indices. So Soufflé uses the optimal index sharing approach, and it turns out that using diodes you can actually implement that in a scint, where at compile time the machinery for implementing the bring your own relation stuff can actually calculate the optimal indices and then write to them. So this is showing that using that approach on this machine, it goes out of memory, you know, just barely. It's you can see it's like almost there, because here we're getting 2x generally kind of blow up. And so sometimes that's a real help, although it does make it slower because there's more contention around locking and things like that. So next I'd like to talk about our language Slog, which is a new language that we have a new engine for. It runs on MPI. It's a distributed engine. It can scale up really nicely to supercomputers. So it's built on a sort of a restriction of this language called Datalog exists, which allows us to extend Datalog with the power to put an existential in the head of the rule. And so, for example, here we can say, if there's a student that's enrolled in some class, then there has to exist some teacher that teaches that class. So it's a popular extension for reasoning over things like ontologies and other sort of semantic web querying and things like that. But it's, in general, kind of undecidable. It's easy to cook up places where these just don't terminate. Like you can trivially build examples where you can, you know, build an infinite list or something like that. Or here, for example, this is one where you say if there's an edge between x and y, well then there exists a z such that there's an edge from y to z. And you can just keep doing that again and again and again. And culling this kind of very, let's say, unrestricted behavior has been the point of a lot of research projects throughout the years, trying to come up with variants like, you know, shy and warded Datalog, exis, and things like that. The basic issue in all of these variants is the fact that you really only, well, at least as far as, you know, we would make the case, you really only want to instantiate an exists once for every bundle of sort of for all values associated with it. And in practice, if you produce multiple different exists, you're in trouble because they kind of can't be compared and they need to be unified, things like that. And because they're Skolem terms, you can't really introspect on them, you can't really give them much structure. And it leads to a number of paradoxes that make Datalog exists kind of hard to grapple with. And our case is that these are sort of genuine language design issues rather than just kind of unfortunate things that need to be dealt with semantically. And so we have a new language called Slog, and rules in Slog look like this. First of all, Slog reasons about S expressions. So if you're somebody who knows scheme, S expressions are from scheme. So here we're saying, if there is an S expression that matches this pattern, like a lam with a var x and some e, then you materialize binder of x. So that's how you read this rule. It says, if the fact lam var x e exist, then build the fact binder of x. So whenever there's a fact lam var x e, build that fact. And this gives us basically S expression Datalog, or Slog, or S-log, as Yehow says, right? So nobody really knows how it's pronounced. Now our formalization of it, we call it unique exists. So this is exist bang, ID head. So every fact has this form, where basically you get an exist bang, but that exist bang then is forced to be unified with the head of the rule. So you don't write this exist bang, this rule right here translates down into this, kind of under the hood. So in Datalog exists bang, or in Datalog unique exists, every fact is uniquely identified by an S expression. And in a significant departure from Datalog exists, the fact structure is then observable via patterns, because you can give it a nice bottom-up semantics. So to evaluate it, so here's a program up here. So let's say, for example, if there's an ID g that's equal to g of x, and if x is equal to just an atom, A. right? So if you have an atom, that's just, there's just, well, you can just do that. It's like an S expression. It's written a little bit differently here because we were writing it for a paper where we were kind of explaining it to a community that wasn't so S expression focused, let's say. So that's the first rule. And then we say also if we've got an IDT, where we've got T of IDG, and then you can decompose these into a little S expression. So then IDG equals G of IDG prime, and IDG prime is equal to G of X. Well, if we start with this initial database, so delta 0, first of all, the database is something I'm calling referentially closed. So this is just that it's monotonic. Every subfact is in the database. This kind of gives you a nice, kind of relates to the model theory of the language in a way that we can talk about offline. But we turn the crank. Here I'm using a version of delta where stuff that was in the database before doesn't show up in the next delta. So this is kind of a variant of like the restricted chase, let's say, rather than the monotonic semantics that keeps adding things again and again. So the first time you discover this new fact, T of G of A, and then the second time you discover T of G of G of A, and then you're done, because it's kind of a flat set of sequence. But in general, it could, do things like create little loops and execute an arbitrary amount of stuff. In fact, it's Turing complete. We can actually trivially implement a lambda calculus interpreter in Datalog exists bang. Labeled nulls are opaque, confusing, kind of lead to what I think of as unintuitive restrictions, where I think unique exists Datalog really gets at kind of the heart of the issue, while imposing an algebraic structure that, at least for me as a scheme programmer, feels very familiar. Only instantiate a new Skolem term with finitely existing observable algebraic data. It's all nice, it's all bottom up, it's all well-founded. And we've found, we don't really have a proof for this, so this is something that maybe could work on. It's just a hypothesis. In our experience, you can translate many of the existing RDF-style workloads into this unique exists Datalog with no issue. Because the decidable subclass of Datalog exists are also not hard to hand translate into our language Slog. So for example, the Lubin benchmark, which is a nice little TGD benchmark used, I think, in Chasebench. We've translated all of that to Slog and run it in our engine.
What's TGD?
Tuple generating dependencies, which is one way of basically saying that being able to observe a tuple can generate or can trigger the execution of a rule, let's say, yeah. And we argue that in practice, these RDF workloads, even though you might think they're over here, and of course in general they are, lots of the stuff that you actually care about, we argue is actually Datalog exists bang, kind of closer to here. Right, and maybe we're wrong. I'd be interested in hearing your input offline. We can talk about this if you disagree. So Datalog exists bang is a small kind of core formalism that we present. It really only consists of binary joins, kind of single, so it's kind of like a core formalism. But then for all of full Slog, we level it up to a full language that you can do things like functional programming, and Tom and I will talk about that more. Our application inspiration was that we wanted to take these sound by construction approaches to abstract interpretation that Tom talked about and implement really scalable and rich context-sensitive analyses that run over enormous code bases at the highest possible scale on a plethora of high-performance backends. GPUs, GPU clusters, supercomputers, server chips, all of that kind of thing. I think this is where I hand it back to you.
So to kind of dig in a little bit more to the kind of abstract interpretation examples that I was talking about before, we really want to be able to take these kind of standard small step interpreters that we would find ergonomic to write, where here we have a current expression and then some environment and then some current stack, so it's sort of like a Crivens machine, and we can show how it steps to a successor state, and we'd like to be able to abstract this, right? And so this is basically the relationship that I was showing you before visually between these concrete and abstract states. And so we want to be able to take this kind of approach and even maybe handle things like big step semantics, right? Or natural deduction style rules for type systems, and be able to just take kind of out of the box textbook style standard semantics and reasoning systems, and then just basically transliterate them into code as much as possible. So the code just very closely mirrors what you would ideally want to write in a paper or on a whiteboard to express it to another human being. And of course, in Datalog, vanilla Datalog, this is impossible because it's closed, and we can't do an arbitrary amount of work. And that shouldn't really be necessary for a finite program analysis, but it's necessary in terms of having the ergonomic expressivity to be able to implement them. And so we have this paper, Datalog with first-class facts, and this is basically on our implementation of Slog, and on Datalog unique exists, which is kind of a logical perspective on that language. And the basic idea of Slog as a language is really that we have first-class facts, that all facts are data, and also that every datum is a fact, right? So what does that mean? Well, it means that if all facts are data, then facts can be referenced, right? They all have an identity that allows you to reference them that you can then embed in another fact, right? So you can sort of nest facts and build up tree-shaped data. And several others have touched on this today, right? Max and Oliver have kind of talked about being able to treat ASTs as tables, right? And so I think it's a very familiar theme. Several of us talked about in our goals this morning, right? Trying to figure out where we're talking about the same thing in slightly different ways, and I think this is a great example of it. We really want to be able to implement tree-shaped algebraic data types basically that would normally be stored in a linked fashion on the heap as tables so that we can make them amenable to joins and then index them and get all the speed improvements that we would naturally get in a data log, right? So one of the main repercussions of saying all facts are data and therefore that they all may be referenced is that structured data is always automatically indexed and can be optimized via joins and indices in the same way that Datalog normally would, including automatically computing sort of minimal sets of overlapping indices if you're using trie-based indices like Kris was mentioning Soufflé does and the Descent does. And the other thing that I think is really interesting that comes out of this sort of unified abstraction for facts and data is that then data can trigger rule evaluation, right? If every piece of data is also a fact, then you can say it triggers rule evaluation. And so if it's in the outside of a join plan, right, if you discover a new piece of data, it's also a fact, and it can trigger a join plan to run that would then deduce new information to put in your database. And that really gives rise to a number of powerful idioms that basically allow us to implement functional programming in Datalog, and then hopefully extract data parallelism and performance out of sort of traditional functional programming by implementing it in Datalog. And that's also really what's allowing us to implement things like richer abstract interpretations more naturally by just directly transliterating them. So this is going to basically enable things like call return idioms and defunctionalization for functional programs that are written in Datalog. So the first benefit I'll sort of go over more quickly by just showing you this graph from our this table from our paper. This is basically a comparison of Soufflé and Slog on 8 processes and 64 processes for a KCFA benchmark. For many other program analyses we've run, the difference is much more modest. You know, it might be 3 or 4 times faster or something instead of 5 seconds versus 45 minutes, you know. And a number of these you can see timeout for Soufflé. Really what this is showing is just, it's good to have indices on your data. It's really important to have indices on your data and you get a huge speed up from it, yeah?
So what's going on here, are you using just the Soufflé ADTs?
Yes, exactly. Yeah, so all this is illustrating is really that if you have the exact same program and you're doing an apples to apples comparison, but you have our S expression facts, right, which are data and facts, and you compare them to Soufflé ADTs, but otherwise it's exactly the same. Because the ADTs in Soufflé are not indexed automatically for you, you don't get these speed ups, right? So it's kind of a very simple result. I don't want to oversell that, but I think it's really nice to be able to have that be fully automated, right? You don't really, as a programmer, want to have to specify those sorts of things, and this is a nice benefit of having this unified abstraction. And so then, really, I think the main benefit in terms of improving the expressivity of Datalog and being able to more easily and ergonomically implement more expressive program analyses and reasoning systems in our language is the ability to do things like calls and returns and defunctionalization directly in the language. So for example, if you have a functional program like this where you have two nested lambdas, basically a curried plus function, then Reynolds defunctionalization would basically say you can implement this using first order applies and a closure creation, right? So here for lambda 1, we basically produce a closure lambda 2 of x. And so this is basically the relation name or the struct name, or you can think of it as a tag at the front of the S expression, right? And then this is the content that's in the closure, right? So basically it's like in closure conversion, the way you would have a function pointer and then an environment, right? And then we can pattern match on this, right? And so our system also naturally has ad hoc polymorphism and the ability to do pattern matching on these closures. And so you can just say, well, when I'm applying a lambda 2 with a free variable x, right, on some value y, well, then you can take y and x and add them together. So this is what this would look like in our language. And you can see how this basically implements calls and returns. Because now that you can reference facts, right, you can sort of put a fact in the head, you can have a fact in the body of a rule which is also in the head of a rule, right? Because it's being referenced in the head of the rule and it's being checked in the body of the rule. So here, this first rule is basically saying, if I have a call site where I'm applying a lambda 1 on x, right, and that has this identity, IDC, then I can associate that call site with its return value, which is lambda 2 of x, right? So this is, we're calling lambda 1, we're returning a closure for lambda 2 that's closed over the value for x, whatever that was. And so here, you can see that we're basically putting this fact that there has to be a call site in the body of the rule, but we're also referencing it in the head of the rule. So now that we can reference things, we can associate it with its return value. And then here we have the same basic idea, but when we're calling lambda 2, we can pattern match on there being a closure lambda 2 with the value for our free variable x, and then also a dynamic argument y, and then that's a call site that we can reference. Now that we have x and y, we can add them together and say what sum are they associated with, right? So this is one notation for doing that, where just in our language, idiomatically, the last column would be the return value. And that's also what we're doing here, which is with this, this returns relation, which is just an ordinary relation, right? So plus here is sort of a built-in computational relation. Returns is just a normal ordinary relation, which is associating this call site with the sum that's being returned. And so now that we have these sort of idioms where we're putting a fact both in the body and in the head of a rule, which doesn't make sense unless we have first-class facts, right? Because if we're just checking that something exists, there's no reason to deduce it again by putting it in the head unless we can refer to it. But now that we can, that gives us an excuse to add this syntactic sugar, which is a huh clause following scheme and the scheme pronunciation. And so we have huh clauses, and then I'm also introducing this curly brace syntax. Curly brace syntax is basically just to say what value is associated in the last column with some set of other values, right? So the way we had in parentheses plus xy sum, this is basically saying unify this with the sum value, right? So it's exactly the same thing as pulling this out as a clause and adding a variable sum and then putting the variable sum there, right? So we can say basically do a lookup.
And then huh clauses.
And then huh clauses basically desugar into exactly what I showed you before. So a huh clause is something that you can put in the head of a rule where you would want the pointer or the reference or the ID to that clause, but that also has to be in the body of the rule, right? Meaning the rule is contingent on this clause existing or this fact existing. So this is basically saying, if you have a call fact like this, then generate a returns fact that references that call fact and associates it with the final sum. So this is just syntactic sugar for what I showed you on the previous slide. And then curly braces is also syntactic sugar. So to show you a sort of more interesting involved example using this syntactic sugar, this is free variable analysis in our language. Right? So where you don't have any other body clauses outside of the clause, you don't have to use square braces or use an arrow, but this is still a rule, right? So this basically says if you have a reference to x, well then x is free with respect to that reference. The next rule says if I have an application in my program of E0 on E1, and if either x is free, if x is free in either of those two sub-expressions, then x is free with respect to the application. So OR is also just syntactic sugar that breaks this into two rules at the top level. And then the last rule basically says if I have a lambda abstraction where I have a variable x that's free in the body of the lambda, and if x is not equal to the formal parameter, then x is free. So these kinds of syntactic sugar and these idioms for doing calls and returns anticipates our ability to do defunctionalization in a more general way for arbitrary functional programs that we might want to write and then basically compile down into our language. It enables an elegant transliteration from natural deduction style rules. And we also get ubiquitous data parallelism for all of these facts. So ASTs are basically being flattened into flat tables that we can then parallelize across. So whatever we're doing at in the back end of our Datalog solvers to extract data parallelism and scale these things up on multiple nodes or on GPUs, we can apply that across nested structure as well now. So this just kind of explains that. I'll show you a few more examples just to kind of flesh this out. Yeah?
So how do you actually generate those IDs across in a distributed setting so that you don't end up with duplicated terms? And how do you manage that in like big?
That's a great question, yeah. I have a slide in just a couple of slides where I'll talk about exactly that. But yeah, that's sort of a critical point in how we actually implement this in our various high-performance computing backends. But basically, it turns out to be really simple. So you can basically just you could do interning in parallel and assign the IDs in parallel. But it does take a little bit of care to do that. So here's kind of just an example of being able to transliterate these kind of simple textbook big step rules. And this also introduces a new piece of syntactic sugar that I won't flesh out quite as much, but is also really very simple, which is these bang clauses. And so bangs are kind of the natural inverse of a clause, right? A clause is a clause that's nominally in the head of a rule, but that also is required in the body of a rule. So you can kind of copy it over into the body. A bang clause is basically a clause that's in the body of a rule, but is sort of an intermediate head. Right? And so whenever you have all the variables in the bang clause ground, and when all of the other clauses in the body that deal with those variables are also have been checked, then you can, on the fly, as you're evaluating this rule, emit those facts as though they were sort of intermediate heads, right? And that basically allows you to emit a fact that represents a call to a function, basically, right? So this is like, in order to interpret plus of E0 and E1, first I have to interpret E0, and I have to interpret E1. And this also becomes a natural place where we can extract data parallelism, right? Because both of these head rules or intermediate heads are straightforward to detect that we can do them in parallel. So we can emit them both and then let rules that handle doInterp handle those in parallel. And then when we have both of those values, we can then pattern match on interp of this call site and the value that came back for each of them, right? And then we can just add them together. And so again, the is also in the body. So we have to have this before we can do these nested calls. And then also this plus is syntactic sugar for applying that plus once we have those variables ground. And then I'll show you one more example that just kind of further illustrates that we can take straightforward functional programs and just directly implement them in our language in a nice way. So not necessarily this is the way you would want to do it, but we currently support linked lists in our first version of Slog, which are just desugared into linked facts, right? Because now we basically can represent facts that are that can be referenced, and so we can build up linked lists in a very natural way. And we have this syntactic sugar with square braces, and this is how you can implement append in a very direct way, right? So if I'm appending something to the empty list, it's just that something. If I'm appending a list with at least one element to another list, then I can append the tail of the list, and then when I get a value back from that, I can look up that value, right? So here we're using a bang nested underneath the curly brace, but again, this is all just syntactic sugar that our compiler takes care of, and then that puts that in, spliced in as the tail of the list that comes back as the result for the overall append. And I won't dwell on this, but just especially because we're using a different notation. Kris kind of mentioned this in our paper. We used a somewhat different notation for that paper, but just another example of simply typed lambda calculus rules being transliterated into our language fairly directly. And so then this gets to your point, Arlen, basically, how do we implement this in a high performance way? Well, we have a couple different backends that we're working on, and we're working on a new version of Slog that kind of tries to pull together all of the different ideas we've been working on into one system that's as usable as possible, and that is more future-proof in terms of being able to integrate with some of the GPU backends that Kris is going to start talking about in a minute. But the current version, the first version of Slog, which is open source and on GitHub that you can kind of play around with, is fully MPI based. And so it uses kind of an MPI everywhere approach where the only parallelism in it is coming from MPI. And what we basically do is we have a distributed hash table for our indices, and we're just doing a straightforward domain partitioning to parallelize the workload. And what that means, sort of unfortunately, is that we have we have this intra-bucket com, which comes from the fact that basically we have two layers in our hash table, so we can deal with key skew, right? You might have fundamental key skew in the topology of your graph or of your relation. And so we have some intra-bucket com between different sub-buckets which manage the key skew. Then we do local join, project, selection, reordering, etc., all of our relational algebra locally in a fully parallel way. And then unfortunately, because we're distributing it in this very simple way, we have an all-to-all communication phase, right? Which is sort of part of what makes this MPI-only approach not scale at some point. But in our experiments, it'll scale up pretty well to thousands of processes. So until you're getting to like 4,000, 8,000 processes, the all-to-all com portion of this isn't going to stop scaling too well. And also gave us an opportunity to do some cool HPC work in terms of how do you optimize non-uniform all-to-alls where there's very little data, but it's not uniform. And so that was kind of neat. And then basically in a parallel way, you can just break up you can have basically a partitioned set of bump pointer allocators that are allocating into distinct portions of your U64 space, basically. And so it just turns out that doing parallel interning, which is really what supports generating these IDs, which can then cheaply refer to tuples using just a one-word value, that turns out just to be really simple. You know, it sort of dovetails with this approach. And we're using, another thing I would point out about this is just that it tries to minimize the points where you have synchronization. A lot of other approaches to doing parallel data log are using, shared memory locking data structures. So that's what Souffle does. That's what Ascent does. And that can scale decently, but usually only to maybe 4 or 8 threads. I think Souffle used to scale a bit better in my observations, and I think they optimize the data structures more for memory use than for parallelism. And so lately when I run experiments with Souffle, I notice the scaling kind of falters at something like 4 to 8 threads. But in our approach, we really want to scale up to very large number of threads, GPUs, multiple GPUs on different nodes. And so we don't want to run into those problems. So what we have in our approach is really just 2 or 3 different cheap synchronization points where all the threads have to synchronize, and otherwise there's no synchronization whatsoever. And so that's mostly the approach that we're taking kind of going forward with our new backend as well.
So as Tom mentioned, we formalized some of this in Datalog unique exists, which we have a VLDB paper about. Since we're kind of short on time, I'm going to skip past some of this and just start to dive into some results. So we compared, you can use Slog to encode some traditional provenance style reasoning. So this is Y provenance versus a solver called Nemo, which is a new solver in Rust. I watched a talk on it recently at Datalog 2.0 in Dallas this year. There's another slightly older system, I think by this same group, called Vlog or Vlog. I'm not sure which one it is. And then RDFox is an industrial sort of RDF engine. And then we've got Slog here. And we can see that we're kind of on course with RDFox. RDFox is a very good engine. It beats us some of the time at 12 threads. And these other engines don't seem to do quite as well as RDFox, but we are either faster than RDFox at, let's say, 12 threads for these Y provenance examples, or we're at least kind of at parity with them. And then this is an example showing scaling a context-sensitive program analysis of Linux. This was data that we got from an ASPLOS 2017 paper. And this is scaling up. The scaling efficiency is not amazing, but we can see it kind of bottoms out at 1024 threads here. So just kind of showing the potential. This is not, to us, good enough yet, but it's kind of a sort of kicking off point, as Tom said. And as Tom mentioned, the traditional way of doing it on a CPU just does not seem to scale too well after a certain point. So for example, if you look at Souffle and you benchmark it and see where is it getting bogged down, it turns out that at 16 cores here, 77.8% of the runtime on Souffle is just spent in basically serialized insertion into the data structure. All right, so this kind of an approach just isn't going to work for what we really want to do of using a GPU to do Datalog, where we have a massive amount of parallelism, extreme memory bandwidth, and this nice kind of SIMT architecture. So there's no overhead from inter-warp divergence, but unfortunately, there have been some efforts to create GPU Datalog systems, but none of them truly beat Souffle on a single CPU. So I'm just going to foreshadow some of this work, since our student Sowmith is going to talk a little bit more about GPU Datalog in his talk. But I'll just say we have a nice data structure that we've got called HISA that my student Yihao kind of came up with after thinking about this for a while. And it's a multi-layered data structure that addresses the issues with previous work in GPU Datalog, where you get kind of an outer layer of a hash table that then gives you a sorted index array that's backed by an underlying just traditional flat data array. And HISA facilitates implementing these fast relational algebra kernels. Our initial ASPLOS 25 paper was called GDlog. It's an engine that uses this HISA data structure. Most of the relational algebra kernels are relatively straightforward once you get HISA, but we kind of decompose them into two phases. So we do sort of a cardinality estimation phase, where we kind of go through and run the query and see what's on a sort of allocation bound. And then we do another phase where we do materialization, just because you don't want to be doing allocation on the fly. It will really kill you on the GPU. So just to kind of show some quick evaluation, since kind of running shorter on time here. So here's an example of same generation of GDlog, which is an ASPLOS 25 system, versus Souffle at 32 threads, and QDF, which was a system by NVIDIA that people are using to do sort of RDF style workloads, like relational data frame workloads on the GPU. So this is on an H100 with GDlog. We get 5 seconds versus 74.26 seconds on Souffle at 32 threads. We were using a 64 core machine, and 32 threads was the optimal performance that we found on that particular benchmark. And so I think, similar trends we see here. QDF is often runs out of memory for reasons we can talk about offline. We also have a AMD version. So HIP is sort of the AMD competitor to NVIDIA's CUDA. And so we have a HIP version as well. The allocators for HIP are not tuned quite as well as NVIDIA's allocators. And so the performance is not quite as good. This is just a big transitive closure operation. where we're running over some very large graphs. So we've got like 14 seconds versus 232 seconds, and then the other approaches run out of memory for various reasons we can talk about. We've got a context-sensitive points-to analysis. I'll just show you a picture of it here. It's relatively simple. It's not as big as the one that we showed earlier. The exciting thing is that versus Soufflé, on Postgres, we are getting, let's say, 1.27 seconds versus 57.82 seconds. Okay, so pretty good, good-looking results for at least that relatively simple analysis. We kind of followed that up with a column-oriented version of this engine. So that's a AAAI 25 paper that Yihao wrote very quickly after writing the first paper. And so we have an example here that is a subset of the Lubbock benchmark that's a tuple generating dependency benchmark. This kind of goes back to some stuff we can talk about offline, but it relates to things like provenance and such. So we can see on a GPU, it's 0.15 seconds. In Nemo, which is a Rust-based competitor system, 0.65 seconds. In our DFOX, 0.44. This is on a CPU. So this is not using the GPU. This is just using the column-oriented approach, and it's basically taking what would be running on the GPU and then just running it on the CPU instead. When we switch to the H100, we get 0.01 seconds. So we get a much faster implementation. But we showed this just because you might say, well, your results are only looking good because the GPU has a great memory bandwidth, right? So if you're cynical on that, you can kind of look at these CPU-based results. And then most recently, I'll say, we have some sort of late-breaking work at ICS 25 where we're doing multi-node, multi-GPU data log. So here's an example where we're using 1 GPU per node. This is transitive closure, and we're scaling on some large graphs. This is the largest one here. So at 1 node, we're at 682 seconds. And I think that's on the CPU only. 1 GPU is 66 seconds. We go all the way down to 2 seconds at 32 nodes and 32 GPUs. There's 1 GPU per node. The CPU version would be 28.48 seconds. So just kind of looking back at our systems, we've done a lot of sort of innovation on the just vanilla data log space. So we've got a few engines there. GDlog is our GPU engine. VFlog is an iteration of that for column-oriented stuff. Multi-node, multi-GPU data log. It's an ICS 25 paper. We've got Ascent that kind of does the sort of Rust data log stuff. Slog is VLDB 25. And all of this work so far is funded by an NSF POS large. So we've got a big diagram of what we're hoping to work on over the next few years here. Kind of calls out the various angles we're looking at. So I'm working on some declarative disassembly and decompilation stuff. Working with Tom on like abstract symbolic execution and finite flow analysis. We are also very interested in doing things like equality saturation and kind of looking at how our engines can sort of harmonize with that. So we'll be interested to talk to some folks here. We're interested in doing some traditional graph sort of operations like feature extraction, community detection, and we're working with Swarat at Texas on some neurosymbolic AI stuff as well, kind of in this space. And then Matt Might at UAB doing some precision medicine like PubMed querying, drug repurposing, that kind of a thing.
Part of what this illustrates is sort of our vision of being able to take a wide variety of different applications and then use Slog as sort of a unifying, integrating platform to support those with a bunch of different high-performance computing techniques.
Exactly. Exactly. So thank you so much for everyone for coming out to this workshop, first of all, but also for listening to our talk as well. So we really appreciate it, and we're basically out of time, but maybe we can take a question or two and then start the next talk. Yeah, thanks. So the next talk is going to be by Arlen, and he's at IDA CCS, as he said earlier. So he's going to talk about structural code analysis with Datalog. Take it away, Arlen.
So I'll preface this with saying you've heard versions of this talk several times today already, I think, because I'm going to talk about representing abstract syntax trees using facts and Datalog. And probably the most important thing on this is I think I have the coolest email address ever. It's pretty great. The history of this is we used to be known as the Supercomputing Research Center. We were the I think the 4th .org ever, and so anyway, that's where that comes from. this is also sort of a pragmatic take on this. So my goal here is to kind of bring this to, well, a certain subset of the masses. And so a lot of what I'm doing here is I'm taking ideas that you've just heard a lot about, and I've tried putting them in the hands of people who don't do this like as a researcher, who aren't doing this stuff professionally, developing program analyses as professionally, and watching what happens and responding to that. And so this talk is sort of a follow-on from that. So. Few parts, and I'll try to keep this short so that we can all get to like fun times here on time, or maybe a little ahead of schedule too. So, all right. So I'm going to talk about structural code search. So I haven't seen it presented this way yet here, but if we're talking about code auditing, and that's the context in which this work exists, people who are auditing code do a lot of searches through code. You're looking through snippets that are looking for like buggy snippets, looking for broken bits of code, whatnot. And if grep, which is sort of the going tool for doing this, makes this kind of hard in some circumstances. You know, grep operates fundamentally on character sequences. And so if what you're doing through is looking for something like this, this potential buffer overflow here, because you have a fixed length buffer that you're doing a scanf into, you can get yourself in trouble because there's, I mean, you're not guaranteed, for instance, that this buffer is declared in the same place that it's used. There could be a different buffer. There could be a whole bunch of code in between there that could like end the function boundary, and you have, you're doing something else entirely. Now, one could argue that scanf %f into anything is probably a bad idea, but it's a short example. Additionally, grep doesn't distinguish comments from code. So one of the problems that I've run into a bunch of times is you'll find buggy code, but it's been commented out and replaced with something else. And just sifting through that is kind of a pain in the butt. And really all this is because grep has no concept of the structure of the code. It doesn't know anything about it. So what is the solution to this? The solution is to convert everything to an AST, right? So parse it, and so we can parse this code into this form. We've got a block node and a declaration, and this is a character array, a buffer of length 50, and some other code represented by ... and a call to scanf with the arguments being passed %f and buffer, right? And once we do that, then we can run searches over this AST instead of running searches over the character string. And you get all the structure that you, well, not all the structure you might want, but it's a bunch of the structure that you might want. But there's a really big problem with this. If you go and give this to somebody who is looking to do code auditing, they look at this and they go, "You're crazy," because these are messy. So good, like if we wanted to codify this pattern, what we've done here is we've generalized this and said, well, we converted whatever the name of that buffer was into name. We've converted whatever the variable being passed into scanf is to the same binder here. And then we have to codify this entire tree to say this. So what does this actually mean? Well, we have to talk about what it means to have kind of intermediate values sprinkled all throughout here. So we have to represent this large structure to do what is this otherwise relatively simple thing. And people don't like doing this. Turns out I don't like doing this. Even if I know what I'm doing, I don't like doing it. It's pretty awful. So one of the big things in this is to just reuse the parser. So if you take the parser that you're using to generate the AST and you use it to parse the query string, you can now use the query language as the same language as your parsing language, and you get a sort of a natural correspondence between the syntax tree that you're searching for and the syntax tree that you are searching through, right? And this makes it really easy to generate a structural search from a string input. It's very easy to write. You don't have to remember, don't have to think about any of the internal node names. You don't have to think about how these trees are labeled. And basically what you get is a kind of direct pattern match infrastructure built on top of these syntax trees. So for example, what we can do is we can write this query in this way. So here what we're doing is we're saying, this is a way of saying this is in the C language, and that we're going to look for a block. And we're going to look for a character with this specialized name, a character buffer with this specialized name buffer, where we don't care about what the length of the buffer is. Any kind of predetermined value is bad. And then we're going to do a scanf where we are going to skip over the first argument and look for any subsequent argument that has the same buffer here. And we can then parse this into this tree pattern that then we can use to do the search. So, great. But more structure is often required. So in general, we want to know things like control flow graphs, we want call graphs, we want points to graphs, we want dominators, we want all this other kind of program analysis infrastructure. And the problem is that just simple search like this doesn't give you any of that infrastructure. And so this brings us to how we get from like simple code search infrastructure to analysis. So I claim, and I think this is kind of probably the only really unique thing that I'm going to talk about here, that you can build an awful lot of program analysis out of composition of searches. And so what do I mean by this? Well, a good example of this is the core of a call graph construction is this little search right here. So this is a little bit hard to read, but this is basically a function definition, right? Where we don't care what the return type is. We extract the function name. We don't care what the arguments are, so we kind of leave them elided, and that does the right thing. Oh, that was interesting. And then this says somewhere within the body of this function we have a call site to some target function, and we don't care what its parameters are, right? So this search is finding the definitions, extracting the name of the function, finding the call sites, extracting the name of the callee, and then connecting all of these call sites and function definitions through an implicit closure operator. So this underscore here is saying that any kind of like any occurrence of a call site within the subtree is an occurrence of the call site within this function. So this basically gives us a call graph, a direct call graph, but a call graph nonetheless. And we can use this, and then we can, well, yeah, anyway. So we can do similar things for control flow graph, but it does not fit quite so cleanly onto a single slide. And we can, so the point is we can use code search, right? This is a really simple code search snippet to seed analysis tasks. So we can use this to generate a call graph, and we can use that to do like call graph reachability kind of queries on top of that. So the big thing, and the reason why Datalog and why I'm here, is Datalog is a wonderful language to do this kind of composition. So we can, you've seen this stupid reachability example, I don't know how many times today. Every talk is going to have this, I think. So a requisite. But you can extend this to other graphs. So we can turn this into call graph reachability by taking this call graph snippet and dropping this directly in as a Datalog predicate and using this to seed the edge graph. And then we can get reachability by basically just doing the transitive closure of that edge graph, right? So really straightforward application of Datalog, but we're basically mixing code search with Datalog in a way that we can build simple lightweight analyses out of this. Yeah?
Is there ever a time where you want to seed it with the stuff, use the Datalog to generate something, and then use that to keep doing code search? Is that possible?
You mean generate code snippets that...
Yes, that thing you search for. Is that even sensible at all?
I will wait till somebody asks me for that.
Sure. Yeah.
I think I think that's plausible, but I don't know that it's going to come up.
Right. That makes sense. Yeah.
I think that you could certainly, one way that you could architect this system, it is not currently architected this way today, is you essentially write instead of say, doing this as a pre-processing pass where you, which is what I'm about to tell you, turn this into Datalog, you could actually integrate this in as a direct query operator, and then you could kind of fuss with that and evaluate that on demand. But like I said, I'm not sold on that being a necessity.
Right.
So in general, what we're doing is we're embedding code search directly into Datalog. So the Datalog predicate language is extended with these code search predicates. These let you bind things like names, node IDs. Every node has an ID, shockingly enough. It gives a bind child index. So if you want to get things like this is the ith parameter of a function, you can extract that kind of information or restrict it to search on that kind of thing. There's a few other things too, as well. And then you can use Datalog as the analysis language. So basically compose the complex searches and construct all the graphs that you want. Datalog is pretty good for that. Do things like build function summaries, really up to the limit of whatever your Datalog engine is capable of doing, right? So this expressivity of Datalog is important here. So what does this actually look like? It's not pretty, and this is why I say writing these things by hand is truly heinous. So this little gem right here that I showed you turns into this grotesque monster. So what is actually going on here? This is a direct translation of that. I'm using a little bit of an extended Datalog here because I'm reasoning about ASTs, and I'm reasoning about sort of a generic AST structure where I'm not baking the, there's a single schema for every AST here. Which is important because I support more than just C, and I support every language that you could conceivably want, at least in the limit. And so what happens here is we take this AST and we label it, basically this is just giving you the names for these things. So we've got the ID for the definition site, and this basically says let's match the name using a literal, which is missing here, which is the typo that I meant to fix but couldn't find again this morning when I was trying to fix it. And it's basically we extract the identifier from the function definition, and then we use a transitive closure thing here, starting from basically the call sites, searching upward to find the definition sites. So that is what all of this codifies.
You have a question?
Yeah.
Observation, this might be an answer to Chris's question, that the code snippet search is a good way to specify essentially recursive properties in BAST.
Yes.
Yeah.
Was that your question?
A situation where you might want to feed the output of one Datalog structure back into the search.
Yeah, but you don't have to regenerate queries as you. So the nice thing is you can use these as kind of structure, and then you can these are just Datalog predicates, right? So you can put as many of these into one Datalog rule as you'd like, and so if you can use one snippet to restrict what another snippet looks for, or and how these things kind of interact, and is kind of complicated. But the degree to which you want to do that depends on how good your query optimizer is in kind of eliminating messy intermediates in there. Yeah.
I thought I answered Chris's question, and now I'm less certain, so I want to check. I think an example of the sort of place where you'd want a dynamic pattern is something like you detect an enum, and then you want to check cases of switch to make sure that every case is accounted for. Is that the kind of thing you were thinking of, Chris, where it's like the pattern you're going to generate is going to depend on the data? And it seems like here, this static desuggaring wouldn't quite cover that.
So, kind of do I have that one supported? I've certainly written things that look like that. I don't think I've actually checked exhaustivity with it before, though, and I think that is indeed a case where you at least want a different sort of quantifier, right?
Never mind the aggregation. I just meant really, well, the size of switch, the number of cases you're looking for is this one where the number is different. Well, what number? Well, it's different. It depends on the definition of the...
Right, but what you can do for that is you can say extract each enum value from the definition of the
I know
enum.
you're looking for switches, but
Yeah.
you can change where you're selecting.
And then you look for a switch that doesn't have one of those, or it has one of them but doesn't have any second one.
Similar thing, I guess, for if then else chaining, right?
Yeah.
You could just, well, give me the maximal chain and then I'll see if it's the right thing.
Yep,
Yeah.
yep.
Yeah.
So you could solve it via generation, but I'm not sure that's an example of a place that is necessary yet.
No, not necessary.
Yeah.
It can be.
Maybe.
But that is what we were talking about.
I think that's a filled-in version of what I was talking
Yeah.
about. That sounds a lot more coherent.
That wasn't sure exactly what we meant. Cool, man. Cool.
So one of the places that I think this is really fun is you can use this to do cross-language analysis, and this is something that I genuinely does not exist out there in the wild that much. So a really neat place for this, for instance, you can basically construct a call graph for C, and since we also support Lua, you can construct a call graph for Lua. And then you can write a couple of rules to, and I'm not going to do this here because it's a little bit messy, but you can write a couple of rules to describe what the FFI looks like between Lua and C, and now you have a way of linking the call graph from C to the call graph for Lua, and you can do call graph construction across language boundaries, right? So you can take a code base that has a Lua extension language, you can take a bunch of Lua extensions and analyze them together as a complete system to find things that are interesting, right?
This seems like a great system for rewriting MOS.
Maybe. I'm not going to do that for you. Yeah, there's a joke to be made here. I have an abstract interpretation background, and everything I've told you flies in the face of abstract interpretation because this is just like developing lint tools. This is terrible analysis. But it turns out that most users actually kind of want terrible analysis. What they want is something. The reality is, I think Max and I were talking about this at lunch a little bit. That there is there's an interesting thing. Like if you present a user an artifact that's kind of beyond comprehension, that's essentially useless. Like if it doesn't answer precisely their question in totality, it's essentially useless. And so there's a lot of value in kind of scaling back what you're doing and to the point where what you're doing is comprehensible. And one of the things I really like about this infrastructure is everything is tied back to the abstract syntax tree. So everything is traceable back to something that the user is looking at and can witness and can interact with, right? Is like there's not really anything that's kind of I mean there are IDs that are synthesized, but those are IDs are attachable back to locations in the original code, right? So there's actual like grounded information, and then everything from there is derived by a set of rules that are either completely correct because they are not abstracting over anything, or they are written by the user. And because of that, there is a complete deductive chain from anything that the user interacts with to anything that they're looking at in the result. And I claim that this is a much stronger property than like soundness of analysis because this is something that's much more akin to what users actually want. Now, it's not formal. Like, I mean, it's formal, but it's not formal in terms of like the target language semantics. But it's, I think this is a very constructive way of thinking about program analysis in an end user centric sort of way. So. All right, so the obvious thing to do here is, well, you take all this stuff, you chuck it into Souffle, and you call it a day. Souffle is the kind of go-to Datalog for program analysis. It's pretty fast, so on and so forth. So what happens when you actually do this? So just a little example. You take a search for Linux kernel allocation functions. You pre-process the Linux kernel into a big pile of syntax trees, and what you end up doing is you spend 2 minutes compiling the generated C++ code, 11 minutes doing I/O, reading the Linux kernel into Souffle's in-memory structures, 3 seconds of computation, and you get your results. Mission accomplished. Yeah, okay, this is not what Soufflé was designed for. Yeah.
Can you, what is the 2 minutes compiling generated C++? What is that?
Oh, so Soufflé has an interpreter mode and a compiler mode.
Soufflé code.
Yep. So Soufflé turns the Datalog into C++, and it generates, it's got to be some of the world's worst C++ code.
Competition stiff.
Yeah.
11 minutes ago, you're counting the write the CSV and the load the CSV?
No, just the load the CSV.
Oh, so you're not even counting fact generation time?
Correct.
What is fact generation time?
That has evolved so many times.
If you don't know off the top of your head, it's cool. Sorry.
It's somewhere in the same ballpark.
Okay. Yeah, my guess was this would be evenly split between write it all disk, load it all back. And to me, it highlights a core theme, which is if you can avoid having to build a separate data structure for your Datalog facts, you are going to be much happier.
Yep. Though in this case, it's kind of a nasty situation because this is a bad benchmark. Okay, this is an objectively bad benchmark. I'm not claiming anything otherwise. When you start doing cross-translation unit analysis stuff like call graph kinds of things, you pretty much have to have all that stuff in memory at once, like all translation units in memory at once, which is fine if you've got enough memory to do it, which you obviously have if you're doing this with Soufflé, but I'm about to transition away from that.
There's a bunch of prior work on how to have a database deal with insufficient core.
Yep. So I think you could argue you could try to do this on the fly, but or just like store this all in memory and then operate directly on the structures in memory, which is a win over doing this with Soufflé in this way. I am not convinced it's a win over over doing something else. So I'll get there in a second. So there surprisingly aren't that many alternatives. This is maybe a hot take in this crowd. It's probably also a little bit unfair to say that Ascent is roughly the same as Soufflé. It does produce, the Rust code it produces compiles much faster than the C++ code that Soufflé produces. But a surprisingly compelling solution to this problem is to chuck all this into SQLite and use SQLite, convert your Datalog to a bunch of, to essentially a SQLite program, and then use SQLite to solve this problem for you. I sense a question or an objection.
I feel like this didn't answer, the thing that took all the time was fact generation and then loading.
Yes.
And so you're saying that, well, if we ignore the fact generation time, SQLite will make loading faster.
Yes. Because in most queries, we're touching a relatively small percentage of the whole system.
Sure, but then Amdahl's law gives you a maximum 50%.
Yeah, but this is assuming that you're assuming that you're going to re-index for every single query, right? The reality is I'm going to write a whole bunch of queries against one program. So if I can amortize that cost, I'm going to. And the reality, like the reality of this is I'm writing hundreds of queries over a single index time. And if I can get the index construction time under 10 minutes for the Linux kernel, I don't really care. I'm going to do that one time, and then I can write, as long as my queries take, seconds to evaluate, I consider that a win.
It's certainly better.
Yeah.
So when I was an intern at Microsoft, all the kernel developers used this tool called Source Insight that basically indexes the whole kernel and then lets you do this kind of stuff. And it was that kind of workflow. It was like basically every few months you'd re-index the whole kernel, and then you'd write a bunch of queries because you're trying to figure out, you're a kernel developer who's only touched a few thousand lines of this million-line code base, and you're trying to figure out what it does. So I think that sounds a lot like
So this isn't new in the sense that there are lots of things that construct indexes of large code bases, right? What's new here is that it presents that in Datalog and gives you a nice way to kind of seed your Datalog with references into that into those structures.
Yeah.
Have you looked at using these product systems like XSB, that particular one?
Yes, I have looked at XSB. I have not evaluated its performance on this problem.
So in general, so first of all, right, there are actually two submissions. One is the inference, one is exactly this data thing. And so for inference, we have done some analysis just very informally, but we did write down something more simple than the last year. It was like for the transit closure example, SXB, is 10 times faster than Souffle. Okay, and then for the sort of, the load data and stuff.
Yep.
They had built in the last couple of years a Python interface, and they were saying, we didn't use any really scale things, but the main performance is like 1 million facts in some seconds or something, 1 second or something like that.
Mm-hmm.
Because they just basically it's the same, right? The data is mapped from Python to XSB.
Okay. Okay. I mean, I will have to look at that more. I'm not familiar with that
and then
precise.
You can declare all indices, so you can generate index,
Yeah.
tabling, and all that stuff.
Yep. I am familiar with XSB. I have used it for small stuff. I haven't used it for the big stuff. I should say the indexes here are kind of sizable. The Linux kernel one, I think, is like 20 gigabytes, kind of sizable. In SQLite, which does actually a reasonable job of compressing it, it's worse when it's CSV. Yeah. So anyway, SQLite for this particular problem anyway completely destroys Souffle, right? Because I said it's I/O bound. 30 gigabytes. Yeah.
Does anyone think Souffle does a good job?
No.
Because I was smoking Souffle 10 years ago, whatever, 7 years ago when first time. I assume it's gotten better, but I don't actually. Is it?
So so it's really easy to throw darts at Souffle. I think for what Souffle was designed for, it is pretty good at it. Like and so in my experience, like differential data flow at problems that Souffle hasn't gone horribly off the rails on produces code that is roughly the same speed as Souffle, right? The problem is it goes off the rails all the time, right? And I think that's the thing that that needs to be fixed in this world is there needs to be a better default that provides what Souffle provides in some sense, but doesn't go off the rails all the time.
The off the rails here is the data loading, right? But it ran fast. It looked great.
Yeah, the performance though. So you seem to be talking about more like bad join planning and stuff like that, where this is more like I/O, and that's kind of an intrinsic issue, right? It's just like you have to load everything into RAM.
But it's more than just that, right? Like this particular example is just data loading. But there's a whole bunch of other ways that Souffle goes off the rails, and planning is part of it. Index construction is part of it. If you know what plan directives are, I view those to be an affront in so many ways. Yeah. So yeah.
I'm very interested in actually just knowing how does XSB beat Souffle on TC? Is it doing worst case optimal joins, or like what's it? Because
you can imagine, right? By the way, that was computing, right? All paths, right? And all pairs, right? It's not like even query would be even much faster. No, but even for that, right? Basically, it does tabling. And so first of all, XSB was compiled to this thing that runs in the C emulator. This tabling, they optimize so hard, right? Think about it. That's like the minimum overhead.
Right.
It's just absolutely, anyway.
Right. So it's materialization, right? We can talk more offline.
Yeah. No. This is all good.
I didn't mean to disrupt it, but it was like a recurring theme was Souffle.
Yeah, I know.
And it's hard building a general tool that works for all things for sure. And I just wanted to make sure I was getting the right take out of this, because if it is just Souffle is the name is also like cool, like pick a thing that's full of hot air and collapses. But trying to get my head around what for each of these things,
is that Souffle does lots of things pretty well. And so it's a good baseline for people to use, and that's why people use it. But then anyone actually working on Datalog is trying to sort of push out in some niche direction a little further, and then beat Souffle. And then they all want to say, well, look, we beat Souffle.
So
that's why everyone's trying to beat Souffle.
I have an anecdote on this. So Byron Cook, who I'm presuming a bunch of people in this room know who I'm talking about, once said to me, one of the best ways to succeed is to solve a problem first badly. Because then everybody has to cite your lousy attempt at it. And any attempt you make it better just decreases abilities to beat you and therefore decreases your citation count. I'm bad at following this advice, so anyway. Yes, yeah. Well, that's not really my goal. My goal is to actually solve people's problems. Anyway.
But just like to unpack the slide, for example, SQLite Datalog doesn't destroy Souffle because of advanced join planning or worst case optimal joins or anything like that. So
I will say its join planning is significantly more sophisticated than Souffle's, right? Souffle does like left to right join planning, right? Whereas SQLite actually does cost-based estimation and does for what it is, very good job of it, right? Anyway.
Souffle might be unintentionally following this advice because I think in a lot of ways it's gotten slower over the last 10 years. I thought it was pretty impressive in like 2015, but in some ways it's gotten a little bit slower. But I think they've been really optimizing for memory use, right? Like the shared indices work was really cool, and I think they've also innovated in their data structures to improve the memory use. Yeah, that's kind of orthogonal. In fact, sometimes it hurts performance.
So anyway, back to my talk. But compute-bound queries are quite slow compared to Souffle. This is not really a surprise. Large, complex queries fail due to the 64-table join limit that's built into the SQLite. This was a really big annoyance the first time I gave it to a user and they hit that limit inside a generated query. It's really hard to work around that 64 join limit. Yeah, don't bother. It's not really worth the effort. And the join optimizer, while sometimes is good, is also often a curse. Cardinality estimates tend to fall apart when you're joining beyond 4 to 5 tables. I'm doing self joins like in a lot of these things. It'd be like tens to hundreds of tables, right? Usually self joins, because they're usually on the AST table. And so the join optimizer takes a perfectly fine query and makes it bad. And the big problem with this is it really makes it impossible to predict when SQLite is going to fall over. And this is a really, 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 really bad property for a code analysis tool that you're hoping people are actually going to use. So, all right. So you might ask, what about other database engines? One of the things is I don't want to be running this on a server. I want this on like end user terminals kind of thing, like grep kind of style here. So you could say something like DuckDB works here. It doesn't have a join limit. The query execution is very fast. But it's designed for these OLAP kind of use cases where it's basically really, really, really heavily optimized for scan and aggregate kinds of things. And so it has a poor / limited support for highly selective indexes. And as a result, it is really, really good at using a lot of CPUs to accomplish no more work than SQLite is. It's not actually faster at these kinds of problems. But boy, does it load data off disk a lot faster. So I guess that's a thing. Kuzu, which is a graph database that has every feature under the sun, is slower and buggier, falls apart. So this brings around the last part of my talk here, which is building a better Datalog. You've already heard a little bit about this, so I am working with Oliver on this. So Draupnir, referenced here, hedgelog, which is, I think, the language that sits in front of the Draupnir engine is sort of where we're headed with this. But designing a data log for analysis. So embeddable data log, disk-backed. One of the bizarro constraints is that I have a lot of users who have like 8 to 16 gigs of RAM on their machine, and therefore analysis of big things need to fit inside 8 to 16 gigs of RAM and be happy. Controllable, so join order algorithms should be user controllable. So do automatic generation as like a default, but be able to override that in some sort of way that is programmatically reasonable and doesn't fall apart like plan directives in Souffle. Incremental, so one of the issues of this is, at least when I'm using this, is I will write something. It is almost never the right thing on the first try, and so I'm modifying that query and producing a new version of what is almost the same query, but not quite the same query. So this is a version of incrementality that's a little bit different from like I've updated the program that I'm analyzing. This is I've updated my query, but you can use a lot of the same tricks and techniques from incremental view maintenance to do this variety of incrementality. And ultimately customizable, allowing for user-defined functions and aggregates. And in particular, I think aggregates are a place that are interesting and relatively underexplored in this. Like viewing a lot of program analysis infrastructure as aggregation is kind of interesting. Like function summaries are a version of aggregation, and being able to support function summaries is useful for constructing large-scale program analyses. And I think you'll hear about from Dennis on this tomorrow, some work that Dennis and I have been doing where we actually do function summarization in Datalog. And this is a problem when you have, say, recursive functions, because now you've just introduced recursive aggregation and you've got a problem on your hands. Yep. So, yeah, okay, fine. It's a little bit different. I think the program analysis workloads are a little bit different than kind of your traditional SQL workloads. So going forward, this project, which Oliver introduces Draupnir, we've also been calling hedgelog, which is a new Datalog variant with selective incrementality, custom aggregates, uses monoid semi-rings and rings to do these aggregation things, and pushes kind of the expressivity boundaries of Datalog, and it's all done in a way that it's disk-backed. So the Spinning Rust project of this is developing disk-backed Datalog so we can fit stuff onto bigger analyses onto smaller workstations. And yeah, the goal is to incorporate all this back into this code search and analysis infrastructure and produce something that is hopefully more reliable than what I've been able to deliver to my end users today so far.
I'm very happy that we have Dr. Annie Liu here from Stony Brook, who's going to be giving this talk on incremental computation. What is the essence? Something that's kind of core to sort of everything I think we work on. You need to use incremental computation to really make it work for real, right? So I'm very excited to have her here and looking forward to her talk. So thank you so much for coming.
Thanks so much, Chris. And thanks everybody for cutting short your whatever kayaking trip. So this was given actually CPEPM first I prepared. I actually spent a long time working on this, but you will see. Oh, Stony Brook. That's just 50 miles east of Manhattan. Incremental computation. It studies how to efficiently handle continuous changing input by storing and reusing previously computed output. Okay, I say there are two big kinds of views. First, computer programs, right, handle input from the real world, and real world changes continuously. So you need incremental computation. But the other one is even more exciting. Any computer program processes non-trivial data, by iteration or recursion, loops or recursion. Okay, and the computation happens by, working on the repeatedly changed states. And that's incremental computation, okay? You already see it's fundamental and ubiquitous. There are all kinds of graph algorithm, program analysis. We talk about all of them here, and everything non-trivial essentially, including automatic differentiation in training neural networks. So what I'm going to talk about the two parts. This is the first part, an overview of incremental computation. There are tons of work. I group all of them into just 3 categories. And the point to show is just the essence. I call incrementalization. And I will also mention how it's related to partial evaluation exactly. Okay? And second half, since the essence is incrementalization, how to do it systematically. And that corresponds exactly to differentiation in calculus, except that's, continuous domain, we do on discrete domain. And even more exciting, when you do optimization by incrementalization, it's integration by differentiation. Okay? And then the side message is you can do this to any computation at any level of abstraction, but if you do a high level data abstraction, control abstraction, module abstraction, you get beautiful results. Okay? You get new and better algorithms or improve the complexities and even better problem specifications you will see. Okay? So, of course, this is only possible because of all this amazing work. You might recognize some of these things at the top, and all the amazing collaborators. And by the way, the first one here, Scott Stoller, is right there. And these amazing students, and my advisor at Cornell, and some people working at Uni Road, and grants, and even some industry grants too. Anyway, this is one slide about the 3 categories. Okay? The first one, incremental algorithms, including dynamic algorithms, online algorithms, streaming algorithms. Okay, these are specific algorithms for computing particular function and particular kinds of input changes. Okay, like computing shortest path, okay, and the changes adding, deleting a graph edge. Okay, and you can do, wow, airplane. Wow, look at that. Oh, beautiful. Wow, I've never seen it so close.
Yeah, there's a seaplane.
It's just, can we take that? Yeah, so for us in language compiler, of course, incremental parsing, incremental, just all that stuff, okay? And the second is try to be more general. So these are incremental programming evaluation frameworks. And there's some frameworks trying to evaluate at least general classes of problems, okay? And you can express certain functions and certain input changes in that framework, okay? And this is function caching, tabling, I mentioned the change propagation, and all kinds of combinations. And the last one, incremental algorithm and the program derivation methods. Okay, these are methods that can derive the algorithms or the programs given functions and input changes. Okay, and there are lots of transformation techniques, tabulation, finite differencing, deriving incremental view maintenance. Okay, actually I will talk about even more precisely later. So just a quick look at the history, right? The oldest one, Henry Briggs, had this tabulating polynomials. Okay, that's from 400 years ago, and Charles Babbage actually implemented that algorithm, and that's the difference engine, first computer, some people call that, and 200 years ago. In terms of paper writing, there's one paper actually called Incremental Computation by Lombardi in 67, but I couldn't find the picture, so this is even the 2 papers. This is the earlier one, okay, on incremental computation of computing lists as expressions. And then this one by Michi called the Memo, published in Nature, 1968. The title is called Memo Functions and Machine Learning. Okay, that's all the memorization. Of course, in terms of transformation, there are all these pioneers, especially people who invented the high-level programming languages, like John McCarthy, cursor functions in Lisp, and Jack Short's sets in the Settle programming language. I mentioned to some, that's predecessor of Python even. All right, so even in 1993, Purple 93, there is a paper just talk about bibliography, 117 references. Okay, and now the thousands. So anyway, in terms of essence, this is really the one definition you need to know, and happen to be somehow when I formulate this way, everything else falls in exactly. Okay, so incremental program. Okay, given a program f or a function, and operation delta. I describe how the input to f changes. A program f prime is called the incremental version of f under the plus. If f prime computes fx plus y efficiently by using fx. So you compute fx, you want to compute fx plus delta x. I just call that y, okay? And so precisely if fx returns some result r, I want to compute the fx plus y. Of course, it depends on x and y, but I also wanted to use r, the previous result. That's why there are 3 arguments here. Okay, there are lots of formulations like this before, or even after, but not exactly like this. And they don't work exactly. They work for a lot of classes. Okay, so incrementalization is the process of deriving f prime, giving f and plus. Okay, and I call that the essence, and we'll see how the 3 classes I talk about. The first one, right, particular problems and particular input changes, right? So that's just f0 and plus 0. And you get f0 prime. So this is exactly the same except the special f0 and special plus 0. Okay? And the second incremental evaluation framework, right? So this is an evaluator or interpreter. You can think about the evaluator, right? Takes a program or a function and the data give you the results. Okay, and now the incremental version, the eval prime, would take that x, which is this pair, and y and r, and compute, right, this is 1x plus y. So, right, it's general because you can have, think about all different f's and some pluses, but those are the ones this evaluator handles. So it's not totally general, it's whatever the evaluator handles. Okay, but it's more general. And the last one. And you can already see this is just some magic inc function that takes f and plus and give you f prime. Right, so now it should be very precise. The 3 categories are totally different, even though they're all about incremental. Okay, any questions? Yes?
So for C3, is f like any function you can write down ever, or is it, I see, okay.
Yeah,
understood.
In principle, yes, but f of course has a language what you write, right, but the principle is the most powerful in general.
Right, okay.
Okay, yes?
For C2, are we imagining that y is allowed to change f as well?
Excellent question. Absolutely. In principle, this y can be changed. I mean, this x is a pair, although most frameworks only handle changed data. Okay? Excellent question. I was waiting to see this audience will have it. Excellent. Okay, so now I just make a little connection. I don't know, or should I skip this part? Everyone knows partial evaluation.
No, you should do it.
Okay, so partial evaluation, okay? It's just a function takes, input, you can separate into 2 parts. Say, let's call it x1, x2, 2 parts, okay? And then partial evaluation says, let's evaluate f on some particular value for the first argument, okay? So you get, partially evaluate f on the particular value of the first argument, and you get f specialized to that argument. Okay, like x squared plus y squared, now you know x is 5, so you can compute 25 and wait for the y. So now indeed, now later when you gave the y, the x2, then you can compute it more efficiently because you already did everything on x1. Okay, that's a partial evaluation. Now this, I don't know, people all know the Futamura projections. That's the magic thing that's, gave you the compiler generator. I don't know, do I need to do this or just we all compiler people, right? I said, compiler class should.
Please.
Oh, okay. Okay, right, this is database expert. So anyway, so interpreter, we already seen, takes a program or a function and data produce a result. Now remember the partial evaluation was taking the function and apply to the first of the 2 arguments. So look at this thing. A partial evaluation take the function and the first of 2 arguments. So take interpreter and the first argument, it get the interpreter specialized to that program. And this is, right, fx1, and then that apply to the x2, the second argument, that gave you the result. But now if you stare at this function, right, what does it do? It is something that takes your data, gives you the result. Didn't need an interpreter anymore. That is the compile the program. Okay, so partial evaluation is doing some kind of compilation, but it's, anyway. And now you can do the same trick, right? Now this function, this function takes 2 arguments, so I can apply partial evaluation to this function and this argument, and then take this one. So see, apply partial evaluation to this function and this first argument, I get PE specialized to interpreter, and that thing is going to take the second argument and give me to specialize the program. Remember, this is a compiler program. So something takes your program, gave you a compiled program, that is a compiler. And the very last one, since the same thing, this function applied to 2 arguments, function applied this function to first arguments, right? So PE applied to this function, this first argument, give me this PE to PE, and this guy's gonna take the second argument and produce that, right? Produce that. So this is something that takes interpreter and produce a compiler. So that's a compiler generator. And that's the end of story because that's all done. Okay? Of course, that's the theory. Anyway, we'll see how it's exactly related to incremental computation. In fact, in Pulp 93, I mentioned the incremental computation bibliography, but in fact, there are 2 tutorials that year. One is exactly called a partial evaluation. The other one is exactly called incremental computation. Pulp never had tutorials, invited talk, nothing, just papers before, and suddenly there are 2 tutorials, exactly 2, by Tom Reps and Charles Consola. Anyway, and then by the way, I looked, Pulp didn't even have tutorials for many years after. Some years later, quite a few years later, they had some invited talks. Okay, and the title is a tutorial on partial evaluation, categorized bibliography and incremental computation. But what's really interesting, actually, this paper I mentioned by Lombardi, okay, his second paper is actually called incremental computation, but if you see what he's doing partial evaluation. These are just S expressions. You know some part of the input, and you try to evaluate already and waiting for the rest. So he called it incremental computation. In some sense, you feel, yeah, it's incremental, but it's exactly partial evaluation. But what's really interesting, I found when I was visiting the assignments with database group, the first paper they cited for incremental view maintenance by Peter Buhlmann, okay? It's actually, if you look at the paper, it's called partial evaluation. Everywhere it's called a partial evaluation. Okay, anyway, but these are just a sort of computation view, right? If you take the transformation view, this partial evaluation, is done by specialization. And incremental computation, say you do this derivation transformation, I call incrementalization. And the correspondence in math, for those in partial evaluation, I like to say this is the Kleinius SMN theorem. I don't know, anyway. And then of course here I said it's differentiation. Okay. So partial evaluation, of course, is intrinsic to language processing, compiler, right? It's very core. But you can view it as a trivial case, actually, even, of incremental computation. Because this x1, x2, right, is a pair. And you can think, what's the change? The change is whatever x2 is, threw it away. And just keep whatever's on x1 and take any arbitrary y as the new input. Okay? On the other hand, incremental computation can be also viewed as a trivial case of generalized partial evaluation. So these Japanese people had these, Fujimura projections, and even in the 90s or maybe even the 80s, they had a paper called the generalized partial evaluation. There, it doesn't have to be 2 input. This has a fixed value. Okay, it's like any information you have about the input. For example, you just say x greater than 5. Happen to be your code saying if x greater than 5 do something, you can throw out the rest. So now I can say, well, with that view, I can say, oh, my x is some previous value plus y, and f of previous value equals r. And then you get incremental computation, trivially, if that works, of course. So I can say, wow, that's the almighty optimizer. Okay, so that's just on the side. Now I'm jumping to the second half of the talk. Okay, any questions? Because we're done with the 3 categories, what's the essence and connections. Okay, no questions? Okay, so you already see this picture, right? Ink, the magic ink takes F and the plus gives you F prime. Okay, how do you do this systematically? And this actually was my journey for my PhD. This was done just for recursive functions at that time. Okay, the key idea is I want to compute fx plus y. Okay, I want to use it compute it by using the result r of fx. That's the problem. So by doing program transformation, you understand everything here depending on x or y. So I do program analysis, okay? And actually the whole transformation method was inspired at that time. The partial evaluation people were doing lots of transformation to do the specialization. So the general transformation approach was inspired by their work versus a lot of transformation work that's not systematic. I try to do it systematically. Yes?
I have a question. So are you only allowed in your attempt to compute the updated result to use the old input, the old result,
and the change. You're not allowed to use any other intermediate state?
This is the first step, okay? You will see, excellent question, brilliant, okay? So the idea is everything about X and Y, so what I want to do is the first step, explore only the previous result, okay? This was, anyway. So the idea is I try to separate things on X from those on Y as much as possible, transformation. And for those on, right, for those on X, I hope to use R, okay? And indeed, if you happen to see fx after you're separating it, then don't compute it, replace it with R. Okay, that's just the most trivial case. In general, R is not just one number, right? It can be arbitrary data structure. It can be a pair, for example. So I can explore the structure, use parts of R. Okay, and right, I see it returns fx and gx as a pair, and if I see fx in the gx, whatever in the result there, I use, first of the pair is my gx. So that's data structures, and you can explore control structures. You can find, I see fx under some condition. It's not always computed, but under some condition. So I can say, under that condition, I can use it. That's just our standard program analysis, data structures and control structures. Okay? And turned out that was a really hard part. It took me 2 years to do this. When I finished my university, you can graduate. But then, of course, I got these questions like Michael asked. So here is it. Usually, you want to use intermediate result. Remember that memorization, caching, population, right? The question is how? The resilience paper then saying, these beautiful theorems, and afterwards I can do Fibonacci. Okay, that's just so hard. But I was lucky I wasn't trying to solve that hard problem. Once I solved P1, now you can see there's a trivial reduction. I call it a cache and prune. So the idea is I give F, I compute Fibonacci for it, I compute one number at the end. But I compute an exponential tree up there. What I can do is I can do a trivial linear transformation of the F such that if it computes, it will produce the whole exponential tree. I don't have to compute it, but it is a function that will return everything in the tree. Now I already solved the hard problem. You have everything computed and saved. My f prime of that version, the extended version, f extend, I call it f extend prime, will be able to use all the results to compute the new Fibonacci x plus 1, for example. Then, of course, not all is needed. We know Fibonacci, if you do the next one, you only need the last one before. Then prune, you do dead elimination, you delete all those. All these are static transformation. You don't really run that code. Okay? Alternatively, you can also do selective caching, right? You come here, look in your computation, you see fx, you use the result. But you can see, gx was in the intermediate result. Let me just say only that one. Okay, you can actually do either one. There's an interesting trade-off. But anyway, the whole key idea is it reduced the hardest part to P1. How to use this whole big data structure. Okay? Yes?
So, I like this it's a really elegant framework, but one of the problems that I've always, one of the problems, the difficulty I've encountered with this kind of thing is like, how do you, as the user, how do you communicate how the selective caching, or like where you want to apply the pruning and things like this in a way that isn't, that it doesn't just devolve to
absolutely
incredibly complex.
Absolutely. You cannot believe the transformation that cache all is totally trivial. Yeah. And then when you do incrementalization, of course, since I did the hard part P1, that was easy. And even just the pruning, that elimination, people studied for decades. None of them were even good enough to prune out the bad thing. We had to invent the algorithm to do that. We have the best algorithm for dead elimination, all recursive data structures. And this was actually ended with, I had to ask Patrick Cousseau, and even found it. Anyway. So anyway, that's the second thing, okay? And now, of course, you do really incremental computation. People know I'm not only using the result, I need to save something additional, okay? I call it discover auxiliary information. The point was additional, that wasn't even in there. How in the world are you going to find it, okay? And turn out you can find a whole class. Of course, that's the class of the chore. Okay. By the way, all these are systematic. Later, I will tell you some concrete intermediate result. That's totally automatic. Okay. So the idea is the same. Okay. I have this fx plus y. Okay. And something here was fx. Something was intermediate result gx. But if I see an hx that wasn't in the result wasn't in the intermediate result, what is that? Whatever hx. It's something that depends on x only. I could have computed because it only depends on x. So I call that a candidate auxiliary information. Okay, it's the same idea as reduced to P1 to find such a thing. And then I do the same thing. So basically this reduce P1, and I do the same thing. I have this extra thing. Now I put that back into the result too, add that to the result. And I do the same, compute whatever the original result, intermediate result, and that piece of things, and I incrementize. So that's the whole idea is reduced to P2. Okay, and turn out there's really cute example. You couldn't believe that's my thesis. I won't have time to talk about detail. There's also a really interesting trade-off. Indeed, the whole goal, as you said, is a mess. There are infinite many transformation papers or so on. The whole goal is how to do it systematically. Okay, and so indeed for this particular one, actually I was implementing. I don't know if anybody heard of the synthesizer generator. Okay, that's the interactive. So it's beautiful. Everything is right grammars and stuff. And my advisor's company actually produced that for no bias, we chose it, but it's really beautiful. I imagine you give me a sort, okay, and you say, oh, add a new element, and I just magically come up with insertion out of, say, selection sort. And how do you know where it comes from? And here we actually have a button. Mostly, there's one that's enabled. There are a bunch of transformation. You just click, 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 and see each step. Oh, gee, from selection sort, and give you an incremental just insertion. Okay. Of course, our later transformation, I don't know you guys, but turn out the recursive function is the hardest of all. Our later things are all totally automatic. This is semi-automatic. Okay, so you will see. Now, just before I continue, I just want to make a connection with differentiation also more precisely. Okay, so both incrementalization and differentiation, you see study changes in the output given changes in the input, right? I happen to be, of course, even use that prime for the incremental version. That's exactly the derivative. Okay, so indeed, x plus y. So here, the main thing is we say the explicit change operation, right, with a big Y or delta x versus infinitesimal, small. So this is saying how input changes from the previous input x, right? This is x, and this is the whole x prime, and this prime really says how the output changes from the previous output R. Okay, in the most ideal case, by the way, that combination would delete the x. Then that would just take the delta in input, produce the delta in output. Okay, but this allows you to do arbitrary case. Even you cannot delete it, you can still try to use all the result as much as possible. Okay, so that's the connection. Of course, there are many more actually. Caching intermediate result, that corresponds to exactly the chain rule in calculus. Okay, and discovering auxiliary information, that's discontinuity removal. In fact, it's much harder. Actually, for decades, I thought they do the hardest thing, but I was told. Anyway, turn out the handling changes in discrete domain is actually harder. Because when you're in continuous function, you just say, oh, it wasn't defined at 0, let's add a point. But in discrete domain, right, it's a matter of grid of lines. Most things are holes, and you have to invent a whole function to go through in there. Okay, that's why the auxiliary information itself is a whole function expression to compute. Okay, anyway, so the most exciting part is, which is totally beyond my thesis, because anyway, it's called optimization by incrementalization, and that's exactly integration by differentiation. In fact, when I did my thesis proposal, I did all the thing I said before, and Neuro said, oh, you're doing integration by differentiation. It took me 3 years to understand what he was saying. When I was finishing my thesis 3 years later, I was looking at my Fibonacci. I was telling you, right, Fibonacci, you say changes +1, and I smartly saved the previous result and just do a little add, right, and that's constant time. But I feel like, gee, what am I going to do with this trivial thing? And then I realized, oh, if you add a loop outside, I get a linear Fibonacci, starting with exponential Fibonacci. And then it took me only 3 years. And, oh, that's what he meant. I was doing, whatever integration by differentiation. So that's really thanks to a new world. Okay, now the exciting part, of course, there is a whole general method I studied after my thesis, and in fact, I did write a book. 3 steps. The first is called iterate. right? Anything non-trivial is not just 1 to 3 or 2, maybe something non-trivial, but the point was you need to determine a minimum increment to take repeatedly, iteratively, to arrive at your result, right? Input come in one at a time. You have a graph. You can do one node at a time or one edge at a time. Pick a minimum increment, okay? Now that's the delta. And then plus, I'm sorry, the same thing. But anyway, and incrementalize is just make the expensive computations incremental in each iteration by maintaining a distance value, as I talked about before. And then finally, if these computations were done with sets, database relations, you need to design appropriate data structures, linked lists and arrays. You can, of course, use hash tables, B-tree, whatever. Okay, that's the 3 steps. Question?
The first step in that process, I think there's sort of an implicit assumption that, to use your graph example, you're only getting sort of one type of change. Is that?
Yes and no. So what's really interesting, I have to tell you, in the entire approach, because you asked about the master and so on, everything beside the first step is just totally systematic. I said our new implementation are even automatic. But for the first step, the minimum increment is actually a heuristic. What's minimum? In what ordering? Okay? But happened to be this one took me 3 years after my PhD to find it. You think about Fibonacci, right? I said, if you have Fibonacci, if increment is +1 and you add a loop, but who tell you it's +1? Why not +2, plus k, -4? Okay, and in fact, there are all these complicated dynamic programming algorithms take multiple arguments. There are papers just saying, for this example, do this argument, for this argument, a lot of theorems, right? And for me, I actually, at one point, one of the papers saying, C number, +1. C list, adding 1 element. But 3 years later, I finally realized it's totally trivial, I just didn't think about. Because you think the only thing I could do, everything we've seen so far, is incremental computation, right? That means you give me F, you give me plus, I will try to reuse. Well, I didn't get to choose plus, I have to do that. But now I get to choose it. The only thing I could do is to reuse all the result. If I have a choice, I would minimize the change so that I could maximize the reuse. So that really took me a whole 3 years. And what's funny was this is the heuristic, but now you look at all these people's complicated paper, different arguments, you just take the minimum, and it's even better than what I did. I have these exercises, even Ackermann's function, all these complicated dynamic program algorithms. Okay, that's a brilliant question. It's indeed, this is the heuristic. This is the part, okay? But of course, for some domain, you actually know the domain very well, very simple. Then you know the minimum. But when people write arbitrary recursive function, you have no clue. And they may not even terminate, right? It doesn't exist such an order for you to finish. Okay, so it's a heuristic. Now here's the whole view of the whole thing. Okay, so basically the 3 steps, okay, applies to, everything I told you is totally general, especially here. And so it applies to all language features. That's what Kris asked, what languages? So indeed, it applies to loops, just basic primitive functions, arrays, like imperative programming. I call it imperative programming here, right? And set expressions, relations, like in database programming. And recursive functions, like in functional programming. And finally, logic programming with the logic rules. Okay, those are the really interesting part. And these objects are actually, they're totally orthogonal. And object with fields, and anyway, that's all programming, of course. But the key thing is, what are the abstractions? Not these names or function or imperative. So we're looking for high-level abstractions. So when you have loops and arrays, I say no high-level abstraction, because that's arrays, that's already how machine memory is in there, okay? But you have set expression, that's data abstraction. That's why database is so powerful, okay? And the recursive function, that's control abstraction. In logic programming, logic rule, Datalog, it has both recursion and the predicates, right? Sets of tuples. That's how powerful it is. But you see, I love this data abstraction because, right, if you want to do high-level abstraction, you have to first have a high-level data abstraction. So this method applies is, in all cases, you need to do incrementalization I2, 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 I2. But when you have control abstraction, you need to I1 because they're recursion. You need to turn to iteration. And when you have data abstraction, you need to I3. You need to implement the sets or relations in the right data structures. Okay? And the multi-abstraction doesn't, just wrappings. Okay? But it's important for scaled up application. Okay? So that's one slide overview. Any questions? So let me give you examples then. Oh, thanks for my former student Tom Rothman for the names. Forever, I don't have name for this, and they start to call this a Liu method. I didn't like this thing, and so Tom was a genius out of my all choices, and he just put, because one year I decided to put all these choice of name for each step, and he taken 0 time. He said, I like the I's, and you think about iterate, incremental, implement, almost like software engineering, but they are really the fundamental things. Except a lot of people say, what's that, the third Roman numeral there? But anyway, so here are some examples. Of course, I don't have time to tell you, but it's really magic when you do high-level things, okay? Even low-level things. So all the example I mentioned are ours, except the indicate about page. This is the Settle group people did a totally amazing work. Okay, so basically, when you just have loops and arrays, you can write it like hardwares. How to compute the square root, integer square root, and how to do image blurring. So that's the example we have. And the people in the domain, the expert, are saying, how can you do this? So of course we did what they did, and we did better. Okay, it's really interesting for each of the application. But my most favorite is the sets. Okay, you do the join query optimization, and all these applications really critical, right? With security, access control, and just program analysis, lots of things. I'll show you one example, and regular path queries. And for us, I mentioned the last, 10, 15 years ago, distracted doing distributed systems, distributed algorithm. It's all sets, sets of messages. Okay, and then Bob Page did this totally impressive work. He has the best. This is already from the 80s, 90s, or something. He has the best algorithm to do regular regression, to NFA, to do a DFA, the one we all learn, okay? And DFA minimization, tree pattern matching, multiple pattern matching, attribute closure, for those in database will know that. Anyway, partition refinement, for those who do model checking, that's just a couple years ago, the people who first did this even got the Dykstra award. Anyway, and then for recursive functions, any sequence processing, lists, and all the dynamic programming algorithm, you start with writing recursive functions, and you can generate the tabling, and stuff, and tabulation they call it, and match the algorithm text program, and better, actually. I won't have time to tell though. And of course, come back now to all of us, to logic rules. We start with Datalog rules, program analysis, so we have new algorithm for each of these instances. And for objects, there's no algorithm. It was just some way of wrapping, but you do actually yield these design patterns. Software engineering people have design patterns, and out of principle, you'll get those. Okay, and what's really nice for some of the problem you get, we get new languages and new specification of the problem. That's a simpler and better, including for distributed programming, even for set queries. We have these patterns. You can write Python can write comprehension. It's much simpler writing a loop. But if you use the pattern we have in our language, it'd be 1/5 of the size of Python comprehension. Okay, just write pattern like English, it works. Okay, so I really just want to emphasize that data abstraction with sets and rules are just so powerful. Okay, so I love the database and all the data work. Okay, but what's really neat is everything before we did this logic rules, right? You optimize, and here's optimized program. You can say, oh, this looks faster, or looks like a linear, quadratic, cube. But with logic rules, you can just stare at the rules, generate this so-called optimal program, but that's only half the thing. The most exciting was we generate the complexity formulas, the precise time and space. And you don't even have to understand that method. I show you an example. You just stare at the rules, you know exactly what's the optimal time and space. Okay, so, oh yeah, by the way, I mentioned Bob Page did impressive work. He also has something correspond to the III, which he called dominant convergence, finite differencing, real-time assimilation, and something to implement this thing, actually multi-set discrimination. Even quantum people talk about that stuff. But anyway, because he was working with sets, just exclusive set all. And so everything you feel like is very specialized to sets, okay? And turned out that they were just beautiful. This high-level thing, he can indeed just have a built-in set of rules. Indeed, in his paper at the end, appendix, rule C1, D4, I don't know how to name it, but it's just really powerful. Okay, so let me show a couple examples at the end. Okay, so this is the one indeed everybody has to see this example. Okay, transfer closure. But this was what we did right soon after I went to Stony Brook. And so let's apply the 3 steps. I. Okay, so for rules, the minimum change is one fact at a time. That's what your question was, is nodes or edges? Well, depending on your rules. It's for Datalog, it's just one fact at a time, okay? And then incrementalize, of course, you maintain the maps, that's like indexing, okay? Basically, right, if you add an edge and then this W is shared, so you maintain the index, that's map, this W to V, and vice versa. You need to maintain an inverse map of edge. Okay, but anyway, and then finally, of course, these are just relations. You need to design data structures. Now, let me tell you the most exciting part was the complexity. Okay, so the time complexity is the number of rule firings. For rules with 1 or 2 hypotheses, is absolutely optimal. Because every combination, right, of this thing that can match, you have to at least consider it. Okay, and this method is considering each such combination at most once, by the way, in the data structure, in the worst case, constant time, okay? So that's optimal in that sense. And you can actually do with me, for this example, how long does it take to compute, right? The first rule, how many times it fires, I didn't even put in here. It's just number of edges, okay? And the second rule, well, there are 2 ways to fire. One is you consider every edge, and for each edge, you need to find the matching path. So number of edges, and then with the fixed W, you need to see how many V's come out of each W. Okay, so that's edge. I use the notation, path dot second argument per first argument. Okay, that's an out degree. Okay, that's as a bound. Okay, and symmetrically, you can say, I may count path and see how many edges matches. So it's number of paths, but here is given the second argument, how many first argument are there. So this is dot 1 per second argument, okay? Both of these are upper bound, right? I'm saying this is like the maximum out degree. In my real computation, it's an exact match, really optimal. But both are upper bound, so indeed you can actually see, right? This is edges. This in the worst case, every thing goes to everything else. Then it's number of vertices, okay? And by the way, Arlen textbook wouldn't tell you it's edge times vertex. They tell you vertex cubic, right? But for a sparse graph, it's much worse than this. But the other bound thing is output times in degree. If you have application, your in degree is constant, then it's optimal because you have to print the output. In fact, for program analysis, by the way, if you change the order of this path and edge, right, it will be output times out degree. So for analyzing programs, in degree, everybody can call this function, but out degree, if you have if then else or case statement, it's a constant number of output. So it's optimal in your output size. Okay? And there's analysis for space, I'll skip. It's a SID, okay? And now here's interesting. I told you this works for rules with 1 hypothesis or 2 hypotheses. What if you have more? Okay? Here's one example, regular path queries. You have a graph with edges and vertices and one initial vertex, and you have regular regression pattern. And what you want to do is find all vertices in the graph, okay, such that there's a path from the initial vertices to that vertex that matches the regular expression pattern. How do you do that? Okay, well, the regular expression pattern can be turned into an NFA trivially with transitions and states. Okay, so that's what the initial states and transitions, that's the NFA for P. And that's the standard 2 rules to do this, right? Initial vertex matches initial state. And then if some vertex matches some state, and there's edge coming out, there's transition come out, then the end vertex matched end state. Okay, that's the 2 rules. So what do you do now? We have more than 2 hypotheses. You break. The second rule, I do the first 2 together first. See that? I introduce a new one that takes all arguments in here that appear in the rest. So this has V1, S1, V2. Okay, but V1 is not used afterwards. This doesn't have V1. So I only have S1 and V2. And now this thing can take the transition and give the result. Okay, that's just breaking. And you can actually break 3 ways, right? You could also break this one and this one first, or these 2 first. But what's really interesting was almost for all problems essentially we have, you just actually do the first one, already give you the best one. Because for each one, we'll generate a complexity formula. And you can see which one is the best. Okay, so for this one, you can calculate yourself. How long does the first rule, how many firings, how many combinations the first rule matches, right? Say this is number of edges. And then when this V1 is fixed, it's just how many states. So in the worst case, all states, okay? So it's edges times states. And the second one is saying the transition, worst case is all vertices. But see, that's the complexity, edge times states plus this. But the standard model checking people doing forever, they were saying, oh, the complexity is a product automata. Product automata is edges times transitions. And if you have a dense graph or dense transitions, that can be a whole number of vertices difference. If you have a million vertices, it is a million times slower. Okay, so that's an example. And of course, by the way, there's a trade-off, right? You don't get for free because I save these intermediate results. Okay. And then this is the, program analysis point analysis. Anderson's algorithm that also shows up in almost every Datalog talk, right? These 4 kinds of C statements, and I give them name, and these are just copied, from everybody, the 4 rules. And the only thing you see, oh, now these 2 have more than 2 hypotheses. Break them, as before, exactly. And just even combine the first 2, right? See the first 2 here give you something, and that something, take this one, give you that, exactly the same. But what's neat was you have this big complexity formula. Okay, the Anderson's algorithm is famous to take a cubic time. Okay, and there's so many papers was saying, oh, we did something, some optimization special with cycles or whatever. Now it looks like a quadratic, looks like a linear, but on some of the 10 examples. But why, right? And so now you can actually see. Imagine if you didn't have this form, this was all gone. Okay, and in particular, the 2 really meant points to, right? The points to. So unless your program, everybody points to everybody, there's not n. That's just how, for each one, how many they points to. Okay, so that you can explain exactly what's the complexity. Okay. Do I have time to talk about distributed algorithms? These are really exciting. That got me stuck in here. That wasn't my goal. So. Indeed, all the optimization here is incrementalization of logic quantifications for all and exists. Okay, we had those examples. If you take the whole access control, standard, whatever 50-page standard, there were only like 2 quantification, and we just did that ad hocly, right? Quantification. But then you go to distributed algorithm, it's like the tiniest thing has lots of quantifications. So you have to do it totally systematically, okay? So I won't talk about the detail, but the point was, unfortunately, the distraction was we had to invent a whole distributed programming language. Because in Python, right, if you do centralized sequential programming, you tell kids, I teach the pseudocode, make a colon, make indentation, it runs. But for distributed protocols, well, gosh, the pseudocode to say send a message or wait for reply. But if you want to implement, you use your, MPI or OpenMP, it's huge number of libraries or sockets, whatever, right? Hundreds, thousand lines. So I want to do is just extend Python. And so you can see actually it only has 3 things. Distributed processes, just object can be concurrent and distributed, or can send the messages. And then when you have control flow to say how you handle receive messages, it's actually just 2 contracts, await and receive. But most exciting is this part. We have high-level queries of message histories. You decide what to do based on what message you sent and received. So you don't have to write all the low-level handlers. Okay, so with this language, actually, this is the first time I actually built a real language, and of course my students, but before even the little language, and here this one actually extends Python. Okay, so you can write arbitrary Python and that stuff. I won't talk about the detail of the syntax, but it's really beautiful and was using things from the Settle's predecessor, but the Python's ancestor language called ABC. It had this beautiful logic quantification, writes like this. Some X in this set has some property, right? Instead of colons, bars, or Python general expression, you just totally readable. Okay, but the key thing is, again, systematic incrementalization. I'll show you one trivial example. This is the Bible paper in distributed systems. So Leslie Lamport had this invented logic clock, and afterwards he had to say how to use it. So he has a mutual exclusion algorithm, which is described from here to here, okay? And he has a whole separate paragraph at the beginning saying how to how to initialize it. Okay, so I copied there. I didn't copy the paragraph initialization and has all these steps. But if you write in this algo, and this is a complete program, I mean the algorithm part. But what's most interesting is, this is what the keyword are highlighting. Most interesting part is if you see all the rest are trivial. Send a message, get the logic clocks. It's this thing, condition. You wait for each request, each request in the queue, your own is smaller than all the others. And for every other process has already sent you a reply. So you can already see each has something. Each something has some. That's already 3 quantifications in this little code. Okay, so what's really exciting was actually incrementalization gave you this. Everything's exactly the same except inserted the blue code for incremental updates. And the red one now becomes just looking up in the queue. And this one has an even much interesting story actually. Turned out, we don't usually delete the critical thing, but this example is gone. And turned out you can simplify that code, right? It's like 20 lines in here, and now you can simplify to just without any queue. And then turn out you can even simplify without logic clock, basically, just number. But what's really interesting is once you make this so simple, we have the systematic method. We can do quantifications, or actually turn quantification into aggregation and incrementalize it. And what's really exciting was for this example, you do systematic following our method. You don't need a queue at all. So this is the same as before. You just add a little more green things. Instead of a whole queue, you have to do some kind of priority queue because of the comparing order. It's simply 1 bit each process. You match that. And actually, for this example, we even found bugs in the algorithm. Almost every algorithm we looked at, there's some bugs just because it's so hard to get it right. Okay, I'm not trying to sell all this thing, but when you make it simpler, you can look at it and you'll see all these problems. So here's the conclusion. Okay, the first part was just the 3 categories. And the key thing I want to emphasize is incrementalization. And the second half is how to do it systematically with this II method. But the key of all of this, which I really love this workshop, really try to come, is the high-level data abstraction, okay? And actually a bunch of these things were published in the Program Transformation Conference. But actually I was a little regretting I didn't have time to prepare more when I was hearing people's interest. What we're doing actually, this is near to our heart. We even to do all the years since whatever 30 years ago. But what all these enabled, especially distributed system, right? Needed quantification. Since we do quantification, we actually now say, oh, we don't have to worry about how to implement these quantification. We can actually even understand these rules with negation, recursion, aggregation better. So we do have a unified semantics for arbitrary negation, arbitrary quantification. Okay, so that's our work in logic rules with constraints. Very simple and unified. And then of course the other part was the distributed algorithms. The one thing actually somebody mentioned, but anyway, all of you here, of course, Rust will help you do a lot. You do arbitrary things and you can do some Datalog. But what we had since already extended Python with this algo, like distributed part, we also extended Python to have Datalog. Okay, and there what's really neat was you think about it in logic programming, I don't know if you guys know the Prolog people, right? You write the path and edge. Turn out that computes transitive closure. But if you have another example, I don't call it edge, I don't call it path, I call it, say, link or connected. You cannot use those 2 rules you have because those are constants. They need a higher order logic to do that. But when I connect this to Python, the edge and whatever path is just set of pairs. I can pass in any set of pairs and get out any set of pairs and call it anything. I get a high order logic, so-called whatever the thing for free. Okay, so that's the last part we're doing. That's all.
So much.
You mentioned earlier the code itself. Could you say a few words about if there are special considerations for incrementalizing changes to code as opposed to changes to data?
I see. Interesting. Of course, the whole thing. I even started my thesis. Okay. Well, I mentioned the synthesizer generator. I guess these are so young, never heard of it. But anybody know Tom Repp's? Okay. So that's Tom Repp's PhD thesis. Of course, my advisor started that even before. And the whole point was IDE then even started 70s, but Tom started 80s. And there was indeed, you write the code, right? And they try to do the smart attribute evaluation. That's why they have not just the parsing, they have attribute grammar to describe your types, your defined variables. As you type, it will tell you it's undefined or it's wrong types and all that stuff. And so the whole point Tom did incremental attribute grammar, attribute evaluation is as you change the code, these analysis is expensive to find types. So how to do incrementally. So because every type was specified as attribute grammar attributes, and so his incremental attribute evaluation framework, that would take care of it. Of course, that's also when Tim had all new students, that's not enough. That's, by the way, that's saving this thing and change propagation. That's what he first had. And then Susan Howard's actually take this whole program as a database. And she actually did incremental view maintenance for program as the database. Okay, so indeed, as your talk is that all that thing about the programs, those are tree facts and or database relations, and the incremental computation on them or just happen like you do.
So there, you're treating the program as data itself, but you had that sort of dichotomy in your presentation of the incrementalization takes in, or the function takes in both logic as well as data that the logic is applied to. I'm curious if there's somewhere fairly early on in the talk.
Yeah, actually the Y, right? This definition. This is really the critical one. This one that takes the old input, the change to the old input, and all the result.
So a little bit further, you had, sorry, this was for the interpreter, incrementalizing the interpreter.
Oh, that's not the incrementalizing interpreter, that's a separate thing. This one you meant. Yeah, okay.
Right.
Yeah.
Is there some fundamental difference between the functions and the data in that picture, or could you just treat them both as effectively forms of data?
Yeah, indeed, for lambda calculus, for example, I mean, you can think that's just a lambda expression, and that has some functions and data in there. But on the hand, for exactly this framework was first for the attribute evaluation framework. Okay, so this evaluator is the attribute evaluator. Okay, and then this F is any like type analysis, whatever, define whatever analysis, and then this data was of course your program.
Right.
So there the separation is really important just because the attribute grammar framework is formulated as a tree and decorate the trees. And so the equations is the F, and then the tree is the data.
Can I try to your question in a different way?
Sure.
So that's code as data, but it's not exactly, I think, what he's asking. If I have a program and I run it and I get an answer, and I realize that my program has a bug, and I change the program, where ideally incremental evaluation would let me reuse the non-buggy parts of my program if my fix were somehow local. Where does that fit into this framework of thinking about incremental evaluation? Did I get that right in your question?
Essentially, like if I change some portion of the data that feeds into 3 joins, okay, I'd like to be able to reuse the part of the result that doesn't come in, that doesn't get touched by my change, right? And it seems like they're closely related. I'm wondering if there's, the question is there some fundamental difference between propagating changes to the program and propagating changes to the data?
I see, right, when you describe everything as facts, right, then it's the same, I can have a see. But to answer his question when it's separated, indeed, this incremental attribute evaluation framework was used when they write the whole interpreter. They write so many other functions, even including graphics thing, using attribute grammar. And then when you write the evaluation, I mean, the interpreter is the attribute grammar, so when you find a bug of whatever reason, you changed it, and everything was saved and reused it and do the change propagation.
But let's say I find a bug in my attribute grammar. Yeah. Not in my program.
Okay.
Attribute grammar.
I see.
I find a bug there.
Oh, there, no, they had to recompile.
Okay, but then to me the question is, so for incremental evaluation, are we talking only about changes to data? Or can we also talk about changes to the program?
Yeah, that's what his question. So this framework is not limited to, right? This is just saying the whole program and data is the X. And if you have a good framework, you should be able to handle plus Y. Y can change the program or the data. In fact, when you write Datalog, I mean, that's why database is so powerful. Everything just relations. And it is the same thing. Yeah. I hope you're happy with that.
I find this incredibly exciting. Like one of the interesting things to me is you got a new Datalog rule. Is there something fundamentally different about the incremental recomputation that I need to do to insert that one Datalog rule, or is it just compute what that Datalog rule would have computed, insert the resulting tuples, and then you're back into data?
Yeah, especially for adding incremental or adding rules, absolutely everything totally reuse. Add that thing and for everything new, that's all. When you have deletion, negation, that's a separate story.
Yeah, okay, I could see that being a problem.
Yeah, but of course I mentioned that what we did.
Well, at that point you need, some sort of, fine, it's not dramatically worse than deleting data.
Yeah. But that's what actually I didn't get to talk about, which I actually talked about the ICLP that have invited tutorial last year, and even this year at this paddle was talking about semantics for negation and aggregation. Actually, it's actually also least fixed point computation, and so you absolutely can do it. But the hard thing for that is actually that's what I'm interested. That's what we actually Scott and I did in the last number of years. We haven't really had any serious implementation. We had the sort of little prototypes and even Scott just to prove, I mean, think about their PQR example, what does it mean even, right? You cannot do this by hand, we have the semantics. But in terms of that thing, I think really settled what's the semantics, and really should be time to put all these together.
Excellent. Well, thank you so much again.
Okay. Sure.
The next talk in the session is Andrew Johnson's talk, who's going to be talking about some work in progress. The talk title is Distributed Runtime Checking of Mostly Monotone Queries Networks. That's very exciting. I think everything I've been doing myself has been monotonic, but I've always been very interested in kind of the non-monotone cases because those are the very interesting ones to me. So I'm excited.
Yeah, so thanks for coming out. Thanks, Kris. So yeah, this is a kind of work in progress. It's part an example problem and part kind of a proposed solution. So I'd like some feedback on it. So here's the motivation or example problem. A combination of factors has led to a rise in the need for effective and automated runtime monitoring generation for networked applications. So one factor is that hardware has become programmable in the form of either programmable switches or FPGA-based NICs. And this has led to what is essentially organization-specific networking algorithms. So instead of having the one routing algorithm ASIC that everybody uses, now Google has their own, and Amazon has their own, everybody has their own. Well, of a certain size. So this is super useful for these companies because it makes their networking algorithms very flexible, but it also leads to this explosion of kind of bespoke network protocols that no one's checking, and a lot of them have errors. They have like teams of full-time software engineers that work on them, and they change them all the time. So This is a little more resistant to kind of the standard version of network verification, where you take the one big network protocol and you do a bunch of thinking about it, and you say this protocol is right, and this implementation is right. Instead, we need some form of runtime monitoring, so that when every couple of months they change their control plane algorithm, they can still check their safety properties without having to go back and change their big safety proof, which nobody's going to do. So this is what kind of I want. Users will specify a set of global properties that their system should satisfy, and these will change sometimes, but probably less than the protocol. So for example, if you have some safety property that you're not dropping packets randomly, and you make an efficiency update, you probably still don't want to be dropping packets randomly, something like that. And I want to compile these into local monitors, and then they'll detect errors if the global property is violated. So this is going to be our running example, which is priority-based flow control. It's used in many places, but one of them is in RDMA systems for ML training. So this supports, the whole point is that it supports lossless congestion control, because especially for RDMA, you don't want to drop packets at all, and it's for basically high availability and deep queued networks where they don't think packet loss is going to be a problem, as long as, or they don't think crashes are going to be that big of a problem. So it works by just having nodes that when they get full, when their queues get full for any reason, they send messages upstream to their neighbor and they say, stop sending me packets, this pause frame, and then when they're ready to go again, they send a resume frame and they can keep getting packets. Here's an example of this working properly. Let's say S2 becomes congested or breaks or whatever, and then its queue fills up, it'll send a pause frame upstream to server 1, which will no longer send things to it until it like comes back online, or I don't know, clears its queue and stuff.
So there's no acknowledgement to the pause frame?
No.
Okay, I see.
Yeah. The whole network is supposed to be lossless. Like, you're not really dropping packets on the wire ever. The only way you could drop a packet in this model is if your queue fills up and you drop them. So that's all really the only thing we need to avoid. So then it empties its queue and then it resumes it, and then the network is running properly again. There you go. So this was, again, for these data center networks where they figured if we just put in these pop frames, nothing will drop. But as you can see, there's no ACK for it, and it looks like ripe for deadlocks if you have a cyclical network. This wasn't a problem when everything was like a fat tree, so there were no cycles, but people have been playing with data center topologies a lot, and now there are cycles. And they've found, here's a citation, oh, well, down here, where deadlocks happened in like Microsoft's RDMA rollout, and they had to basically implement a distributed deadlock detector to fix it. So that's kind of the thing, the main example I want to do automatically. So again, what I want is for the user to give me a specification of what their error is, and I want them to give me a data structure that tracks it globally as though it were like an omniscient monitor that saw every event instantly when it happened. And then they'll also tell me some function on that data structure that causes them to, oh sorry, this is an example of just the deadlock occurring. So again, the same example earlier, but now S2 just takes longer to come back online, and we get into this loop of 3 pauses, and it's just totally stuck. There's nothing in the PFC to recover from this. This can either be spread to the rest of the network and just like no packets will ever flow, which is obviously really bad, but easier to detect, or it could just be like this local thing, and now just these 3 servers are stuck, and you'll just have terrible throughput and wonder why. So yeah, this is the approach I kind of want to take, where you specify this global omniscient monitor as a state machine, and it has some data structure S and some query Q, which is a function of S, and the query is whether or not there's a bug. And it takes the events, which have their locations and the nodes, and then it should output local checkers to run alongside the application. In this case, the checkers would be looking at the pause frames and where they're going. So yeah, in this case, the events would be the pause and resume. And the nodes would be the network components. This data structure, again, this is user provided, but in this case, the most obvious one is just a network graph that says whether each edge is paused or unpaused. And the query is something like a DFS, you'll look for a cycle. So this is what that looks like. In this little, here's the little graph. IJ means I is pausing J. So when our deadlock occurs, that will change 2-1 to pause, and then the next one will change 1-3 to pause, and finally we'll change 3-2 to pause, and we'll blow up. Yeah, go ahead.
Is the network topology dynamic here? Is that where the problem is coming? Because you said like we have the network graph as input, and the question is, does it have cycles? Which doesn't feel like you would need to do that at runtime, right? So,
well, the graph of pause frames, not
graph.
The graph of who's pausing who. Sorry, not the graph of just who's connected to who. It's the graph of whether or not they're paused. So in this example, like U means unpaused and P means paused. Is there a cycle of pauses? So you could follow this. Okay, 2 to 1, and then 3 to 2, then go to 3, and then back to 2, and that's your cycle. Does that make sense? Okay. And so, yeah, here your query, as I just said, shows you there's a cycle. That's an example of the problem. I have a lot of different problems in the networking domain that follow this kind of paradigm. But my idea for compiling to local checkers is to use CRDTs, which is conflict-free replicated data type, and they allow independent distributed changes and there's no round-trip update, so there's no ACK, which is really nice. And so these are basically anything that includes a data structure that has a partial order and a join operation, and it guarantees monotonicity and eventual convergence as long as you send updates forever. And I think we all know what that is. So the plan is to have this global spec. We look at it, we come up with a local version of the data that's stored at each node. And the user will build their global spec with basically a library I'll provide of types that can convert themselves to CRDTs. Every message, be it pause frames or other packets, so that's kind of the key thing, will piggyback CRDT state changes kind of as they happen. And then any detected error is going to be a global violation for monotone queries. And what monotone queries mean, because the data structure is always going to be going up in monotone because it's a CRDT, but a query is monotone if once it's true for the state, it's true for every subsequent update. This is not true. Oh, sorry. I'll get back to that. So here's this kind of the proposed solution of local checkers for PFC deadlocks. Now we just have a little table at each server, and so when it pauses, it pauses the 2 that have heard about it, and then eventually it'll gossip it down to number 3. When the second pause happens, the same thing occurs, and then once the third pause goes, S3 will know, as soon as it sends the pause pretty much, that this is going to cause an issue and it should start whatever deadlock recovery mechanism, which will be like, some sort of network reset or dropping a whole queue one at a time. So the problem is that what I told you is kind of unsound, because if you have resume events, even though your CRDT this graph you can pretty easily make a monotone data structure out of, the query itself is non-monotone. Because I'll show you an example of why, but basically unpausing can cause a deadlock to go away. So if you're in this kind of risky state here, and S3's queue fills up, and it sends this pause, well, it's going to think, oh, I just caused an error, but it doesn't know about some resume frame on the other side of the network because S2 came back. So actually, this is like a near miss deadlock, and it's a false positive. So the idea to solve this is to use a system of vector clocks, and we'll just have a clock at each server, and we'll also have a clock. This is an introduction of vector clocks. Basically, they track logical time, which is just a natural number. They're ordered as natural numbers are. One vector clock is less than another if all of its components are less than the other one. There's one number per node, and every time anything happens at each node, they increment, the one assigned to them. And then when they're gossiped, you just join them and take the max of everything. So kind of the key insight here is that state updates are rare when compared to the number of overall packets. So how I kind of think of it is that this vector clock is ticking like way faster than the actual CRDT is getting updated. And you can think about it in this example, PFC pause frames are only sent once a queue fills up, which is like, these queues are really deep, so it's like sometimes millions of packets. Whereas you can theoretically update your logical clock every packet that you send. So the idea is to use logical clocks to prove that there's been a violation. We'll keep a piece of a timestamp on each piece of state in the CRDT that says when it was last changed. And then I proved a little theorem that says that if a state S has the query be true, so it's a violation at time t1, and the time where that happened has advanced to some greater time, strictly greater time, then, and no data has changed, then there must have been some time between t1 and t2 that there was an error somewhere. Yeah.
Sorry, quick question. Maybe I missed an assumption, but if people are pausing connections, is the possibility of state advancing happening on some other control plane rather than the actual packet data plane?
Oh yeah, so that's me simplifying the example a little bit, but remember it's called PFC, which is priority-based flow control. So what that really means is you pause in increasing priority. So as long as we put our, and the top priority is for like control plane messages, and which is what our thing would be. And then you'd pause like data packets.
I see. So we can get to a strictly greater time because the switch will still be processing higher priority control plane packets.
Yeah.
Even if it's block things.
Yeah.
Got it.
Okay. So this is my final one of these. We have the clock, which is a time of each. This is like the master clock at each server, which is marked here. And then I'll show you the little clocks for each timestamp as they appear. But again, S2 breaks. I've just advanced the clocks a little bit to show, packets are flowing and the clock is moving even when nothing's happening. Once the pause goes, S2, which kind of owns that cell, because it's the only one that can change it, will update, will tag it with its current time. And then S1 will remember that. That'll be part of the gossip when it hears about this pause. And once again, it will end up at S3 as well. And we'll keep doing that for the next two P's in our little matrix. And then finally we get here. So this is a where we were before, which was a false alarm. It looks like an error because this is like an erroring local state, but we can't report it yet because we saw earlier it might be a false positive. So instead we have to wait, and how long we have to wait depends on what these clock values are. So the latest one is this 767, so we just have to wait until 878 or longer, and then we can report it. And so this is sound not complete because you can't have both, but I think it's pretty close to complete given this intuition I told you about earlier, which is that the packets including logical timestamps are flowing like literally orders of magnitude more often than the events in most of these examples. Okay, so again, this is a work in progress, so kind of, oh yeah, go ahead.
Does the logical clock tick on the data packets or the control packets?
It can tick on just everything, yeah. Right now, it just ticks on everything. It'll tick, yeah, on just basically every packet, which is not really that costly. You don't have to gossip it all the time. You don't have to. You can do every 10 packets, every 100 packets, whatever. But the point is it's more frequent than these control plane events. Yeah.
I see.
Is it helpful to gossip when you have nothing to say, or?
It is, yeah, because, for example, in this thing, S3 needs to have heard about at least one more tick at S1 since.
Gotcha. So for the higher level decision protocol you have on top of this, it's important to keep chatting.
Yeah.
You know, once you are in a risky situation, keep saying as much too.
Yeah.
Gotcha.
Which is not bad because, the clocks are tiny compared to an MTU packet. So it's just a little header that I just put in.
Is that right? I mean, there's a lot of computers in a data center.
Yes, that's true, and I have some ideas for that.
Okay.
But they're still not that big because you can do pretty, 8-bit integer or something, and yeah. Again, I mean, I haven't rolled it out to a data center or anything, so maybe, but I think it'll be okay. So I started the implementation in P, so I'm changing the P. Has anybody heard of this P language?
Yeah.
Okay. It's like a model checking thing. So I'm changing the P compiler, I'm adding some stuff to that. And so basically you write a P spec, not a P program, using this crtd-able library. And then the compiler outputs a P program, which turns into a C# program. P is a pretty thin wrapper on C#. I formalized like the semantics of these global and local machines. I have this proof about these logical clocks. And so yeah, it sounded complete if your query is monotone with respect to your data, and it's sound if it's not monotone. And the reason I did P is because it's easy to kind of test out, and basically I have this fraction, which is the number of events per data plane packet, and as long as it's like one order of magnitude bigger, again, the gossiping happens so fast, even for like big cycles, big examples, things hear about it. And another interesting note was that you asked, is it interesting to gossip if you have nothing to say? So usually you would think that it's always like this example where whoever, like for this cycle, somebody in the cycle is pinging that it's an error. But if a lot of the times, it's kind of stochastic, but it's not. It'll be like just some other random node. Think about it, someone that's close to like all three, some middling network node close to all three will be the one that actually does the report. So it's like also a healthy node that has no congestion issues, which is nice as well. This is just some related work. If you have more that's like in this vein. I'm open to changing a lot of things, actually. But there's the CRDT kind of formalisms and stuff that gives you that free like monotonicity, soundness, and completeness. There's like, pick your favorite textbook on vector clocks. There's a lot of stuff in distributed monitoring, but not exactly like this. And then there's like, kind of what inspired me was this like distributed temporal logic paper, which I don't think was super popular, but I thought it was pretty interesting. It was like basically about gossiping partial results of temporal logic queries. And yeah, so I think I'm about done. I have this runtime monitoring. I've argued that runtime monitoring is kind of a crucial thing for modern programmable networks, and that this omniscient global spec is the best and also kind of only way to write them. I mean, if you're writing like local specs, then you have to also prove that your local specs imply global properties. That's what you care about. So that's pretty hard. And you may as well just prove your programs right. And I have this kind of gossiping scheme and vector clock scheme idea, and it's kind of in progress. And yeah, go ahead.
Have you talked to any of the big kind of network operators to see what the systems level constraints on such a solution might actually be? Because I'm kind of curious how much they would be willing to tolerate as far as like packet overhead for control plane packets or for processing overhead, and how much of that could be factored into this kind of design. I mean, I'm certainly willing to believe they're willing to tolerate some, but I'm kind of curious if like how much actual like compute and data transfer you could use in your solution.
Well, I mean, I haven't like interviewed them about this, but I think related to, I'm not gonna go back, but related to the reason that this is kind of needed, which is these programmable networks, they can kind of fix the problem themselves too. So you'd be running this on a NIC, be running this on a programmable NIC. So you're not actually really paying compute on the server at all, which is what they want to sell compute on the servers. That's what they build. So there's a ton of different monitoring solutions that run either on programmable switches or NICs. I know that to be true. And I don't know, I just interned at the Google Network scene.
I was just curious if there was a systems level component to this of like, we need to figure, it wouldn't surprise me if there was some very low limit on how much they were willing to tolerate you using. And so it would be interesting to look at this from how can I verify this within the bounds that are imposed by Microsoft or Amazon or something like this.
Yeah, I have like there's obviously space constraints with this, and I have ideas about like you could do, since you're not complete, you could scale it down and you only do track cycles of length n or something like that. You kind of shrink your data structure to catch the most obvious errors, things like that. But yeah, this example was inspired by this paper where they did essentially this. They keep a big graph of who's paused and who's not at every node, and that was rolled out because they had these deadlocks. So yeah.
In their solution, they just reported telemetry to one central place and literally they can maintain that graph, you're saying?
No, it was a distributed thing. It was kind of similar to this, but it was like, another bespoke thing. And I was like, well, that looks automatable.
Sure,
yeah.
They wrote another program that could also fail.
Yeah.
The program failed too.
Yeah, well.
I get that strategy.
I have a question about the use of CRDTs. My impression is that, first, that you do not require that the updates be applied in the order of associated vector timestamps. And that this is why you need a CRDT, because you might be applying updates out of order. Did you consider applying them in order and not using a CRDT?
I didn't. I'd love to chat about that.
That would be kind of like, so to speak, a conventional approach.
Yeah. I guess my thinking was just that these, again, the clock updates are pretty cheap. And I don't know, time is like, I'm not sure if you would end up detecting it at the same time.
No, because I think, I think you would, because basically once you receive you do have to wait to apply an update till you make sure you don't see any other one that could have happened before. So sometimes you have to delay an update you've already received. But I think that would correspond to your waiting for that T2 anyway.
Yeah.
So it would just, yeah, anyway.
Yeah, I don't love queuing, because you could potentially, like if one thing is broken, you could potentially queue an update for a long time while you wait.
Well, yeah. But again, I'm not sure that it ends up being really different than you're waiting for T2.
Okay, well, I'll look at it, yeah.
You have to think more carefully.
Yeah.
Then you're still keeping track of time because you have to know
Oh, yeah,
how
no.
far.
You need the vector clocks in any case. The question is whether you need the CRDTs.
The CRDT here is basically what you're describing.
Yeah.
Well, no,
It's technically a CRDT, but it's not a very interesting CRDT because of the vector clock.
yeah, no, right. Well, all I'm saying is I don't think you actually need CRDTs if you apply updates in causally consistent order.
You're describing a CRDT.
Okay, if that's how it's implemented internally, but I think in some cases it doesn't need to do that.
Okay, well, I've run over, so,
Okay, sorry.
but please chat with me after. Thank you.
Right, so in this Google Doc that you all have access to, I have made my talk title into a link, and you can click it to get to another Google Doc, which is this one. And from here, there's more links, but these are to, these will open in your browser the different Dusa programs that I'm going to be showing you. I probably actually don't want to open them directly and just talk through them. I'd actually prefer to, at least to start out, just to kind of start with a blank file and write it, interactively so you can follow along. What do I want to say about this before diving in? Not too much. So Dusa is, as many of us have presented on today, a kind of Datalog variant, but it's also aiming at something that for those of you who've interacted with or heard of answer set programming, it's also targeting a kind of similar set of use cases to that. So the idea is you're interested in somehow like enumerating or generating, potentially with some kind of non-determinism or randomness, a large class of solutions to some kind of specification written as a logic program. So I gave a talk with Michael and our collaborator, Arnsenius. You're both directly in my line of sight. And our collaborator, Rob Simmons, who's the main implementer of this system. We gave a talk on our POPL paper about it in January. You can find the paper as one of the links down here. I will check to see if the recorded talks are up and eventually add that as well. That's going to be much more focused on like the theory behind it. But yeah, I thought for this group, I would just kind of dive in to the editor and show you a little bit about how it works so you can follow along and like try your own things and, break it and ask questions and that kind of thing. Sound good?
If you want the recorded talk to be more useful, you might make your web browser bigger or like take up more of the screen.
Big font size, please.
Yeah, so I can do this.
Oh, I meant just like there's a lot of extra background space around your browser.
I will also do this.
That's all. I mean, it's just a nitpick.
No, thank you for the suggestion. Great. Okay. What's on the screen right now? That's fine, but that's not what I want. Okay. So most of you, if you open this up, you'll probably see like a default program, but you can also press this plus button over to the side just to get an empty one. And let's see, I'm gonna pull this over to my other screen so that I can, oh, that's the wrong direction. There we go. Okay, so a theme of what I'm going to talk about today is infinite data structures, right? Datalog notoriously is finite in nature. Solutions only kind of represent finitely much data, but we write down things like lists and trees if we're in a functional language. Those represent infinite data structures. So one thing that I'm actively exploring with Dusa, and this is not by any means the only thing you can do with it, but is kind of one of the cooler things, I think, is generating instances of infinite data structures. So first, I'm just going to throw some Dusa syntax into the editor. So a comment starts with a hash symbol. And let's say we've got a 2-player game of rock, paper, scissors. P1 and P2 are players. And player P can make gets to make a move, which is a choice between rock, paper, and scissors. Okay. So already, right, like this is not vanilla Datalog. So there's a couple of things going on. One of them is the word is, which is a keyword that we use for functional dependencies. So everything to the left of the is the I guess the tuple. I'm also trying to map. I'm not a databases person at all in the least, so I'm trying to kind of map my own way of thinking about things into words that I've been hearing people use today. So let me know if that seems wrong. It probably is. So maps the predicate and its arguments to a value, and those values have to be unique. So when we write these 3 comma separated things, what that means is that actually only one of them is going to be allowed to be chosen. So when we, where did my cursor go? Come on, come back. Yes. So when we do load program, so we actually get 9 different solutions corresponding to the different choices that are being made. So each of these should have the functional dependency property. There's only one value mapped for each player to the move that they choose, but we get all 9 of the solutions generated. Right? So good. So far, so good. Okay. So next, we want to find out who wins. Right? So we say rock defeats paper. Okay. The outcome is certain player wins if they play some better move and defeats move better, move worse, right? Not player, play, right?
You're missing an is. E prime is.
Thank you. Okay. Same 9 solutions, right, okay, so same 9 solutions, some additional information. The cases that don't have an outcome is when something are, well, what are those situations? The ties, right, okay? So typically, you're playing rock, paper, scissors against your friend, you tie, what do you do next? You play again, okay. Let's do that. Okay, so we're gonna have a notion of a round. So outcome R is O, wins P, outcome R is O, means at round O, at round R, outcome is O. Okay. So let's see. Outcome. Okay, So we're going to say 0 is a valid round. And as long as we've got a valid round, we can play. But we will also generate another round. So successor of R, let's say, if we have round R. And in round R, we don't have a winner yet. So that corresponds to the situation where we've got a tie. So that would be play P is M for move, I suppose. And then play P prime is M. Sorry, play, oh yeah, I should just use the concrete terms, P1 and P2 probably. Right, because that's when they make the same move. Okay, so that will, so let's see, who thinks I did this right? I don't know if I think I did this right. We've got an extra premise here that populates this variable, and we'll have one of those for 0, and we'll have more of those as long as the previous round is a tie. Does that look about right?
Each player is still playing once, not once per round.
Yes, thank you. Each player is still playing once. Okay, so let's run this to see something is happening that's not correct.
Well, you keep tying. They're tied once.
You played once, and so yeah, now they're tied forever. Cool. Okay, so that's a fun bug. Okay, so the play at round R for player P is so we've added round now as an argument to play, and we'll have to say round R, and we'll also need to change. Hopefully, the editor highlights that now we're using an inconsistent number of arguments for play. So play RP, play RP prime, play RP1, play RP2. Cool. Okay.
Is there a way to ask without derailing why you don't just negate outcome R as P?
I do not have negation in this language.
That's a good reason.
Yeah. Yeah.
Slows you down.
So, what were you wanting to use it for, though? It was.
Well, I just feel like, so here you stated the tie condition explicitly.
Oh, sure.
Like to me, it feels like, well, look, we're going to do another round if we didn't get that.
Okay, yeah. If you wanted to say outcome R is not something or isn't something, yes. What you have something to say?
Open rules for this.
You could use open rules for this. Okay, Michael, dictate the open rule I should write instead.
Outcome R is question mark tie.
It's tie for round R.
Yeah, R has to be around. Yeah. I think
Yeah.
me, Michael, dictate. I was like, I don't know what I'm doing.
Yeah, really putting you on the spot.
Keep a talk with you, and now this.
Yeah, so then we would replace this with outcome R is tie, yeah. Yes, and this is good because I also, it's slower for some reason, maybe.
I think it's a better program.
I think it's probably a better program, I agree.
Well, because as soon as, this is the same problem that I ran into. As soon as it derives round R, it's entitled to guess whether outcome R might be tie or not. But
That's true.
Wait
That's
until
true.
the players play.
Yeah, so we are still discovering what the right, like evaluation strategies are in this language, because it is also wildly non-deterministic, but we explore things in a somewhat intentional order, but we're still not quite sure what the right order is. So this is like, I think, probably a semantically equivalent program with some different performance. But it also gives me an opportunity to explain what this is question mark thing is, right? So I've said that is a functional dependency, and it can map to a set of things. If I map to something with a logic variable in it, and like implicitly that's like, it's got to be exactly one unification of that as the value. But if I use this is question mark thing, then I'm not committing to making this value be like the value of this attribute. I'm giving it another option for what it can be. And if nothing else happens to get selected to put there, that is in fact something that would be forced, but it's something that's not going to preclude the possibility that something else would get filled in for that value. Okay. So even though this program might be better, I'm going to undo it so that we still have the slightly faster version.
Can I ask a quick question?
Yeah.
Is defeats backwards, or am I not understanding this program?
I am, well, it's all very subjective. I am reading the predicate, the relation defeats as defeats, move one, move two means move one defeats M2. M1 is better than M2, right?
It's exactly backwards.
It's exactly backwards.
It's fine.
Oh.
It's fine. The rest of the program.
We're playing reverse rock, paper.
We're playing reverse rock, paper. Thank you. It was on purpose, and we're playing reverse rock, paper, scissors. Yes. Yeah. Totally forgot how to play rock, paper, scissors. All right. Cool. Yeah. So reverse RPS. Okay. Anything else about that? Like, this is kind of like demo program 1. I don't know. There's much more I want to say. Yes.
Is sort of meant to be a default value or an extension of like.
A what value? Oh, a default value. Yeah.
It's a fallback.
Yeah, the is question mark is I think very sensible to call a default value assignment. Yeah, and that's like kind of semantically that's like the pattern we use it for. I think the most often. Yeah, it's
without a question mark is not a default value.
Right. So yeah, so very, very important difference, right? This keyword with the question mark is distinct from this one without the question mark. Okay. Yes.
So in the outcome open rule, because we can't determine that it's a win, we just eventually go, okay, it's a tie.
Yeah. So these conditions obligate us to conclude that the outcome is a win, right? By contrast, this condition does not force us to conclude the outcome is a tie, but it permits us to. And if we can't conclude anything else about the outcome for that particular round, it will force us to. Yeah.
Multiple is question marks for the same.
Yes.
The same head.
Yes. Yeah.
However, you have multiple possible universes.
Yeah. Then that's kind of that's similar to like let me start a new. File. So like if I say P is like A, comma B, comma C, right, which is just these three solutions. This is, I believe, going to be the same as if I say P is A, P is B, P is C. Yeah. So as a simple example, at least. Yeah. So it gives you more options for what you can put there. If I made all of these closed rules, if I took away the question marks, so I maybe haven't used this terminology explicitly. Question mark means open rule. Lack of question mark means closed rule. So if I turn all of these into closed rules, then there will be no solutions because I cannot, in a functional dependency way, assign something to P. Right. Okay.
So doesn't this mean you have negation?
Yeah.
That's just that programming for you.
So try it. This is an exercise for the reader in code negation.
I mean, if you lift the value with bottom and you say is question mark bottom, is that the same thing in negation?
Yeah.
Yeah.
Some other stuff, right?
Yeah.
Yeah. Yep, that's exactly right. So when I said we don't have negation, that was kind of a lie. And in fact, when you proposed using negation and Ernst said, oh, use an open rule, that's, yes, there's a very close relationship between those things. Yes, so good observation. So yeah, so this is kind of coming from the starting point of like, negation is weird to reason about from a sort of like operational and constructive point of view. Let's just start without it and start with a kind of mutual exclusion as our starting point, as our sort of original source of like contradiction, and then we can encode negation with it. Yes, question?
Is it fair to think of open and closed rules as lower and upper bound bounds, essentially? Or, sorry, upper and lower bounds on the value? If you think of the set of possible values.
So, I don't think so. Like, there is something kind of like intersection-y about closed rules and like union-y about open rules, but I don't quite know how to make that idea formal.
If you take the set of everything you can derive by an open rule and the set of everything you can derive by a closed rule, it seems like the open rules give you a, probably getting this wrong, but upper bound, lower bound on the contents of the set.
Contents, yeah.
Derived by a closed rule gives you an upper bound.
Yeah, maybe. Yeah, I haven't thought about it very hard, but yeah, I think that's,
talk later.
Yeah, okay. Yeah, okay. So, all right, so that's already, we're generating kind of infinite data if you think about like plays of rounds of rock, paper, scissors as infinite data. But we can also talk about things that maybe look a little bit more familiar. So,
Are we seeing something?
no, sorry, I'm flipping back over to my document. Yeah, I'll actually go ahead and just use the link where I don't have time to. Yeah, I wanted to like type everything in, but let me just pull up the list generation code. Okay, so the first reveal is that we've got some kind of built-in data types like numbers, so that we can do kind of handy things. This is actually syntactic sugar. I think somebody else had a system that had this, but basically this is the like, if you have a functional dependency kind of thing, so you have like minus d, minus xy is z is how this would ordinarily be written, but with a functional dependency you can use it like a function. So we can say in place of a specific term what subtracting 1 from d is, and use that in a predicate. Okay, so we're defining some range of valid data, and the idea is we want to generate lists of arbitrary lengths where the elements of those lists are drawn from that data range. Okay. So how does this work? So it follows a kind of encoding trick where what we do is we're going to kind of lazily generate indices into the list, and then for every valid index we have, we're going to pick some data to put there. So we'll start with index 0, and then we will say that plus I1 is an index. Assuming we've chosen to continue at index I, this should look very similar to the round structure we had before. And so then we use a rule, a choice rule, to decide whether we're continuing at index I or not. And so long as we've chosen to continue and D is something in our data range, then we can pick a value to put there. So the at predicate is representing the data at the index I. So everything above like line 15 is the code to generate the like familiar kind of relational definition of the list. And then something else that might be kind of interesting to do is to observe that you can kind of aggregate that data into a nested term that looks a little bit more like the kind of thing that you might see in a functional language. So we can pick out our max index and basically calculate the collected list as prefixes going backwards. So we can say at the max index, the list is nil. And then working backwards, if we've got that there's some data at I and the prefix at position I+1 is the list L, then I can build backwards my list at I to be cons data L. And then pick out specifically the prefix at position 0 is the list that I'm interested in. Okay, so if I run this, it should start generating lists for me, and I can sort of start flipping through some of these and see the like nested Herbrand term that represents the list that I've aggregated, as well as like the actual logic programming representation.
Show Pragma, like class?
No, we could. It shows things in alphabetical orders. There's a lot of, alphabetical, naming things with alphabetical order hacks. Yeah, exactly. Yeah, it's like, oh, everything just starts with the word answer because it's nice and happens to start with the letter A. Yeah, also like this is a web interface. There's a JavaScript API. Well, okay, there should be more APIs than that, but there's at least a JavaScript API. So you can actually do your own, filtering in a general purpose language of your choice. But this is what the browser interface gives you. So that's the list generation, and then perhaps more interesting is to see and maybe to start to think about how to generalize with the idea of tree generation. So do I have? Yeah. Okay. So the kind of straightforward adaptation of that code to binary trees, unfortunately, is going to lead you to a solution that will not be performant, at least in the browser. Basically for reasons that there are no explicit probabilistic semantics in this, but because of how we do selection of rules, you will wind up biasing yourself toward, basically creating a divergent series where you'll choose to continue, you keep propagating more leaf nodes, and then you have a binary choice to stop or continue at each one of those. And so it's more likely that you're going to generate huge trees, right, than smaller ones. So there's a few different ways to tame that, and one of them is with just a maximum depth. So that's I think the solution I chose here, yeah, max depth. But the idea is now we generalize from an index into a list to a path into a tree. So what's a path? Well, the root is a path, and left of any path is a path, and right of any path is a path, so long as we're continuing down that path, right? And I'm just tracking as a third or as a second argument in the path predicate is the depth. Otherwise, it looks pretty similar. So as long as we're under the max depth, then I can choose between yes and no for continue, and I've got to choose no otherwise. And so this is just going to generate the structure of the trees. Do I have the aggregation code in here? I don't think I do. So this is just going to generate the structure of the trees. There's some more code that you can try uncommenting yourself and running to play around with generating the data for each node. And then I think another exercise, given you have the list one to reference, and maybe this is a trivial thing for most of you anyway, is just to write the function that similarly aggregates the tree, the way we aggregated the list. And then, so once we've got trees, now we're pretty close to being able to actually do, we've been talking about wanting to do logic programs, or wanting to write logic programs that analyze syntax for other programming languages. And so here's a generator for untyped lambda calculus terms. Again, I think fixing a max depth is how I got this to be reasonably fast, but just using, reverse de Brown indices, which are kind of a silly representation. But yeah, that's, yes, there's a hint.
This seems like a really fun, quick check kind of thing.
So property-based testing is one of the things that I've been excited about trying to use this for. I have had some collaborative conversations with someone who works in property-based testing, but both of us have been busy doing other things. So yes, I am absolutely, if you have further thoughts on that, I'm definitely interested in them. But yeah, Yeah, I mean, one of the reasons people want to generate lots of examples of infinite data is precisely for property-based testing, and I don't know, I guess also fuzzing compilers maybe sometimes.
Question?
Yes.
So, maybe this is just a misunderstanding of terminology, but you're talking about infinite data here, and what we've so far done seems to be finite data structures with recursive type. So
the data type is infinite, right? As in the type contains, if we think of a type as a set, more or less, contains infinitely many things. Each member of the type is finite, right? If we're talking about inductive types, like co-inductive types contain infinite, like actually infinite data, which is not what I'm trying to do. Yeah, I'm basically just trying to say, like, in some sense, the Dusa program, right? So like each of the solutions in Dusa is kind of the analog of a single solution in a Datalog program, right? And so in that sense, you know, each of those is like just as expressive as a Datalog solution. It can only be finite. But the analogy that I'm trying to kind of shift to is that the solution space of Dusa is a good representation. That there's some formal way I can say that as a representation of an infinite data type. Yeah.
We could use a new type. We could use explicit new types in there to construct co-inductive types.
Explicit, like...
Greatest fixed point new.
Yeah, the databases themselves, the solutions themselves are finite, so there's no...
But a presence of a mu in the result would...
Oh!
I see. I heard mu.
I see. You mean if I were like syntactically represent the... Yeah. Okay. Yeah, like as syntax. Yeah, sure. Okay. Yeah. But was there a... Yeah, sorry, you have a follow-up question? Yeah.
You mentioned something about strategies for sort of... You said scheduling, I forget the word you used, but sort of, it seems like the order in which you choose to instantiate things matters a lot.
Mm-hmm.
The property-based testing thing made me think first of small check rather than quick check.
I don't know about small check.
So small check is like alloy based on the sort of small model hypothesis. Like, you can find out the small thing.
Oh,
so it enumerates exhaustively to some bound. And that seems to be like what a default Datalog style thing is going to do here.
Yeah, so we had a deterministic semantics originally that basically did that. I mean, it's going to diverge in some cases, is the problem.
Sure, no, so you have for any of these things, the stream, like I can imagine the way you would use this is, well, the way people use quick check now is you say, oh, I want to do 1,000 tests, and you instead say, here's my time budget.
Sure, yeah.
And here's a stream of things to run it on, let's go.
Yeah.
And the thing you want to make sure happens is that you're going to generate interesting things.
Yeah.
Some of those are really small and some of those are really big.
Yes.
And so that seems like and so thinking of that, I asked about scheduling and strategies. Because how do you interleave the small stuff and the big stuff so that within your time bound, you see an interesting sampling rather than a bunch of neighbors in space.
Yeah, exactly. Right. So I mean, yeah. So the typical thing is, and I think like with answer set programming, like a lot of these things are actually going to be very, very close to each other. Sort of adjacent in possibility space. And I mean, I think in our case, I'm not running that in the right window. Sorry. Like in our case, if you flip through the solutions, the adjacent things are not all that similar to each other. I mean, this is also like they are. This is max depth of 4, so there's only finitely many to begin with, actually. And you could imagine doing a kind of at the in your host language, gradually increasing the depth if you wanted to explore that in that dimension. But yeah, I mean, but this is actually something we were very intentional about in terms of wanting to build in non-determinism into the semantics and not wanting to run into this problem of like, I've been running this thing for this many iterations and everything that's been generated is the same on this one dimension or something.
Have you thought about how you might express a schedule or a strategy?
I don't exactly know what you mean by scheduler, I guess, but
so you have a bunch of choice rules.
Yeah.
And you have a bunch of I guess it's really fundamentally about the choice rules.
Mm-hmm.
And you get to choose among these choices. And you might have like a couple of different ones. Like you go back, like there was this ordering constraint where you were. It seemed like trying the defaults before you tried. Trying the open rule before you tried.
With the rock paper scissors example.
If you had a bunch of choices, you might choose to explore some of them in certain combinations more than others.
Mm-hmm.
say, okay, look, I want you to pick this and then pick this and then pick this.
Are you suggesting that like the programmer might want to have more control over that, or that there's just strategies for like, yes, was that, yeah. Maybe, yeah, maybe.
A related example, maybe like we sort of know looking at this that we're going to get to R pretty soon, right? Like if we're working on it, it's going to be done pretty soon, then it'll be done. But I can imagine other, some. The thing in my head is that coalesce, but like there might be a thing that wanders off and then eventually comes back.
Yeah.
Pulls us in. How would we know that? Should we try to produce? You can imagine trying to produce all the positive effects before all the closed rules, let them terminate before running any open rules. That almost certainly is defective in different ways. But
another example, if you go from test generation, people will often write generators that are called shots. They'll say, okay, no, I want to, like, you give me a size, I'll generate you a term of that size, more or less.
Right.
And this is one of the ways that you write good generators. You like say, okay, cool, now let me select a bunch of sizes across different ranges.
Yeah.
And so for that, it's like, well, no, don't try any of the, let me pick the size first and then pick everything.
Well, and in a lot of the functional like generator stuff, it is actually, there's sometimes more control than you want, because you are forced to say the order in which you're choosing, like generate the size of the tree, then generate the data, right? And there's in some sense, this is like, one of the nice things is giving the engine a little bit more choice over that, but obviously that's not all, you want the ability to do both, yes.
Can I say some things about this? So
yes,
there's at least one heuristic about what order to make choices in that's in Dusa already, which is deduce then choose. So closed rules with only one conclusion, things where you don't have to write the curly brackets and there's no question mark. Those run first, before any question mark rules and before anything with multiple options.
So these are invertible, right? These are safe to apply.
Yeah, right.
Exactly.
Why wouldn't you run them?
Yep.
Right. And I think I've talked with Rob about, like, could we add other heuristics to this? And like, there's definitely use cases for it. Like, one simple heuristic that makes Sudoku solving, like if you just write a Sudoku solver in this, it will not go super fast. There's one simple heuristic you could add that would make it go fast, which is you have a bunch of different possible choices, resolve the one that has the fewest possible options.
Yeah.
This is like the kind of strategy that
Yeah, totally. Yes, right, and it's like, it's not clear to what extent you want to be able to infer those like in the engine versus let the programmer say, this is the strategy I want.
Imagine waiting too, where it's like, well, don't always choose that with high probability.
Yes, yeah, definitely interested in kind of extending the system that way and collecting more examples of what would be desired there.
I would be interested if anybody has ideas for how you could expose the interface. Like, how does someone write a scheduler that tells a Dusa program how to make its choices?
Right, yeah.
I don't know how to do that.
Generalize that to Datalog. I'd be interested as well.
Well, does Datalog doesn't make choices.
No, but it has choices on the order of application.
That's true.
In the spirit of transparency, I don't want us to miss dinner too far. They're going to start at 7:15.
So okay.
We can wrap up.
All right.
For sure.
Let's wrap up. Let me know if you play around with this. The other things, just to say what I didn't talk about. I've got a 14-line, if you ignore the comments, implementation of bidirectional typing, which I think is kind of slick, that makes use of Dusa features in a kind of fun way. Here's some kind of things that I'm maybe interested in talking about in connection with this. If you like type theory, I think there's an interesting connection with the theory of containers for strictly positive data structures. That's it. Let me know if you play around and want help, like debugging or thinking about Dusa code. Thanks.
Awesome. McSherry talked about differential data flow. At least in our reading group, we've read many of these papers, the timely data flow paper, DBSP, all of that thing. And
I'm sorry.
It's very influential work, that's for sure. And so I'm excited to hear your perspective on it. And I know many folks here are also interested to see how it compares to other approaches that we've talked about. So thank you, Frank, for coming.
Hey, no problem at all. Thanks for having me. I'm going to talk about differential data flow. This is
meant to be an introduction to it, so we're not going to go as deep as we possibly could. I'm more than happy to take some time later on, possibly async to avoid terrorizing everyone else here and go into any of the details that you're interested in. I find a lot of them very interesting, and we'll talk at length. The things I'm not going to talk about here that I think are very cool too, differential Dataflow is built on top of this framework called timely Dataflow, which is much more of a systems-y take on how do we schedule all this work, how do we efficiently implement it, these types of things. Not going to do that. We're going to sort of come at this from the higher level approach of differential Dataflow is an opinionated take on what might you say to a Dataflow execution engine that might be meaningful and valuable and give you some useful results. And it's going to connect, you'll see superficially a little bit with some of the logic programming, though you'll also see probably pretty quickly that it is not a logic programming framework. It's very much a programming framework that causes a computer to do a specific thing, a pretty direct translation from what you're going to type here to what's going to happen. But we can try to bridge that gap a little bit, and given some time, I can also talk a little bit about some of the stuff we've been doing at Materialize that lifts the level of abstraction up to like a properly declarative language that can be optimized and all these things. I'm also going to try to save some time for an interactive demo at the end. It's not very interactive, sorry. I'm going to show you a thing, but it'll be a demo with a guest appearance. Differential Dataflow, great. The tagline, at least at the time these slides are done, expressive framework updates computations when inputs change. And that's the thing we're going to dive into. It's a programming language that's meant to support data that are continually changing. Program doesn't change, not that sort of thing. It's expressive, but not too expressive. We'll see. Feel more than welcome to ask questions as we go along. If you have clarifying questions, something like that, raise your hand or maybe just shout if I'm not looking. But it's meant to be understood, except for some moments they're not meant to be understood. They're just too complicated. And but I'll call them out, and we just put a pin in it and smile at each other and move on. All right, this is me. This is a picture. This is a bunch of interests I have, and this is meant to remind everyone these things all sort of feed into each other, and they're exciting and pleasant. I actually am a theoretician originally. Did a lot of work on matrix math and crud like that, but migrated into big data, and then we have big data. You're like, well, how am I going to work with all this stuff? I don't actually want to do this and then incrementality ends up being a really exciting part of, big data is just too big to actually do stuff with all of it all the time. That's a giant pain in the ass. But these things all inform each other in a way that I found to be very helpful, as they informed my work thinking about the constraints of each of these feeding back into the different challenges and opportunities. So differential Dataflow's goal, it's a narrow goal. It is not to fundamentally change the entire world of computer programming. It evolved out of languages like LINQ and Dryad LINQ, these sort of comprehension-ish, collection-oriented programming languages for manipulating data. And the goal that we had, at least, was give people a collection-oriented language where they describe their logic, what they want to have happen to the data, and then set them up with something that supports the data continually changing. So the work was originally done in the world of big batch computation, Spark and Hadoop and MapReduce and these sorts of things. And streaming was nascent at the time, but it was sort of understood a little bit that we're going to do quite a lot of work to count the number of words in this petabyte of documents. It's going to be real annoying if another megabyte shows up and someone says, what are the counts now? And you had to reread the whole petabyte. That's a waste of everyone's time. So what's the main challenge here, certainly felt by the streaming community, is people, even really smart computer science people, are so much better at programming with static collections of data than they are with programming against live collections of data. Right? If you have to describe what am I going to do with a continually changing object that, if I'm not careful, it's different the second time. What a mess. People get those algorithms wrong completely, but they're relatively good at saying, what would I do if the data were just locked down? You put a petabyte in front of me, or however much data is impressive these days, and told me to go to 10. What would I do? I'll describe that. And then the framework's going to be in charge of making sure that that stays up to date as the data change. So the intended lived experience is you type your program from some domain or collection of records in a domain to some collection of records in some range. However, we'll see how these get written in just a moment. But the intended experience is then, as time progresses, it's as if we had looked at the input for each time, looked at the input at time t, paused the world, froze time, ran your program to completion, produced the corresponding output and showed it to you, and then moved on to the very next second or millisecond or teensy unit of time that obviously we're not going to be able to do if we actually run your program from scratch. So the secret, of course, not a massive secret, hopefully not too surprising to folks here, is that we're not actually going to go and reify your data every single moment in time. We're going to communicate instead in the language of streams of updates. We're going to have change logs, essentially, if you will, that we talk about when we talk about collections of data. We're actually going to think about them as describing what's different, moment by moment, what's actually different in your stream. And we're going to see these a lot throughout, so I want to take a beat to talk through what's in one of these streams. How are we going to think about change logs? How are we going to think about data that are continually changing? And the way that differential Dataflow ends up thinking about these things are as these update triples. And you can change the shape of these how you like, of course, but morally there's some data, which is some people would call it the key associated. This is just the raw data. It's strings, it's pairs of whatevers. This is the collection of data that you are planning on looking at and reasoning about lines of text that you're going to break into words that have counts, stuff like that. There's a time, which is a moment when a change happens. So this is a logical time in the sense that it's not just like what happened, was on your wristwatch when this occurred. So someone said, these changes are supposed to happen at this particular time. We're going to treat them as if that's exactly true. They happen at some particular moment in time. Think of these, if you like, as integers for the moment, like versions of the data as we move forward. They're going to tick, tick, tick along, and we'll explicitly annotate these with specific times. And then diffs on the end, easy to think of these, if you like, as plus or minus 1. Plus 1 means record got added, minus 1 means a record got removed. You want to do an update to a record, you remove the old one, insert the new one, right? Feels a little bad, but we'll get over it. These things all generalize massively. I don't want to get you too stressed about that. We're going to see some of the generalizations as we go along, but some of these can be lattices, some of them are semi-groups, some of them are equivalence relations. We can unpick that async. Yeah?
So you said I should be thinking about the data as like the key. So should I be thinking about the materialized version of the stream as like a map of...
Great. Sorry, a thing that I should have said but didn't say is that how should we think about, okay, someone showed us a bunch of diffs. What is the actual collection at time t? And a great way to think about it, is that we're going to for any time t, we're going to sum up all of the updates that occur at a time less or equal to the query time in mind. We are going to, for each data, accumulate all of the diffs associated with that data. So we'll end up with a map from data to diffs at a particular time by summing up all these updates and accumulating the diff component under the semi-group plus operation, or if these are plus or minus ones, addition. Thank you. No, good point. And it turns out this is pretty cool. Just strictly speaking, there's a bit more stuff that's going on here. This is async, so someone has to tell us, are we really done with the time yet? These you don't get to put arbitrary changes wherever you like, back in the past, stuff like that. But let's not dive too deep into that.
I have kind of a naive question.
Yeah, shoot.
Why is it not just a stream of diffs?
So there's some challenges if I just show you a stream of diffs. For example, let's imagine it's been 5 minutes, I haven't shown you anything recently. Is it up to date? Are you just taking a while to figure out what the diffs are? Some of the operators might produce diffs out of order, for example. So you saw something for time 5. So are we done with 4? Who's going to, how do we get that clarity around what is certainly done versus still developing?
And the data here, is that fully materialized data, or is it like data at that time?
Think of these, sorry, maybe a better way to say this is row or something like that. So we're going to build up a big collection, and these are the individual atoms of that collection. Sorry, yeah. So a row in a database, and there might be a bazillion of these things, or a petazillion, or whatever these. I don't know, but I hope that helps. Sweet.
So then the diff is is an update to that row.
Yeah, just for that row, right? So if you think of this as like the indicator vector for that particular datum, where you slapped a diff into that location, you're going to add up all of these things, and it will tell you what, some of them add up to 0, they're not there anymore, but yeah, just the diff for that particular datum. Other datums may have different diffs.
Right.
Yeah. Great. We're going to do the same thing with the output also. In fact, all of our intermediate collections, when we talk about an internal collection, is we're going to think of this also as a stream of these changes. We're essentially writing down what has happened to the collection over time rather than what the collection currently is. So our goal is actually, we're going to start from a stream of diffs, produce for the user a corresponding stream of output diffs so that you can do whatever you want with this. If you want to accumulate this in place, if you want to maintain a map potentially from data to diff, go for it. If you want to do something else like send a message when you see a diff that says something sketchy, cool, do that. Don't keep the whole collection. Whatever you want to do. This is the sort of the interface we're going to think about developing. Maybe obvious these are the same, so these can be composable too. So if you write a program, someone else writes a program, they're gonna work together and be appropriate. Maybe not obvious, but we're gonna unpack this, is that these times are meant to correlate. So if I do an update at time t, I expect to see the results of that in the output at time t. Right, so this is, you don't get to change the time as the data flows through the system. That's confusing and no one wants that. It's as if we froze the world, reevaluated your program, showed you the actual change at that exact moment. Even though real time will have passed before we get to see that, we write the time into the data itself to make sure that we're actually able to correlate these perfectly. Yeah, shoot.
Properties do you assume of time?
It will end up being a join semi-lattice. And if you have a meet, we can do some nice things about compaction. Yeah, all this, but by the way, all of these assumptions, they end up not being assumptions. Like in Rust, there are constraints. All right, so we end up saying you got a thing that's got a join function. I hope it's a lattice, but basically you're writing some code, and we will call into your join function. We'll use your minimum and your maximum elements to do some logic. So, think lattice for the times. Yeah. And we'll see in a moment why lattice, not just integers. That's going to be the main unlock for differential data flow. Is like, ooh, maybe not integers. And we'll see that in just a few slides there. Soup. All right, we're going to walk through an example or two or three, just sort of developing what this kind of looks like. This is not, before anyone gets too excited, this is not reachability. There is no, Datalog has a big implied fixed point loop around it. We're not doing that yet. We'll do it in just a moment, of course. But no, these programs, think about them as broken into three parts. This isn't the most important thing, but I just would like to be concrete. You start out by naming some of the collections that are going to change. You instantiate them. Usually they start empty. And you follow that with a definition of your program, what you're going to do with these things. You're going to wire them up using some of the operators that the differential data flow provides in a sort of fluent style where you just join, concat, distinct. And what this will end up doing is saying, starting from a set of nodes, use the edges to find folks that can be reached in one step, add the original nodes back in, and then hit it with a distinct operation, implicit in Datalog, but not at all implicit in differential. And you have the set of nodes that can be reached within one step, not exactly at one step, from the set of nodes.
What's the bool supposed to be?
Yeah, I think it was just for formatting, kind of. Good. Okay, look. No, it's the example is going to develop a bit, and there's going to be some state that gets carried along. And you're absolutely right. Reachable or not really doesn't need to have you don't need to tell people true. You can just say hello. But.
So these are like mutable operations? Is that what's happening here?
Mutable operations. What do you mean?
So like what? Like it looks to me, and I'm being stupid, but it looks to me like the result is just produced in the.
Oh, hey, great point. So sorry, absolutely. This is a boring program.
Okay.
It will do this and tell no one.
Okay, fair enough.
And what we often end up doing idiomatically is you have like maybe a probe operator here or an inspect operator that would say, for every record that flows by, do something. Sorry, this is a great point. Yeah, no, this has no effect and could in principle be optimized out. Now it happens to not actually be declarative. This will actually build the data flow and do stuff for you. And mostly what it'll do, to be honest, as a paper writing person, is that it will give me a time I can measure. And printing out lines of text is a waste of time if you want to win foot races against other people. So don't do it. Just have the anyhow. No, you're absolutely right. It's not obvious what this even does. All right, next hunk is the execution, if you will. It's actually a little bit more stuff you need than this, but morally, time will go by. Like you'll tick time forward at your own pace. Sorry, I should have said. For each time, you're welcome to go and do some node insertions. This looks, you're probably all pretty familiar with how this is going to work with something like Datalog. You throw some more facts in, you throw facts into nodes, throw facts into edges. Totally plausible. One of the big unlocks for differential data flow vis-a-vis Datalog and some other logics is that you can also do this. You can arbitrarily remove data with each iteration as well, and it will correctly update all of the information. Now, you may not be particularly excited at the moment because there's no loop, right? And you're like, nice job, to join, great, plus minus. This is gonna work out fine. I can see exactly how you do this. And the cool thing. Oh, I'm sorry. There's several questions. Can I go back a slide and do you ask a question about the easier slide? Nice. Okay, I'm not gonna do it because I broke my.
It doesn't really matter.
Shoot.
When does stuff happen?
Great. So one of the things I left out was there's a moment where you basically tell the runtime, hey, run for a little while. So the insertions queue up changes, sort of buffer them, and at some point you say, runtime, go to town. Like, keep moving until, for example, until the probe they put here has actually ticked forward and gotten itself through time t. Right,
so when you ask the runtime to go, it will do everything that it can do at that time.
The actual interface is it has a scheduling quantum.
I see.
You can either say go until this predicate is true, or go once and then yield and let me do some other stuff. Yeah, Arlen.
So in this interface, since you just told us that we have this triple of the data, the time, and the diff. Insert and remove are providing the diff.
Great. What you all are discovering. So the good news is at the end of the talk, there's an actual example of like real running differential stuff, and you'll see some quirks that one of the things you do here is you tick these things forward. You tell them, hey, we're done with time t. Let's move on to t+1, and they remember, oh cool, t+1. When you modify me now, I'll do things t+1 wise, and reserve the right to do more things at t+1 until you tell me to go to t+2. And that action of moving from t+1 to t+2 or further is actually what unlocks the system. It's the thing that says, oh, I can really get work done at this point, as opposed to just tentatively do work. And you're right, it's not written here. I apologize. This is not a compiling differential data flow example.
But insert and remove are just filling in the diff value for you.
Yeah, that's great. But this is a shorthand for +1, +1 with current time, -1 with current time. There's low-level interfaces that say, no, you tell me everything. You fill in the times, the diffs, all these things. And this is one of these, you lie in your I lie in my presentations in an attempt to try to make things easy. And sometimes the audience loves it, and sometimes they.
I'm good with that. That was what.
Perfect. I promise by the end we'll have a real and possibly too complicated and too real example at the end that's like, oh, that's too bad. Where we'll actually see what do you actually have to do for each of these ticks, essentially. All right. I wiggled the slide around with the dramatic reveal. At the same time, some questions come up. The dramatic reveal is that differential data flow supports the same logic. Any differential data flow program can be nested inside an iterative construct as well. And the iterative construct has the semantics of starting from this collection of data in that collection reach, repeatedly run whatever the logic is here, take the result, and feed it back around again, go through the logic a second time, and repeat indefinitely. So iterate infinitely, essentially till fixed point, but if not fixed point, just keep going. And this is a thing that is meant to be stimulating to people in the audience. Meant to hopefully, except it sounds like several of you have read papers already. That's cool. This stuff is 13 years old at this point, so maybe it's not as dramatic a reveal anymore as it once was. But this is a thing that's surprising to a lot of people working in the Datalog space or other forms of monotogic logic. How do you actually do this without rebuilding everything each time? And the catch here is there's a subtle change in the stream inside the loop, which is that the time coordinate is no longer just an integer time. It's now a pair of time and some other number. In Rust, sorry, this is an unsigned 64-bit integer. Think of it though in this case as a loop counter. So our notion of time is now two-dimensional, which might strike you as a little weird. Not immediately obvious what comes before or after other things, and we'll build that out. But this is the moment. This is the thing to know about differential data flow. In principle, if I told you this, you could spend a very unpleasant number of years figuring out the rest of differential data flow from this. But this is the key moment. We're going to do incremental computation with respect to a partial order rather than a total order. A lot of incremental work, like Annie's presentation about incremental computation, was very much there's a sequence of modifications that you make. And the sequence of is a total order. We're going to think about incremental computation over partial orders. And this is the moment where I get really sad, because like the name for this, it turns out, when you look into who else does integration differentiation from partial orders, this is called Mobius inversion. And Mobius data flow obviously would have been the very best name ever for any data flow system, especially when you see how this works. It very much feels like a problematic loop feeding back on. Anyhow, feel sad to have missed that. But a lot of what we're going to end up unpacking is what does it mean to do incremental computation over partial orders? Why would you do that? Efficiency ends up being the main reason. What does it even mean before we do that? And I'm going to tell you, you already know what it means, turns out. So we talked about it already. It was super easy. Collection at time t is the sum over all of these updates at times less or equal to t. No one asked whether that was a total order when I said that to Max. Doesn't have to be. It's partial order. And we're just going to use this as the core principle that we're going to chase down and say, we want to produce updates that have the property that when you add them up along this partial order, they produce the collection values at each time. You might wonder why partial order, like morally, why partial order? And the answer there is that what we're really trying to describe is dependence and independent structure in our computations. I'll draw some pictures in just a moment, but forcing all these updates to be in a total order, we might run this iterative computation for a while and end somewhere. If we have to restart it with slightly different input, where it starts from doesn't really depend on where it ended from. Like it's forcing things into a straight line introduces a false dependence that we didn't really want in the first place. And the partial order allows us to indicate, no, actually, like in the first round of iteration, only rely on the previous first round of iteration, not the previous second or third or fourth or fifth rounds of iteration. I don't know what the hell those mean. We'll get there with the updated second, third, and fourth and fifth rounds of iteration, but this clues us in that we shouldn't be looking to find the answers to where we're going to go next in where we ended up previously, but where we started. And we like patch up the trace of computation, if you like. Numbers, in the interest of time, I think I won't say too much about them except look, they're smaller. Cool. These are big data systems from yesteryear when everything was written in Java and no one knew how fast things were supposed to go. So they go a lot faster now. Here's a CDF of some update times. So these are relatively large, millions or billion node graphs, and this is a CDF of a single edged update to them. So pick a random edge, throw it away, or something like that. And you get some interesting properties. I think, like a bunch of the changes take about 3 microseconds to go and update, because morally nothing happened. In this reachability program, this edge was not load bearing. This was not the reason someone was reachable. You just have to go and check that, confirm it, update some internal state, and you're good to go. There's quite a lot of folks who do a little bit of something, so 10s to 100 microseconds. Still pretty quick for not revisiting the entire graph and doing the entire however many 100 seconds those previous people did. And occasionally you get some cool things that happen. Like in this case, one time it took about 20 milliseconds because it was a real load bearing, like if you prune an edge right at the beginning of the reachability query that you're doing, a lot changes. You gotta go fix a bunch of stuff. It ends up nice in data parallel, and I'll try to explain why as we go along, but it's just all these operators that we're gonna build are inherently data parallel. So as you shift, for example, from 1 to 2 workers, it goes out to, we accidentally turned on 1,000 workers in Materialize recently. It works, spent a lot of money real quick. So it scales out horizontally quite a lot, but even just looking at 1 to 2, some understandable, predictable things might happen. Like the single update CDF, there's really not a lot of work to do, so things seem to get a little bit slower there, but if you're doing 1,000 updates at a time, things get appreciably faster. That's nice. In actual fact, you can't really see it, but the 2 workers is actually better for the single update case because the 20 milliseconds goes down to 10. And that's actually dominating all of the running time in there. So good things actually happen. Like, you bring work to bear and draw down the tails of these updates. Thinking about how long does it take my computation to refresh is sometimes a slightly different dynamic than how long would it take to do this massive chunky batch work, and you have to make different trade-offs. A lot of this work, for example, is going to be a lot less good on a GPU, for example. You do a lot more pointer chasing, and then you're done, as opposed to grinding through a bunch of the same logic over and over again. You're going to bounce around between kernels all the time and stuff like that. All right, this is, hey, look, if it weren't bool, maybe it could be node. This is now a label propagation algorithm for finding connected components that people use. Rather than just being present or not, this flows forward a node identifier, and nodes collectively maintain and continually update the smallest identifier they've heard about yet. And once this reaches fixed point, you can be sure that 2 people have the same identifier, are in the same connected component, weakly connected component, and folks with different identifiers are not. So this is a description of an algorithm for connected component structure, and the implementation gives you an incrementally maintainable graph connectivity algorithm. It is not remotely close to theoretically optimal or anything like that. In fact, it's quite bad, it turns out, but it's what the community uses. Okay, look, it's better. Same story. It's also basically previous things were bad, and there are some amount better now. The numbers get even better if you talk to real people who do real connectivity on HPC things, but soft targets were easy to sort of poke at. So I'm going to draw some pictures. Is Dataflow everywhere? Dataflow. What you saw was a bunch of methods that transform collections into other collections. What they're really doing is building data flows behind the scenes. So that join concat distinct thing turns into a data flow. The nodes join the edges here. They get concated in, and the distinct operator goes and hits them. Each of the moments, each of these edges on the picture is going to be one of these streams. The data may change. So as we join things, we're possibly producing different types of data in the output than we're in the inputs. The times are not going to change, except for as we enter and exit from iterative scopes, but the times stay put. The diffs are allowed to change, but we start getting to these module monoid sorts of conversations that we can go into if you really like. It's interesting, challenging and sort of cool, but also not how we're going to spend our time. Some of these operators are very easy, like concat, right? Concat, think of it as union all from SQL. So you've got 2 collections, it throws them together. And that's super easy. You just take the diffs, throw them together. It doesn't have to think very hard to do anything, and concat really just wires up some more edges together into an output. Some of them, though, are complicated. Like if you try to think about join, what is join going to do? And it's a bit awkward. Like you might have a change from either input, and arbitrary change on either input could match any record that has ever appeared in the other input. Right? We're supposed to produce the correct answer, and that means we're probably going to have to sit on and keep this data somewhere. And that's basically accurate. Like that I'm aware of, every streaming implementation of join is stateful, is going to sit on some indexed, multi-versioned collection of data that allows it to respond correctly to changes in the inputs. Distinct similarly has to remember what it's already seen. Right? If you see a Frank +1, I don't know, maybe there's already a Frank, in which case we shouldn't, distinct operator should suppress the second one. Maybe there hasn't been a Frank yet, and we should emit a +1. So it's got to remember what it has already seen, or at least what it's already produced as output. Pictures of data, time, and diff, cool. So there's a few points to call out here. I'm not going to go too deep on any of these things, but I want to show you roughly what the data parallelism looks like. These are just 2 workers. This generalizes to lots and lots of workers. But morally, they proceed in what's essentially a SPIMD style thing. They're going to be they each have the same data flow, and we're just going to give them different sets of data. We're going to partition the data where appropriate by key, for example. So the joins align records by key, and if we partition the key space between the workers, and then route the data appropriately, like so. SPIMD, same program, multiple data. So like SIMD, single instruction, single program, multiple data. It's, I don't know, SIMD is often 4 instructions, and SPIMD is, you got a whole program. So these workers are all doing they have exactly the same program, and they just have different queues on which data arrive. And they're gonna respond to the data that they see, and like, as far as they know, that's the whole world. It's a little weird that they're gonna send some data into a queue and not see it at the other end, because it goes to some other worker. Like, if they think too hard, there might be a problem, but if they don't think hard at all, and just pretend they're the only person in the whole world, just works out. Yeah, so no complicated, the only coordination that these folks are gonna have is these shared queues. No locks, no funny business like that. And we're gonna insert these exchange edges at each of these data parallel operators. So join needs to have the data shuffled by key. If it wants to be correct, you need to co-locate updates that have the same key so that the single worker can say, oh, cool, these match. But if 2 keys are different, they don't have to go to the same worker. They might go to the same worker, but they don't have to. Similarly with distinct, for that to be correct, you need to make sure to route all copies of Frank to the same worker for it to correctly determine or not whether it should produce an output. So this is the data parallelism in differential data flow. You might wonder, and this is maybe the load-bearing sequence of slides now. Cool story. What the hell goes on in one of these operators? I sort of get that if you move these data things around and these operators work as advertised, this might work out. You may not be there either, to be totally honest, but actually the locus of complexity is in these operator implementations. Like, how do you get these partially ordered diffs coming in? How do you make sense of those? How do you operate correctly? And we're going to spend just a moment or two going through that. Some nice pictures. Hopefully, we'll see. I like the sequence of slides. You may or may not like them. We'll find out. Right, here's incremental data flow. Like, don't think about differential data flow here. Just think about sequence of changes showing up to an operator. We need to produce a sequence of corresponding outputs. The data show up. I say record comma wait. I don't know why I said, but like think data comma diff or something like that. I think I said wait because like at the very beginning, this is not a diff. This is just the original input. You hit it with your operator. I don't know what your operator is, but you hit it with your operator and you produce an output y. Super easy, right? This is batch computation at the moment. You just do a thing, produce an output. What happens now if someone ships a diff at you? So they say, hello, I'm a change, right? If you just math it out, to be totally honest, you say like, sweet, all right, well, the input added together with the operator applied to it will produce y plus something, or we already shipped a y. What do we have to ship as a diff to get the answer to now be the operator applied to x plus dx? And it's just math. You add x and dx together, you can apply the operator, can subtract y, and you get your answer. This isn't the actual implementation. Like this is a spec, if you will. Like this is what we're supposed to be doing inside this operator. The operators will actually be a fair bit smarter than this, and I'll unpack that in a moment. But it sort of checks out that if someone showed you some diffs on this line, you could figure out how to produce the corresponding next output. And you can repeat this process indefinitely, right? You keep sending things coming in, you keep producing diffs on the other side, and you've got a continually executing incremental data flow that can just run forever. So that's exciting. If you're in the streaming space without loops, this is what you build. Actually, you build a whole bunch of these, you connect them together, and you ship it. And you're good. What y'all might be more familiar with is a different thing that you can do with this. You can take these same widgets, connect them all together, and then put a loop going back around. So this is now semi-naive bottom-up Datalog, which I think I say, yeah. You take some facts, you put some facts to a little bit of data flow that derives some output facts, and you say, oh, new facts, awesome. Let me feed them back around to my input. Sorry, let me hit them with the distinct operator, feed them back around to my input, and then see where we go from there. And those new facts will flow through and potentially produce even more facts, some of which may be novel, some of which may not be novel. We suppress the not novel facts and circulate the novel facts back around and keep going until we run out of diffs, right? Eventually if you're in Datalog, it'll converge, the diffs will run dry, and you're like, I guess we're done. So this is now, same machinery, same parts give you these iterative data flow frameworks, in particular Datalog, as you might all be familiar with. Now, what's awkward is that both incremental data flow and iterative data flow are using the same line to try to do their changes, right? And if you try to do both of these at the same time, things would get complicated and confused, and it'd be a bit of a mess. You'd forget why you were seeing a particular diff, right? So how would we potentially take iterative data flow and extend it to incremental data flow? Well, we can't just stuff more stuff on this line here because super complicated. What we can do, and this just echoes back to the secret that we saw before of the pair, is we can just pick a new dimension to describe things as changing in. Right?
Sorry, I'm not sure why is it such a big deal to just put them all on the same line?
Yeah, so like the classic glitch that you get is you have a Datalog thing that you run, you start with a cool fact, you run it through, and you derive 27 more copies of that fact, right? And now you show up and say, cool, I don't want that fact anymore. That fact was wrong. I will retract one of those facts. And then the Datalog setup will say, sweet, you got 26 other versions of that fact. We're good to go. And you keep it. And you really shouldn't have, because that seed crystal of the fact was the thing that led to the derivation of all these other things. So fixing up the output, or attempting to adjust the output directly, and then continue the derivation may already be sitting on rotten data, essentially, that's wrong and can't be retracted from the output as much as retracted from the input, and then we sort of squeegee through the derivation again and see like, oh yeah, all of those other 26 were no good. We got rid of them too.
Is this not, is this all just irrelevant if you only care about the monotonic case where no retraction ever happens? Like,
so
simplify.
Good point. Yeah, sorry. If the only thing you ever do is add facts, yeah, you just keep throwing facts in. It's fine. Right. Keep going. Keep throwing facts in. There's really no problem. You don't need to get too stressed. But that's not what I promised at the beginning of the talk. Yep. No, absolutely. Yeah. There's, you got to think a little bit. You got to prove something potentially. You got to prove something about confluence, and you got to not have certain non-deterministic choices that might lead you on a different path than you would have had you. Like if we're storing a witness as we go, for example, that witness might change and not be correct if we take facts that should have been there at the very beginning and sprinkle them in only at the very end. All right, so we're just going to dive down in a different direction. We're going to call out, hey, this is we had this Datalog thing that ran, or not Datalog, because that's we know how to handle that, but a different computation that is iterative. We'd like to update it. So what we're going to do, we're going to actually make this be the direction of changes to inputs of the computation. We're going to flesh out changes that are one row offset here to indicate a new round of input data change. Not a new round of iteration, but a new round of input data change. And with that notation, we have the same flexibility in the output. All right, so we can just produce an output that now is vertically offset as well, but corresponds to the change to the input, and we can use exactly the same rule that we used before to say, well, the operator should be applied to x plus that dx, and we should diff y out and produce a new dy down there. And the main thing is just to keep these diffs segregated, keep them separate, because you don't want to confuse the reasons that you experience various changes. And this repeats, and this is, to be honest, this is the moment in the code where things are actually quite terrifying. When you have a little bit of both dimensions at the same time, you gotta make sure you really got your lattice stuff sorted out. But you draw the boxes make it pretty clear. Every time we draw a box, there's one space to fill in. You just solve for that one space. And then you repeat indefinitely. And what we have now is a correction, or an edit, if you will, to the trace of the iterative data flow. So we've described how to diff off of this sequence of diffs. It's like a second derivative, if you like to think of it that way, or multivariate calculus, or I don't know, there's various analogies that aren't very perfect. But yeah, and you can now repeat this indefinitely. So left-right rounds of iteration, and vertical, or going down, is forward progress through time as the input data change. These diffs are kept separate, and it turns out this is just a very economical way of doing the diffing, and that we don't get confused about figuring out how to take this information out of that update over there. And everyone gets, this is the thing that tangles people up when they try to fix or tidy up the results of iteratively derived computation. All right, this is little. I'll get you a picture of this if you want, but this is the moment to a slide. If you're going to take one picture of a slide, that's the essence of differential data flow right there. All right. Oh yeah, okay. So there's yes, Max.
So maybe I'm like over-indexing on the two-dimensionality of time, which you said is a partial order. But from this description, it feels more like lexicographic, in the sense that like in the next time step to iterate, I sort of have to start over. Like I can't, to get to 2, 2, I have to start over. I can't start from like the second iteration of the first time step. I have to start over. I guess like
Yeah.
to get to 2, 2, are there 2 paths or is there 1 path?
So it's a good point. I would just back up just a moment. So lexicographic would, I think, screw everything up because 2, 2, well, 1, 7 comes before 2, 2 lexicographically. But we don't, we want to hold 1, 7 away from, or I want to hold 2, 2, sorry, 1, 7 away from the computation of 2, 2, because that's, the stuff in there comes from a different reason that we haven't quite gotten to yet. It doesn't make any sense based on what we're looking at in 2, 2 or 2, 1 or any of these small things. It is a good question. Why can't you leap immediately to 2, 2? And in some cases you can. Join, if I were to show you join, for example, that's a thing that often leaps directly to a future time. If you have a change at 2, 0 and it joins and meets a thing at 1, 7, for example, that immediately emerges at 2, 7. If you were to just approach 2, 2 without looking at 2, 1 yet, things would be very confusing, potentially. Like all of the stuff that's supposed to happen in the first iteration as a result of that 2, 0 change or the 2, whatever change wouldn't be there yet. If you don't actually have that at hand, it's going to be a bit baffling. And you're like, well, first of all, why am I even here? Like I'm only supposed to continue iteration if something happened in 2, 1 that prompted more work. Like, I don't know, anyway, this is a great example of like, okay, hold on, I have questions, and to be honest, I don't have answers. The math checks out one way, and it may check out other ways too, but yeah. Arlen.
This is just a comment. So when I was struggling my way through this, one of the things that you didn't mention that I think is worth bringing up is that is what the diff is relative to. Right, the diff is relative to like everything that came before it. Right, it's collectively it's if you draw a box around everything that includes the diff, take the one element that you care about, and it's everything else in that box that it's relative to. And that is something that when I was implementing some of these operators that I screwed up a lot. Yeah. And it really messes with my mind.
Is it right that it strikes me based on what I just heard there that like this is in some sense the load-bearing picture of when we're trying to solve for this diff over here, this orange box is how we should narrow our focus. Yeah. And we should really be thinking about to solve for this thing. Maybe nothing even happened out here. We don't, let's pretend we know nothing about that yet. The solution to what should this dy be doesn't care about any of that stuff. We can find the answer to it just by looking at these 4 values and those 3 values.
But critically, it's not just based on the previous time. It's based on the previous time and the previous iteration simultaneously. And so the diff is relative in both of those directions.
Yeah, it is this, hopefully I'm translating correctly. It is this pocket, right? It is not a row or a column. It's just this one little thing. You got to make sure to add this and this. And to be totally honest, the weirdest shit happens here. There can be a non-zero diff here, even if there's a 0 diff here. And that's the bug that usually bites everyone. Everyone gets to experience that once, and then has a very sad weekend where they're not sure that life will work out as well as they hoped. And I'm gonna, in the interest of time, I don't think there's too much, other than those really killer pictures that we all basically I just did like some proof by intimidation here. And we'll have to repair that later over various meals. I'm thinking that what I'd like to do though is bounce out of here. Blah blah times are ordered. There's a few data parallelism. If you're not familiar, hopefully a lot of people already are. Is you can take your operator, slice it by some keys, and it makes all the incrementality very pleasant. Right? When a thing doesn't change, sweet, don't do any work. Not a big surprise. Like if you're going to join some things and someone only has one record with a key, do that work. Don't look at all the keys that didn't have a change. Sort of obvious when you say it out loud, but worth calling out because this is why this is not just a big monolithic operator that has to reform entire collections. It can do this key by key in the worst case. Oh no, sorry. This may or may not be important. But okay, so there's like some nice complicated technical shit going on here about how we actually go and do this. And it speaks a little bit to what you were just saying, Arlen, but it also gets into the compaction mathematics. And this is gonna be, so here's some real proof by intimidation here, which is this stuff grows forever. You're gonna run out of memory. Like you can't just run that indefinitely. I used to understand how to roll things up when there was just one dimension, right? Like that made sense. But now 2 dimensions, what's going on? And you can generalize the compaction, the rolling up compaction that you might have had in your mind for 1 dimension into arbitrary lattices by talking about frontiers, anti-chain frontiers of future times you might see. And there's a bunch of weird ass stuff that you do over here. But not to worry, weird ass stuff always comes with weird ass theorems. So there are 2 theorems. This is a whole proof, by the way. It's not, well, it's not very long. It's also not very clear, but there's a Pareto frontier for proofs, I guess. And so that was the correctness, and there's also an optimality thing that says that this technique basically does exactly what you want to do. You round a bunch of times upwards to be roughly the same, and then you can compact their results together. When they have exactly the same time, you can just add up for every data comma time, add up all the diffs. You don't need to keep them separate. Let me unpack that async if it turns out that this is exciting to people. Because first of all, I'll have to remember how it works. I'll read this out loud to you more or less, and we don't want that right now. All right. I am going to try to bail out of this, except the stupid slide build. Oh yeah, no, here we're great. Data, things are fast. And I'm going to, we're not quite done yet, but I'm going to try to build so I can get to this actual demo of a thing, because it's cute and I want to show off. But there's so much stuff I haven't talked about. And one of the ones, I'll just name check a few things. All of the index state in differential data flow is actually externalized into indexes. So the operators, the reduces, the joins, all these things, they don't actually maintain their own state, with some caveats, but they externalize the state. So if you want to join the same relation multiple times, great. Using the same key multiple times, great. We'll have one in-memory arrangement that maintained index, essentially, that does that. Nice job. In differential, you have to manually program this stuff yourself, and in something like Materialize, we'll see it for you and handle this for you. A really big difference, I want to call it, between the incremental computation that Annie was talking about and what goes on with a lot of these data flow systems is the difference between open and closed loop systems. So in a streaming setting, for example, the rest of the world doesn't stop changing just because you're still working on updating your logic. So you have to deal with the fact that your response time actually affects what volume of changes you're going to see in just a moment. If it takes you a long time to do an update, you're going to see relatively more changes. If your update rules are anything other than linear, you may have a real big problem, because as you get behind, you get further behind, and you have to figure out how to deal with it. So it really focuses attention on robust implementations that are as close to linear as possible and don't accidentally get quadratic, even briefly, because you can just end yourself that way. Yeah, Michael.
Do any back pressure to handle this?
Absolutely not. No, the back pressure, sorry, it's a fair question, but realistically, you can't, there's no back pressure on the real world. So we use instead a technique from a bunch of data plane processing, this run to completion approach that just morally just says, do your work. Start at the front of the data flow, go down and do everything that you possibly can. And that's the back pressure mechanism. That will take some amount of time. And if you get it done quickly, there'll be less waiting for you. So if you've got a million records to update in a second, and you can get them done in half a second, nice. There'll be about 500,000 next time you go and look, and that'll get even faster as you return to it. So the adaptive control theory side of thing is really just this run to completion mechanism. Adjusts the batches of work that you pick up to approach and go on. If you want to pick up less than all of the work because you happen to know that there's some quadratic behavior, cool, absolutely, feel more than welcome. But it's not all I really mean to call it is this is actually a thing to think about now, for sure. Many things are actually groups, semi-groups, modules, stuff like that. I don't want to say anything about it. Mostly, there isn't the time, but I want to name check some cool things about an example. Because I worked on it last night. And you know, I
think Arlen had his hand up. I'm not sure.
Oh no, no, yeah, okay. So here's a differential data flow program that we're going to look at, and the clue is in the name of the file. But we're going to put together a differential data flow computation. Actually runs. I'll show you all the changes. There's some types we're going to go and use. Is this readable largely? Sweet.
You go a step or two down.
Okay, it's going to get wider in just a moment when I unpack some things. I'll have to make it smaller again. But so we're going to use some types. So basically, we're going to represent an AST. We're going to represent an AST using this nice flat representation where we have names for AST nodes. We're going to use U sizes for those. And we've got sort of the node itself, which is going to have an operator name and a list of argument AST node names. And this is just an AST, right? Nothing particularly smart or savvy about it yet. That's fortunate coincidence. It's also the representation that you end up using inside an egraph. And what we're going to do is write a differential data flow program that will take an input that is a collection of this data. So it's concretely a collection of pairs of AST name and AST node, a collection of exogenous equivalences. Right? Someone has just said, I don't know, these two nodes are equal. And we're going to build up an extended equivalence relation that is going to equate all names that belong to the same equivalence classes under congruence closure. So this is the technique that equality saturation uses to extend equivalences of things in an AST. And if you get this out the other end, you're now in a great position to go and do a bunch of simplification and potentially program optimization. This is so basically I read the egg papers like, oh, this is cool, but there's a few idioms I want to call out as we go and do this that might look a bit tortured at first, but hopefully connect some wires in folks' brains. So what are we going to write? We're going to build a data flow that starts from these two inputs and produces some output. And actually, we're going to print it to the screen. Yeah. So what does that end up looking like? And I apologize. This is the moment we realize, like, wow, there's a lot of guff in here. Why do you have to do all this horrible stuff? Like, you got to actually bring collections into scopes explicitly. Why are you doing that? But we're going to do that. Now, our plan here is to start from the AST description, the exogenous equivalences, and develop. It's collapsed at the moment. It's going to expand quite a bit. But we're going to develop a process that's going to be an iterative thing that starts from a trivial equivalence relation that just says, each of these people are their own thing. Awesome. And it's going to develop, using the AST structure and using the exogenous equivalences, a refined equivalence class. Refined, sorry, is the wrong word, but a coarsened, I suppose, equivalence relation that equates more things, and then tell us about it. Now, how many people are actually familiar with egraphs? Like, if I were, okay, not everyone. So I'm neither gonna unpack all of it and tell you all about egraphs right this moment, but I will try to call out a few cool moments. So one of the core things that you do in egg at least, I don't actually know how much of this is actually exactly the same, but as you build up these equivalence relations, you know that two AST nodes are equivalent for some reason. Maybe you got told it exogenously. Maybe you figured it out some other way. You're going to take these AST nodes and say, I don't actually care. Your operator foo applied to bar, baz, crux, let's say. I don't actually care about the bar, baz. Like, those are names. That's cool. I actually want to find out what class they belong to. So in a standard implementation, you go up to your map that says, for each name, what is the class it belongs to? And you rewrite the name with the class, and then you look for things that are the same. Right, and we're going to do exactly the same thing. And the thing that may be non-obvious, may be obvious to everyone, is that the act of looking up in a map, which is what we need to do, is a join. Right, so if we have a relation that a relation that is pairs of node identifier, like actual name and class, a join between a thing that has that name is the way to bring together the looked up value with the rest of the context that you want to go and slot it into. So we're going to destructure this list of arguments into a bunch of node names, the name of the argument, the positional index, first, second, third, whatever. Take that collection, hit it with a join to go and dereference essentially all of those node names and find their equivalence class and then reassemble the resulting thingy-ma-what's-it. And that's this horrible beast here. Again, this is the moment where you're like, wow, declarative programming might have some value. You know, Datalog fits on the screen at least. You know, all we're really saying is exactly that. We're also describing when things match, what is the builder that I use to produce a proper output. And this is the reassembly that's going to go on that says, okay, cool, stitch those back together now. And then we'll stitch the name back on, right? We lost the operator name, it turns out, when we did that. And then it turns out we also lost all nullary operators, like operators that didn't actually have any arguments. They weren't up here. So we got to add them back in. But now what we have is a bunch of, I forget, these are now E nodes, I think. You know, the operator and the list of E classes that they refer to. We're going to use a grouping operator to bring them all together. All folks that have exactly the same E node, bring them together and have all of their names, introduce them all to each other basically. Have all of them elect one person to be the representative. It's going to be the lowest named individual. And that has now done some amount of work towards the congruence closures, or one step, if you will, of that. And to actually make this work out, we got to go and stitch in the exogenous equivalences. So what did we do at this point? Like, we started with this identity equivalence relation, and we did one remapping that did absolutely nothing, except actually at this point, at the end of the first iteration, the data are now in administrative normal form. Like, we found anything that's actually syntactically equivalent now has the same name. So that, you know, that's something. But we're actually going to go and throw in the exogenous equivalences. We're going to, this is meant to be a joke. It's very funny. This is the world's worst way to compute connected components. It's like literally the transitive closure. Not only is it literally transitive closure, it's the nonlinear transitive closure. So this is quartic or something horrible like that. Too bad. Yeah, replace this by something better. That's fine. I got distracted and couldn't remember how to do it correctly, though I think it was just earlier in the talk. But however you want to go and compute the connected component structure, this would be union find in eGraph, but any graph connectivity algorithm will work, and there are better versions than this. And then you're done. That's now the whole loop. That is now an equivalence relation that you then feed back around into and go around through again. And the result you get out at the end is all of your eGraph stuff. And what I won't show you, but I'll throw up and I'll tease, and it's going to feel really good. You remember this fill-in? So we're gonna go and insert stuff like that. We're gonna go and insert a few other things and mark them as equivalent. And actually, story time, like, we'll just do it over here. No, not that one. Wait. All right. So this is the story that Max tells of you know, 8 times 2 over 2. Okay, there's a rule. I've gone and done the E-matching myself, so that is not a thing that this is demonstrating, though in principle that could happen, but with more pain. But I've put in some other rules that I know are meant to match. I've equated them, and you can notice a few things as we go along, like whatever 6 is here. This is the you know, the 6th, I guess 7th actually, thing that we've gone and inserted. I think that's just the 2. The 2 already exists, so we, as it turns out, actually point. No, I'm sorry. This is the A. I apologize. This is the A. It gets mapped to 0, which is the equivalence class for A. In my mind, I had so much time right now to explain all these numbers to you, and it's going to be amazing that that is not true.
Not the end of the world if you take a little bit more time.
Yeah, no, it was going to take a long time to explain these numbers, though. So reading the room, I don't think that's what y'all are looking for right now. But yeah, well, you know, you follow the same. Imagining some oracle has given you the E-matchings and bindings of relevance. You throw in 2 over 2 and 1. You equate those. Nothing too much happens yet. You know, like, there's a little bit of stuff happens here that might be, you know, the 2 over 2 actually already exists, so you have unified. Nothing of substance has actually happened, though. But when we finally go and insert A times 1 and 1 and equate them, we get, these 2 right here. This is a really exciting load-bearing diff. 3, 3 was the root of our expression before. That was A times 2 divided by 2. And it used to be its own thing, right? It used to be like, hey, I'm 3. Cool, you know, no one else is like me. But now we're deleting it, -1, and saying instead 3, 0. 0 is A. So this is the moment where the thing says, hey, you know what? Weirdly, whatever that, a times 2 over 2 is a. And ta-da, hooray, hooray. This has successfully reproduced the easiest thing that we've seen in the eGraph stuff, except, wait, hold on. Sorry, I'm a bad show person. But 2 it's not the number 2, it's a string. So I don't know if you're like, it's a string 2. It's not a number, that might actually evaluate to 0, right? I don't know what 2 means. It's a function. You could run it might turn out and produce 0. This rule is wrong in my, sorry, not in your setup, it's very right there, but in this framework, totally wrong. We should remove that rule. So let's go and delete that. Right, this is now a thing that is challenging in a lot of other frameworks to go and retract an equivalence and get the results that you would have gotten. This wasn't the most recent thing. We're not just rolling back the clock 1 step. This is going back to a previously inserted thing that we let run, finish its derivation. We're going to go and delete the 2 over 2 equals 1, and we get a different set of outcomes that, to be honest, are morally pretty simply like, we undo the a equals a times 2 over 2, but we leave behind some of the other stuff that we figured out as a result. And potentially, if you have a program that might experience arbitrary changes, not just the introduction of additional equivalences, someone's changing the code or something annoying like that, as people want to do, you have the ability to actually update the EQSAT work and get, obviously I've handheld this dramatically. But the theory at this point might be cool. To put words into Max's mouth, at some level eglog is EQSAT alternating with Datalog derivation. You're in a position to do the same sort of thing now if you'd like. We have a little fragment that does EQ, well, at least the equivalence propagation, if not the matching. Can follow that by other productions now, potentially non-monotonic productions, if you didn't want to just use Datalog, and something would happen. And to be totally fair, I don't think anything good would happen. Like one of the nice things about putting EQSAT and Datalog together is they're both monotonic, so you just keep running them in whatever order, and a good thing, you eventually arrive at a thing. There's no reason that would be true if you do equivalence propagation in some other unrelated non-monotonic thing. They might just spiral off into space, who knows. But no, there's these new options now. Like, I mostly wanted to show you what does it look like to take an algorithm and put an algorithm into this framework as opposed to transitive closure or something like that. And lookups basically turn into joins. Coalescing of writes turn into reduces. There's just a lot of translation from existing imperative idioms into, I want to call them declarative. That's not exactly right. I mean, they could become declarative. Certainly not in this context. But sorry about that. But yeah, okay. And now I am done. And I apologize for taking quite as long as I did. And I'm more than happy to take some questions, not too many questions, because there's a next person, and I'm around for a while. So if you just want to grab me and turn me upside down and shake, we can do that async. If you want to do that in front of everyone, I understand. And you can find a forum for that.
I think the next talk was scheduled for 45 minutes, and then Max, we swapped it, so the schedule will actually work if it takes 45 minutes. Okay. So I think you're good for another, let's say, 5 minutes of questions.
Let's definitely, we'll do some questions. I should stop talking though. That's, hopefully we all agree on that. But do folks have questions? Arlen, you have a...
I'll ask the question that I was going to ask earlier. So what is your preferred failure method when you can't keep up with inputs? Like,
oh, yeah.
Yeah, I mean, I know there's not really necessarily a right answer, but you have to address that in practice.
My personal preference, a lot of the internals of the system are designed so that as data builds up, you pivot to more efficient implementation, higher throughput implementations. So for example, like a not uncommon thing is you keep sorted indexes for your data, and if you get a million things you have to go and do, before starting them, sort them by the key. So that as the work builds up, you switch from random access into more sequential access. And you attain the throughput, like the limiting factor ends up being sequential throughput of access to your data as opposed to random access. And absolutely, like once you are receiving data faster than sequential throughput of, I mean, it's not just of one index, you've got a whole bunch of them going on here. So you can fall behind much sooner than just sequential access to one of your indexes, but you make sure to push the limit out as far as you can in this case. And personally, at least, I prefer to fall behind but still produce correct answers as opposed to other folks might say, just drop records or something like that. Things really stop making sense if you start dropping diffs. Doesn't make a lot of sense. There's some other things you could do, though. You could, like, if someone's showing you tick, tick, tick every millisecond, you could say, screw that, we're going to do once a second. Okay, I'm going to compromise on the fidelity, essentially, of the input changes, and skip a period of time by rolling up a bunch of diffs, rounding up, essentially, all of the times to the next integer second, doing that instead, and that's just less fiddly work to do along the way that might get you back on track. But some of this is between you and the user. Some people would be really upset if you rounded up everything to the next second and you missed a really, an intrusion detection bit of logic that would only see a pair of open connections at the same number of milliseconds. You're like, nah, it's good. I looked a little later and they weren't there. Isn't a good answer in an auditing scenario. But might be fine if you're, you just need to get back on track for your fraud application or something like that. So it depends a little bit. Correctness strikes me as being really important. Certainly a lot of work is done here to stay correct. And if you're willing to compromise on that, you probably have better solutions anyhow. Yeah. Actually, Oliver.
So pushing back on the same bit, as you fall behind, your concern was that the algorithm may be superlinear. But is that going to be worse than handling more small batches? Are there scenarios where you can do better by you can process things faster in smaller batches? Because that seems counterintuitive.
Yes. Certainly there are algorithms that people naively implement, and that we at Materialize have implemented, that are effectively quadratic in the number of times that you're trying to retire concurrently. And at some level, the right thing to do is say, hold on. Well, don't try to do them all concurrently then. Go and do them in order. Did you have is there a quick?
I just asked you to define retire. But.
Oh, I'm sorry. Finish or something, yeah. For example, like the most naive implementation of a join in differential data flow is to take all of the updates that you're looking at and literally just join them all. Just do a cross join or join on the key, multiply diffs, and take the lattice join of the updates of the times. And that produces a quadratic number of output diffs you got to figure out what to do with. And it's also a bit of a glitch. You might have a join that's constantly like record in, record out, record in, record out, record in, record out, record in. The results of that join, let's say with itself, are just linear in size. The input's a certain amount of diffs. The output is exactly linear in that size. What's quadratic about this? Nothing. And if you had just gone time out of time, you would see that most of these quadratic diffs that you produce actually annihilate with some other diff somewhere. And you end up with a different implementation that absolutely sort of paces itself. Like local to the join operator, it says, oh, hold on, let's go one time at a time and just do things a bit more carefully to avoid the quadratic behavior.
This smells like instead of doing Fibonacci by doing recursive calls, do it linearly input at a time, rolling up the state.
Yeah, I don't have anything as bad as exponential versus linear, but maybe I'd love to. Like, I think that'd be amazing if there's like, I got an exponential improvement by being smart. Well, in this case, it's more of just quadratic to linear by being smart, which, you would hear about it from me if I did exponential to linear for sure. But so there might be a connection, but it is some amount of think about what you need to accomplish. Take a moment, think about the best way to do it, then do it the best way, as opposed to just blindly run some code. Yeah, Max.
The notion of multidimensional time, and especially with the examples that you gave with nested loops, it makes me wonder if there's a connection to nested loops and like how you might want to schedule those, right? Like, if I'm writing matrix multiplication, right? I might write it in the naive way, but in fact, I want to, invert my loops or, block them, do whatever, right?
Yeah.
And especially with this diff, I mean, it kind of goes along with what folks were just saying, right? Like, are there situations in which you maybe want to progress through time differently, right? If you have a bunch of diffs build up, like you may want to navigate this two-dimensional space in a different way. Like, do you have scheduling primitives?
It's an interesting question. The examples you just used of moments where you could think about scheduling, these are often loops that commute, right? Mm-hmm. And a lot of the loops that we end up talking about here, the only reason that we have nested loops is because they don't commute. There's a non-monotonicity. We need to finish a thing before we start the next thing. And if they did commute, you'd love to actually just flatten them all the way down to just one loop. if you can swing it. Right, so if in the example that Kris had of like, well, what if you're only doing positive additions to Datalog things, do you really need to have 2 dimensions? And you're like, oh, absolutely, in that case, actually, don't even bother with that second loop. That's making things complicated. Your life is absolutely worse with partially ordered time than if you can do the correct thing with totally ordered time. And so if you're in a world where the loops commute, I'd be really tempted to say, ooh, can we flatten them down to just 1? And the only reason that we have these nested ones is that we're kind of stuck with some non-monotone. It's not correct to do that. And as a consequence, our hands are some amount of tied. I mean, they're not totally tied necessarily, but the transformations, at least for me, are not obvious about just reiterating the loops or something like that. Cool, let me stop because this is definitely at /past time now, and we should get the next person up and running.
Fair enough.
Thank you very much.
Thank you so much. Kris.
Yeah.
We have the same name, so, you know.
Special bond.
Yeah, special bond, right. So I was really excited, you know, I reached out to some folks at the Topos Institute, or is it Topos or Topos? How do you pronounce
Topos, yeah.
Okay, fair enough. And, you know, a few folks there working on some stuff that was very related to our interests. So it was so awesome for you to be able to make it out. I'm really happy you were able to make the trip.
I hope I can, what I say connects with, I think there are some connections with what I've been hearing, so excellent. I'll just take it away. This is work in progress, so I actually don't know how long it should take. I guessed 45 minutes, but we'll find out. Cool. So yes, I'm going to talk about incrementalizing queries, specifically in this quite general context of adhesive categories. I'll start with this obligatory slide and never return to it. What's interesting is in this trying to work at the right level of generality where we can talk about something that covers lots of special cases while at the same time is concrete enough that when I say I have an algorithm to do something, it actually can be, without much effort when you're in your specific context, can be turned into something that you can actually compute with. So that's a very delicate needle to thread, and I hope you think that I've accomplished that. And so I will say, actually I won't say what an adhesive category is, I'll show it, and I'll show mainly examples of them. The most important kind of example for me is relational databases, and where the notion of a query that we're going to incrementalize is a conjunctive query. And in particular, because I want to draw these things, I'm going to work in a specific database schema where we have 2 tables and 2 foreign keys. This is just our database instances are just directed multigraphs. So we're going to be working in the category of directed multigraphs. And I'm working on a slightly different problem from what we heard yesterday from Annie about incremental, what is the essence of incremental computation, because the essence, as was presented before, was I have some input that I'm running my query on, and maybe, so I view that as like pattern matches. And then I get some new output, and maybe the input embeds into the output somehow. So I've added some stuff. And now I have my old matches plus my new matches. But I want to say we actually have more data. Often we have more than just this raw extensional difference to work with. More than just knowing that these rows changed or we added these rows, we actually know why they changed. What is the rule that led to changing the input in a certain way? And so we're going to capture that with this notion of a rewrite rule, something that has a pattern and a replacement. And the pattern matches somewhere in the input, and the replacement lives somewhere in the output. So my hope is that this is, in some sense, we have more information to work with. Can we be even more effective than, for example, semi-naive, when we add this to our resources that we know we have at our disposal, the rule that caused the change and how it relates to the change. And that's not so obscure of a problem. I think it's relevant to e-graphs, optimizing with rules in a compiler, the database chase, and also I have a personal interest in these sort of agent-based models where you try to represent the various actions that an agent can take as these rewrite rules, in which case you need to know at any point in time what are all the matches for the patterns of those rules, because the world's changing extremely quickly and you don't want to have to be recomputing this thing from scratch. So in all these cases, there's a notion of a query that we care about, that we want to incrementally update, and more importantly, the changes are coming from this fixed set of rules. And so we always know that when the world changes, it's because of one of these rules that we knew ahead of time statically. So that's the particular informally stated incremental search problem that I'm working on. And I guess we were just talking about a glossary of terminology, so now I'm going to make a sort of mapping into sort of simple category theory terms, how we map these informal things onto them. So the category itself is going to be what I'm going to call like a setting for the problem. So this might be the category of directed multigraphs. It could be e-graphs. It could be term trees that have, ASTs that have these sorts of nodes in them. So in general, you're going to find that you can make a category of these things. And once you do that, we can we can apply all of this theory to it that I'm going to talk about. So first, our notion of a pattern or a query is just an object in this category. And also, a state of the world or a set of facts is also an object in the category. And I think this connects to a repeated theme that we've been seeing, which is that things are just nice when you represent your queries and your facts in the same data structure as the things that you're querying. So a lot of people talked about how you have your AST is the sort of pattern you're looking for, and you're looking for matches in a larger AST representing some program. So objects could be, patterns or states of the world. A pattern match is just a morphism. And in the case of graphs, that would just be a graph homomorphism. And then, so if our patterns are queries, if our queries are objects and our states of the world are objects, then the answer to some query, the answer to some conjunctive query, for example, in relational databases, is just the HOM set from our pattern database into our state of the world, our big database. And now we need a notion of like a rewrite rule, and that itself is also just a morphism. And in particular, if it's only adding things, then if it's a purely additive rewrite rule, then it will just be a monomorphism. And you apply that rule by taking a push out. So the amount of category theory in this talk is actually very modest. It's really just relies on categories and limits and co-limits, in particular just push-outs and pullbacks. So push-outs is going to be this general notion of gluing two things together along a common overlap. So applying the rule, which is adding something in, is just taking a push-out. So to just go over this list in this very concrete example right here, my state of the world is this graph right here. It happens to be small, but we imagine in general they're pretty big. And let's just say our pattern was a path graph of length 2. So we're looking for pairs of edges in sequence. Then the initial answer set to our query for G is the path of length 2 that goes 1, 2, 2, and the other answer is 2, 2, 2. So we start with just these two elements in our HOM set, and then we apply this rule and we update our state of the world from G to H. And H actually has 4 different matches. It has the 2 we already had in G, and furthermore, it has 2 new ones. The ones that we actually care about, the ones we're going to try to find, are 1, 3, 2 and 3, 2, 2. So we want to somehow, that's obviously something we can visually do, and we want to mechanize that. So in the rule is this morphism here that sends an edge to this triangle. And the meaning of this rule then, abstractly, is I'm going to apply this rule to an edge. And when I apply the rule to an edge, I add a parallel path of length 2, and it makes this sort of directed triangle. And then to actually apply the rule, I need a match, which tells me, okay, well, which edge are you going to actually create this triangle for? So in this case, the match goes sends 1, 2 to 1, 2, and that's why you get this result.
Sorry, which rule does does F correspond to? What is the logic program rule?
So the logic program rule is given an edge, introduce another vertex with a edge from the source of your original matched edge and a map from this newly introduced vertex into the target of your matched edge.
This is no longer the transit closure account.
This is, no, yeah, I said I'm never coming back to that, yeah. Yeah, Max.
So is the 3 fresh here? Like, is there, like, there's some sort of existential thing going on. And so would I be free to just keep applying this rule and keep making up new 3?
Yeah. So these are just labels to help me refer to things, but yeah, there's no, it's not a labeled graph, yeah.
I see.
So you're using the HOM set here. Are you assuming that these are locally small categories or that these are enriched categories of some sort?
Yeah. I'm going to assume it's locally small. So yeah, there's actually a set of HOMs. And importantly, because we're doing this on real things, all of the objects are finitely generated. So these are all going to be finite databases. No co-inductive types or streaming, whatever. So yeah.
Is this the logic rule that corresponds to that rewrite rule?
Yeah. It is.
Okay.
Cool, thanks.
That helps some people.
Yeah, and I'll appreciate anyone who can help translate what I'm saying. Cool, so yeah, does anyone, I mean, this is a really important dictionary to just have somewhat at hand as I talk throughout the rest of the talk. So if anyone, if there's something about this that could be clarified, happy to do that now, yeah.
I have a thing I don't understand, but maybe I should.
No, I could hear it and then.
This making sense locally, it totally checks out locally, but though under, I don't know if it's a closed role, like if there's some other edge coming out of it too.
Sorry, edge coming out of what?
Of a 2. So we found a pattern of a 1 going to a 2, and we've dropped in a new thing. And there's a rule for how do you update the answer, but had there been any other edge coming out of the 2?
There is an edge coming out of this too.
Sorry, had there been another, like
7
or something?
Yeah, so if there were 7 edges coming out of here, then there would be 8 matches. Sorry, there would be 14 matches, right? Because I'd have, there'd be a lot actually, because I could have all sorts of ways I could pick. I could send my path 2 and pick any pair of the newly introduced edges. Sorry.
So this could have potentially bound larger than just the 1 and the 2. The fact that we only bound to 1 and 2 wasn't the rule didn't say just bind to these things and then only introduce edges.
Yeah. So yeah, sorry. So maybe the right case to consider is if let's say there was a vertex 4 over here, just because 3 is already taken here, then there would be a new match, which is, so if that were the case, our HOM set XG would have 1, 2, 4, 2, 2, 2, 2, 2, 4, and I think that would be it. And so then we would recover, 3, 2, 4, and 2, 2, 4 as the newly introduced things. Yeah. Cool. All right. There will be plenty of times, and yeah, feel free to interrupt. I want to also just show that it's an example that wasn't graphs. So people have done this trick in almost every talk so far of taking an AST and encoding it relationally. So my database schema would have a table of pluses, a table of times, a table of values, which is just a primary key. And the way I like to visualize these things is where the junctions are the values and these boxes are the operations. And so anyway, this is all to say I could have a rewrite rule, which you could imagine occurring in an egraph-like setting, which says I'm going to match A plus A times C plus B times C, and also a pair also finding A plus B times C. And so this pattern will match any pair of those terms. And then this term here is the exact same thing, except it merges these two together. And it says, oh, actually merge those two E classes. And by applying this rule, I'm going to actually take a step forward in E saturation. So this is not a purely, so before I was saying a purely additive rule is a monomorphism monomorphism. This is not a monomorphism. At the end of the talk, I'll just wave my hands and say, actually, everything I did also applies to not monomorphisms, but it's a little simpler to work with them. So yeah, this is just another example just to further draw the connection that this isn't some sort of, I don't know, obscure esoteric thing, but it actually applies to the sorts of things people have been talking about, to my understanding. But now I'm going to return back to graphs. And now let me return to that thing I said at the beginning, which was how does this connect to like actual algorithms and actual computation in a way that when you say, well, here's my category, what am I going to do to actually incrementalize this? So the first thing to note is that some of these objects are small for practical purposes. This isn't in a formal sense. This is just in practice. The patterns in your rules are small, and the things like G and H are large, the states that you're operating on. And in general, it's really hard to search for all of the HOMs into something really large. In the graph case, this corresponds to the subgraph isomorphism problem. However, there are certain cases where it's actually easy to look for all the morphisms, and that's this so-called rooted subgraph isomorphism problem. So if we're looking for maps from A into something that's potentially really large, if we can initialize certain values for our search, and this is connected, then we can do something that scales with the size of our A, right? So if A is small, B could be really large, and it doesn't matter because we've initialized some values. And then we really can just traverse the local structure of our small pattern to get all the matches, as opposed to having to do anything that scales with B. So this is a linear, quick operation that we can do at runtime, provided that we do have a partial map to sort of kick things off, and we need this sort of property which I call being component-wise connected. It just means there's no connected component of A which is outside the image of this partial map. So I'm not going to say like in every like in graphs I know how to do rooted subgraph isomorphism problem. If you're now working with e-graphs or you're working with term trees of a certain kind, I'm going to presume you can figure out how to do this efficiently, given that I'm going to give you partial maps, which you're going to then have to figure out all the maps A to B that are consistent with that. So that's sort of where the abstract arrows and dots meets like actual algorithms. So I'm going to transform something that looks like find all A's to B's into a series of partial maps from A to B that if you evaluate them, you can efficiently recover the things you need. Yeah, Mike?
Do you have a generic definition of this component-wise connected thing? Because I know what that means in graphs, but...
Yeah. So it means, so I can talk about, I can talk about coproducts. So I can express I can decompose A into, if A equals A1 plus A2, then A1 and A2 are connected components. So yeah, I can say that there doesn't exist a factorization of A such that such as A1 plus A2, such that the pullback of this map with the inclusion of A1 is empty. Does that make sense? So yeah, so there's a sufficiently abstract way to say this, but in the language of graphs, it's nice and easy. You can talk about connected components. But yeah, everything I should say should be applicable in just general adhesive categories. Okay, so let's solve the problem. To do that, I want to first imagine, let's say we have a solution to the problem. We have one of these matches from our pattern we care about into the result of the rewrite, which we said was H. So if we have that, this is where the assumptions of an adhesive category come into play. And all it is codifying this really intuitive notion of how colimits and limits interact. Basically what it says is, if I have a match from my pattern into the result of a rewrite, then that means I could also decompose my pattern in a certain way. I could say, there's the part of my pattern which intersected with G. So H is just gluing together G and R along L. So there's the part of my pattern which overlapped with G, and there's the part of my pattern that overlapped with R. And in an adhesive category, it says that X is no more than just gluing together the part of X that lived over G and the part of X that lived over R over the part of X that lived over L. So if I glue together XG and XR over XL, I get X. So this is something that's like really intuitive, and it's not guaranteed just by an arbitrary category, but any category that is reasonable is going to have this property. At least the kind of reasonable for being something that represents terms with patterns and substitutions. Yeah?
I think I'm picking up what you're putting down here.
Yeah.
But you have some colors, which I think are meaningful to you.
Yes, unfortunately, if I had more time, I would have no color, and then when I do this, then the colors would appear. But the colors, I will say in a second.
Oh, okay.
Yeah. So we can always take, if we had our solution, we get this cube. Every match that we care about corresponds to a cube. Formally, the sides of the cube, these are the 4 sides of the cube, they're all pullbacks, and the top and the bottom of the cube are pushouts. So the question we can ask is, how much of this cube can we compute at compile time? So at runtime, G and H could be anything. They could be really big. It's too hard to anticipate every possible G or H. On the other hand, we know ahead of time what X is, and we know ahead of time what our rules that we're working with are. And honestly, because X is small, the number of possible sub-objects of X is actually something small that we can enumerate. And we can actually consider what are all the possible ways that we can decompose X into some push-out of its sub-objects, ways that you could sort of factor X into 2 pieces.
Sorry, what is X again?
X is our pattern, our query that we care about. This is like a conjunctive query. So.
I thought it's what L and R were the parts of that pattern replacement.
Yeah, so L and R is the rule that we're applying. So these are completely independent things. There's the rule we're applying, which says if I see this edge, I'm allowed to introduce a new thing. X could be anything. It could be I'm looking for cycles. I'm looking of length 4, or I'm looking for friends of friends who are also cousins. That's a general.
So we're maintaining a query X with respect to a rewrite rule. L becomes.
Yeah. That's the general problem. And in general, you could have many different rules that you're simultaneously prepared for. So these could be,
L here is itself a query, right?
L is a query because, in order to actually apply the query, you need to find somewhere in your state of the world where you're going to apply it. So I see something.
XLR, so left and right, or rewrite, left and right side of a rewrite with pattern variables in them. Sorry, X and Y, maybe I should say A, B.
Okay.
Markers are terrible.
Yeah, try to use maybe try to use the black in the future.
Oh, no.
Yeah, this is good.
Yes, excellent.
Okay.
Purely pedagogically, it would be good to use letters that have, or words that convey more variety.
Yeah, so this is left and right of a rule.
Those I can remember, but the X, G.
Yeah, X could have been Q for query. G is usually because this is a graph, and H is the next letter. But yeah, I agree. It's not. Needs some familiarity.
So here, getting intuition. We're decomposing X into XG and XR.
And XL.
To XL.
XL is like, a decomposition of X is expressing X as the pushout of some span of sub-objects. So all 3 of those pieces are needed in order to say like the decomposition of X induced by my map X into H is going to be a whole pushout square.
I thought I was following some story about looking at all the sub-objects, which to me went all the ways of decomposing it into an old thing and a new thing.
Yeah, and
XL is how those overlap or something?
Yeah, well, it needs to be an old thing and a new thing such that if you glue the old thing and the new thing together, you get the pattern that you care about. Just because I introduced 2 vertices doesn't help me get a new path of length 2, for example. Maybe Kris could explain the thing that you were writing?
Well, I mean, just to check that this is the alignment here, right? The rule has some, so maybe one thing I don't understand is there's something I think representing substitutions in your story, right? There's a rewrite rule has some patterns which include variables. We say if A is B's parent, then B is A's child, and that's for all A and B, right? Those are variables.
Yeah, you could think of it in terms of,
Parent of Alice and Bob specifically is a substitution where A is Alice and B is Bob, such that it matches the left-hand side.
So I think the substitution idea you're getting at is the idea of, like, is what you use morphisms to represent.
Yeah, so this match morphism is basically instantiating these abstract vertices as specific vertices.
Yeah, so that's the substitution.
Yeah.
And the concrete graph intuition is like, if my pattern is edges, right? Well, all edges in a graph are morphisms from the graph that just has one edge into that big graph.
Yeah.
Right. So that's how a morphism represents a match.
Yeah.
Cool. Yeah, no, it's very important that I'd rather get through, 10 slides and have us understand it than go off the rails. So this is all to say, when your category is nice and normal enough that whenever I have a map into the result of a rewrite, which is gluing two things together, that also tells me, well, I could have glued my pattern together in a particular way. It induces a way of viewing parts of my pattern as, well, it's the old part, it's the new part, and the overlap part that was both old and new. So we know that the things we care about, which are really just this corner edge, each one of them has a whole cube associated with it. And we're going to use that cube to then actually go the other direction, which is to try to now, so my coloring now, to answer Max's question, black is the things that we could, in principle, compute at compile time and store away somewhere in memory. Red is what we're given at runtime. So we're saying, okay, well, here's your problem. This rewrite just occurred. What are all the new matches? Green are the remaining parts of the cube that we have to figure out ourselves. And so I'll try to be very consistent with those colors throughout all the rest of the figures. Yeah?
You said it would be great to spend as much time listening to yours.
Yeah.
Sorry, you didn't actually say that. But I think the only thing on this cube that I can't figure out how to say in English is xg.
Yeah, this is the part of x which lived, the part of our pattern which was already there before we applied the rule. So taking the pullback of this map and this map is basically just saying, well, what is the subobject of x which lives over g, which is just the...
This is where we diverge on English versus...
Sure. Yeah, I mean, I have an example.
Oh, sorry. Is the...
Yeah, I mean, so there's an example here, which is to say, so our pattern is this path of length 2, and let's say our match is 1, 3, 2.
Wait, so the pattern is the path of length 3.
Sorry, well, 2 edges, yeah.
Oh, sorry. Yes, 2 edges. Okay.
So I'm matching this. So xg would just be 1 and 3, because 1 and 3 in x mapped to 1 and 2, and 1 and 2 already existed before in G. And actually, the entire pattern X lives in the new stuff. And the part that lived also in this over this pattern L was also 1 and 3. And so if you were to glue together XR and XG over XL, you get the pattern back again. In this example, which is maybe also good to think about, the other match, 3, 2, 2. So 3, 2, 2, this whole second, we're saying that the first edge came from the newly introduced edge going down. The second edge was already here. The loop 2, 2 was already there. So our XG is just 2 to 3. And our XR is 1 to 2. So this is new stuff, this is old stuff, and they overlap on vertex 2, this middle vertex.
I'm sorry, why is 2 ever pointing at 3? What am I missing something?
The numbers up top don't correspond to the numbers.
Oh, sorry, yeah. Oh, yeah, I should have said. Okay, so these numbers are just labels, and they're supposed to help us implicitly specify the data of these graph homomorphisms. So if I don't say anything, then that means like 1, 2 goes to 1, 2, or 2, 3 goes to 2, 3. You can't do that forever. So sometimes I'm going to put as like the data of the match saying vertex 1 goes to vertex 3, vertex 2 goes to vertex 2, vertex 3 goes to vertex 3. So this is the function of the labels.
Thinking in substitution world, the labels up top would be variable names.
Yes.
And the arrows would be this variable stands for this.
Yes, and so maybe these should be like XYZ and XY and YZ, and these are the sort of, but I mean, it's important that like syntactically, there is no difference between the things you're operating on in your sort of meta language that you're talking about. I mean, I think that's a cool point. But anyway, so I skipped ahead just because I felt concrete example was needed. We talked about like the top of the cube is just like these three sub-objects, XL, XR, and XG. And so you're picking, this is the full sub-object lattice of X. In general, you could do this in any category, but so this is the sub-object. So I need to pick 3 of these such that if I glue them together, I get X back again. So we saw an example that 1, 2, and 2, 3 were glued together by 2. So this is something that you can just compute at compile time once, forget about it, I've got that. So the algorithm. At compile time, you do enumerate all these decompositions. You also enumerate, because we also know L and R, so we can also consider all the possible back faces of this cube. So that's just looking for maps HL and HR such that you get a pullback square. So this is all stuff that's routine because these are all small and you can do that at compile time. Now, one of these decompositions is bad. We don't like it. It says XG equals X. Now this means that our match, semantically, the meaning of XG is this is the part of your pattern which lived in the old graph. If it is equal to X, then this is bad because we want to solve the incremental problem. We don't care, like any match whose decomposition has this property is not one that we want. And actually it's very important that we skip it also. So we're going to forget about that one. Yeah?
It isn't necessarily true that any decomposition that has this property, XR, I think is what we were calling it, the part that is in the new.
X equals XR?
Right, is going to be trivial?
No, we just saw the example I showed here. XR equals X is.
So XR equals X here, but if XG equals X, is it the case that XR will be trivial? Because if not, then I'm not sure that I buy that XG equals X means that the query is bad.
Yeah. So definitely, I've moved on beyond this story because I'm now working at where I'm not just focusing on monic matches, and certainly when your rules can merge things together, it's very possible to have XG equals X, and because I squashed 2 things together and I got a new match, but yeah, so it's very possible. So yeah, so I think my criterion for something being a bad decomposition, this works, I think, when F is monic.
If F is monic, I think it might.
Yeah.
But I'm not sure it does.
It does. It definitely doesn't. And I have a slide at the end about like the sorts of caveats when F is not monic. But yeah, I'm assuming F is monic for a lot of this talk. Okay, so we ignore the bad decomposition. Now at runtime, I hope it's clear. Well, we have all these cases that we can branch on. So we know what the rule is that we applied. So we can get we can loop over these back faces, and then we can loop over top faces that agree on this edge. And now the question is, how do we actually efficiently get these green things? And luckily, I already told you, if we have a partial map, we can efficiently enumerate the whole HOM set. And we do have a partial map. From XL to XG is our overlap, and then we compose HL and M to go to G. So we can actually efficiently get this and just filter the ones for which this is a pullback square, because every adhesive cube has pullbacks on the sides. And then because the top face is a push out, then actually this green map is just completely determined by mapping out of here and mapping out of here. Don't worry about that. Yeah, so we can actually efficiently start with a partial cube and complete partial cubes. And so if we've covered all the possible partial cubes, then we actually have a clearly correct way of recovering our entire HOM set that we care about, minus the bad stuff that we don't care about, because avoiding this decomposition was precisely what we needed to do to avoid all of the old stuff. And I think I was wondering whether I should try to figure it out, but I think some of the tree toaster stuff we saw yesterday of breaking down cases into breaking down your pattern into possibilities and then making efficient queries for each of those possibilities, I do think it will line up with that, though it'll take a little time to just check the details, make sure we get like the same cases. Yeah, so then I have the sort of, how do we get those 2 new matches? Well, these are the 2 particular partial adhesive cubes that lead you to find the matches. There's a few others, but they don't actually lead to any new matches because, for example, there is no map into one. And if you had a map into one, an edge into one, then you would have found some new matches from that. So I want to say that this is correct. There's also an argument which is to say that this map from XL to XG is always component-wise connected. I would say that's a detail to not stress about right now. Yeah, this is some details. Basically, we're going to assume that our pattern X is connected, and that doesn't really pose any restriction because if X was actually some disjoint union of two things, then you could just incrementally monitor each of the components separately and then use this nice fact, which is that maps out of a coproduct are just equal to pairs of maps out of each of the components.
If I have a rule with a disjunction in the premises, I can turn it into two rules.
Yeah, and a great example of that would be this egraph-like rule where it's like this is well, no, actually this is not, never mind. Almost a disjunction of two things, but yeah, it's actually not that common. Okay, so this was sort of the base case algorithm, and now I see I'm almost at time. There's a lot of things I would want to do. I don't know if I should just fly by them. Also, yeah, I should say, is this actually fast? It depends on what the prefactors are, and some Datalog experiments are incoming, but it remains to be seen. But there's definitely the chance.
What are prefactors?
Like the constant factor. Sorry, yeah. Are the number of cases that you generate to sort of, like we do something very efficient per case that's linear in the size of our pattern, but do we generate so many of those cases that it actually doesn't help you in practice? So that's the sort of empirical fact.
So on the next slide with the shrugging guy.
Yeah.
Is the claim you're making that in principle the algorithms will have for similar incremental updates for these rule rates will have like similar algorithmic performance? Like I don't understand what you're saying.
Oh, I'm saying that, yeah, I think we want to compare to like semi-naive, which doesn't take advantage of this extra information, which is that when you have a change, that you know that change came from the application of a particular rule. So we suspect that there's an algorithmic improvement, but it might just be in practice not actually speed things up. So I'm trying to say that's an empirical question we haven't yet tested.
It did for tree toaster.
It did. Okay, that's a great sign.
Sort of type checking that sentence in the sense that like if there's an algorithmic improvement, I don't know why I need to run experiments to know about it.
I think by algorithmic you mean asymptotic.
Yeah, sorry, asymptotic. Yeah, I meant the. Yeah, so I don't think we need we don't need an experiment to show an asymptotic improvement, but we do need one to show that it's actually practically useful. Like we'd like to connect this to like
Right. No, I have.
Sorry, sorry, I was speaking a bit too casually. Yeah.
I think maybe one of your questions is, do we have an asymptotic improvement?
Yeah.
That's what I wanted to.
Oh, okay.
It seemed like you were making a claim like that, but you didn't. Everything else seemed so formal and this seemed so lax. So
so that gets down to the number of these decompositions that are possible, and I honestly don't know. Like I don't know if I can say that in an abstract sense, like what the order of that is. Like I could do it for graphs in particular.
I think that would for me at least would be.
Okay, yeah. So I've been holding off and actually like trying to work that out just because like it seemed like not the type of question that I could solve in general. But yeah, it would make sense to just do it for an important case.
Generally, have problems that are nobody has a problem in general. People have problems in.
Yeah.
So like I would love to see it for like. Pick an interesting Datalog program. Reachability is.
That's a.
You could probably be more interesting than that. And then I would love to understand this in that framework because I definitely am completely unmoored.
What?
Unmoored.
Unmoored. Okay.
I can't relate this to concrete things that I understand. Is the problem.
Yeah. So I can say. So there's a. So I mean, so this example right here, this decomposition, this choice of like I broke down solving this incrementally. This pattern with respect to this rule f, I broke that down into a bunch of cases, and so we can say like it desugars down to in this case, all I am doing is like so this comes for free. All we're really doing is looking for this. We're looking for
for rooted isomorphisms to that on the graph.
Yeah, we're looking for these. So you and I'm about to show some improvements, which are basically. You might be worried, like computationally, there's a lot of decompositions of X, and I also said like you had to like, we did that extension problem of finding the rooted subgraph isomorphism problem, and then we had to filter those by those which were a pullback because adhesive cubes have pullbacks of their side face. And this optimization, which makes sense when C has a little bit more extra structure that I can talk about, that basically objects have complements. I can say that there's sort of this least object, which if you join it with my sub-object of interest, I recover the whole thing. When I have that, we can actually remove like a large order of magnitude of these decompositions and keep only the ones where XR and XG are complements. In that case, we actually so we filter out a lot of the cases we're looping over. And when we try to enumerate those HG maps, we don't have to filter them at all. So this is very abstract, which is, you're going to unmoor you further.
So the new stuff didn't appear in the prior graph.
The new stuff did not appear in the prior.
Is that what point 1 there says?
Oh, I see. If they have any overlap at all, it's only on their boundary. Like the stuff, like if I introduce an edge, there needs to be from an old vertex, then that old vertex has to sort of live in the new stuff at all. But it's saying you're not allowed to have any extra junk in there. Only the stuff that you literally were forced to have in virtue of.
This is some minimality constraint.
Yeah. So I'm basically trying to make my tops of the cubes as small as possible, and I show that here. So this is my normal adhesive cube, and I'm saying, well, if you have a minimum, if you have like a minimum size one, which would be this outer cube, then this is nice because there's a lot fewer of these minimal adhesive cubes. And furthermore, you don't have to filter these maps. The filtering was to handle some sort of like duplication with the junk, the extra junk. And we're saying there's no extra junk. Sorry. I'm unmooring further.
I mean, do we have an example of, you're talking about some optimization to generate fewer cases. Do we have an example in graphs or in Datalog queries of the extra cases that it lets us get rid of?
Yeah. So, well, sorry, this is not in, there's a Datalog version of this talk. So this is like an XL and XR, which have some extra junk in them, this extra vertex one. This is still in graphs.
That's good enough.
And we're saying, well, I could have factored this into, there's an even smaller decomposition that, sorry, yeah, this is a new reorganization of the various pieces. But so I'm saying I have some sort of,
I'm just trying to get what the pattern, what the query, what the
okay.
right are. And
so I don't show the query. So the query is still the path of length 2. It's not shown on the slide. Okay. We're saying our old stuff is this subgraph. So we're saying what the rewrite rule is doing, whatever the rewrite rule is, it's introducing a new edge. In particular, the new edge that it introduces is going from 2 to 3. And so it might be the case that 1, 2, and 3 live in your pattern, like live over the pattern of the rewrite rule. So the rewrite rule might involve lots of stuff that's not really essential. And essentially the moral of the story is that we could care about whether 1 appeared over L or not, but it's easier if we just ignore, like one wasn't essential. So we can, this is like a smaller, so the push out of these 3 things is X, right? So, but the push out of this is also X with this. So this is like a smaller push out that gets at the same content.
But like, hold on.
Okay.
Okay, the graph here, the old graph is
yes.
Yeah. And then at some point we're adding an edge from 2 to 3.
Yeah,
okay.
not shown.
Our pattern is X is edges of length 2, so 1 goes to 2 goes to 3.
Yeah.
The portion of that pattern that's in the old graph is there's an edge from 1 to 2, but not from 2 to 3.
Yep.
Okay. Why is XL 1, 2, 3?
So it might be the case that your pattern also has 1 in it. So if that's the case, then this pullback includes 1, like the pullback here.
Okay, right.
So if one happened to also be something that was matched, so basically this is saying this is stuff that was old, but there's another distinction of among the old stuff, what was actually matched, and that's kind of like an irrelevant concern, right?
What was actually matched?
Yeah, like when I applied the rule, some subset of the old stuff was actually matched by the rule. That's what's in XL.
When you applied the rewrite rule?
When I applied the rewrite rule, some subset of my old stuff was also matched.
Okay.
And why would you have a different case for like whether or not one was matched or not by the rewrite rule? Like, so that's what this optimization is doing. It's saying, okay, well you can ignore that. Sorry, this was maybe this was a bit too much in the weeds. I did want to. I'm running out of time, so I will have to just gesture at some other things, which is that when we wanted to compare to Datalog, I was all ready to do it, and then I was told, well, Datalog actually operates in batch. Like, it's not one rule at a time. But basically, all the arguments that I've given so far generalize to this case where we're applying many rules at once. So there's, rule F1, yada, 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 rule Fn. You can apply those all in sequence, and you similarly generate a big cube-like thing. And you always, for every match into the result, you get a similar decomposition of this shape. And that's also something that you can efficiently enumerate. And so actually the same algorithm applies whether you have multiple rules at once.
Multiple simultaneous rewrites.
Yeah, so these are all additive, by the way.
Additive?
Like they don't delete anything.
Yeah, okay.
So yeah, is there a question about?
Are you talking about multiple different rules, or are you talking about a rule having many matches to its left-hand side and rewriting multiple?
F1 and Fn could be different rules. They could be the same. It's sort of like a multi-set of the rule set.
Immediate consequence.
Yeah, I think it's got both, right?
Yeah.
But what I'm confused by is you say at compile time enumerate possible decompositions of the above shape, but at compile time I don't know how many matches there are.
Yes, but X is finite. So you can actually, yeah, your pattern is finite. So there's sort of like a maximum number of rules that could add parts of X together, such that you can solve this problem, which was kind of daunting at first, which was like, oh, well, it seems kind of like infinite.
Okay.
And so there's an example here where I have two different, triangle ADDIE rules to my initial graph, which looks like this. And we're going to find a match which sort of goes down one of the triangles and up one of the other triangles. And one of the decompositions is able to sort of recover that in this way. Yeah, I guess there's stuff to say about like what if the match is not monic. Merging is another way of introducing new matches, and everything I said also applies to that, with some caveats of what it means for what it means for a decomposition to be trivial is now, I can't say it in 3 characters, and what this sort of optimization condition to sort of like get minimal decompositions is also a little different and harder to state, but it exists. There's also a notion of deletion, so not purely additive, that I guess I don't have time to say. So yeah, in conclusion, I'm sorry I did not give Datalog examples, yeah, we're working at this level of generality that I think is specific enough to be instantiated. So yeah, we could work out for Datalog queries or for eGraphs what this turns into. Abstractly what we're doing is we're transforming subgraph isomorphism-like problems into rooted subgraph isomorphism-like problems. I think conceptually important that we're trying to leverage information beyond the extensional difference of an update. And we have lots of ways to generalize the sort of basic naive algorithm. Yeah, there's implementation of this for relational databases that I've worked on, but it would be easier to compare apples to apples by doing this in an actual Datalog engine. So that's really the next step. Thank you.
Thanks for coming to the last session, everyone. Hopefully there was an eventful hike and everyone enjoyed the break. So the first person in the last session of the day is Sowmith, who's a Tom student at Washington State. And he's been working for a while on GPU Datalog related work. Recently, he's been working on doing batching for large joins that might spill outside of let's say a single GPU if you try to do them all at once. And that's what he's going to be discussing today. So this is a work in progress, and I'm eager to see what he's got going on. So good luck, Sowmith, and thanks for coming out.
Thank you, Kris, for the introduction. I'm Sowmith, Tom's student. I'm repeating stuff. But so in this talk, I just the main goal of the talk is to introduce the GPU work that the lab has already done and published, which is three papers, I think, this year, which has been over the few years of work that has been published. So the point of presentation is to just introduce those GPU implementations and motivate how we can improve the existing state of the art, which is our existing GPU implementations. So the motivation. So we want fast and efficient execution of recursive queries on the GPU. So there are two parts to this, I think. First is the recursive queries part. I think I don't need to explain why we need those. But the GPU part comes from if the need for throughput. If you have, the GPUs are very good at throughput that CPUs just cannot beat because of the hardware. So that is the GPU part of it. What does this enable us to do is larger and larger program analysis, graph analytics queries, ideally knowledge graphs and ontological reasoning. So what I'll start with is a 2-minute primer to GPU on CUDA programming. I'll start with the 2-minute primer to GPU on CUDA programming so that there is some context of what I'm talking about. So in a GPU, I'm only referring to NVIDIA GPUs. I do like AMD, but it is what it is. So in a GPU, you'll have a bunch of execution units called streaming multiprocessors. This is like your super core or whatever. So each super core or streaming multiprocessor has a bunch of smaller CUDA cores. So this SM is basically a holder of other resources that are not related to compute. So in a CPU core, you will have every CPU core will have your scheduler, will have your cache, and some more other things that are not actually compute. Whereas in GPUs, they group a bunch of CUDA cores together which just do compute, have no idea where the instructions are coming from, where the program counter is. And that infrastructure is shared among a bunch of CUDA cores, and that grouping is called a streaming multiprocessor. This is a bit important to know just to understand how the scheduler affects and where the performance is lost rather than most, yeah. So I heard SPMD today, single program multiple data. I heard SIMD today, single instruction multiple data. This is SIMT, single instruction multiple threads. So which is basically it more or less means that you can be blind to the fact that there are multiple threads executing the same instructions on multiple data, and you can write your nice scalar code, and the execution unit will take care of moving it to and turning your masks on and off, enabling the threads, disabling the threads, and the whole shebang that has to happen for SIMD execution. So this on the GPU looks as such. So I was talking about SM resources, the supercores resources that acts as the SIMD front end, let's assume. And the backend would be CUDA cores, like the actual execution units that y'all are probably familiar with, like having a bunch of lanes, taking in data, enabling the whole thing. Yeah. So this is single instruction multithread on the GPU. Before I explain why are we even looking at this, is GPUs have a lot of throughput to gain. Like if you have a very regular workload that you can put on the GPU, the throughput you're going to get is just unmatchable any other place. So, but you have to be really intensely aware of where the performance is lost in terms of like possible throughput. So let's look at a simple program which has a bunch of branches, which is very bad to be in GPU code. It's also called divergence, thread divergence. So if you have a, let's 5 steps in a program, 5 levels, and assume that each CUDA core has 4 threads or 4 lanes, however it makes sense. So the first instruction gets run on all 4 lanes, which is good. And the second instruction, because the programmer is not aware that whoever it is writing code for multiple lanes, you can write code just in terms of like very scalarly. And now when you come to B, one of the thread is turned off. So what the scheduler has to do is enable the first 3 threads and basically sequentialize B and F. So B and F has to be sequentialized. So whenever you have divergence, you lose a lot of parallelism and all the divergence becomes sequential. So that is a very important fact to keep in mind. Branch divergence, thread divergence, and memory divergence bad. So this is also the only difference from the CPU caches and GPU memories would be there is an additional component called shared memory, which is like addressable cache. That is one thing to keep in mind. All right.
Sorry, can you go back? You called it shared memory, but I don't see the sharing.
SMEM. So the super core has a bunch of shared memory, which is shared between all the CUDA cores that are being run on it.
I see. So for the CUDA cores.
Yeah, and the VRAM acts as the global sharing. Yeah. So the program analysis, yesterday's Slog talk addressed some of that. So we'll primarily look at graph analytics queries for this. Yeah. So the question is, what do we need for graph analytics queries to run? We need, like say, for engine to be called a graph analytics engine, what does it need to be able to run? So this gap benchmark suit says these are like the minimum requirement queries that they want your engine to be able to run to be called a graph analytics engine. Transitive closure, the mandatory query that everybody has to mention, connected components, single shortest path, triangles, and page rank. Page rank is a little more complicated, but yeah, and more. So what do we need to execute these queries? We need joins, projections, filters, fixed point iterations, and aggregations. More or less relational, but yeah. So we'll only look at joins and fixed point iterations. That is because when I say joins, it's join plus projection and or filter, and also they're not very interesting to talk about much. So, and the second one is fixed point iterations, which is the more important and interesting part. I'm not super. I haven't worked on aggregations much, so I'll skip that part as well. Yeah. So we're going to look at joins and fixed point iterations. So before we talk about joins, like I'll not call them joins, I'll call them many-to-many joins to be specific. And how are they different from any join that is out there? So most OLAP benchmarks like SSB, TPCH, JCC, TPDS, they all have what are called primary key, foreign key joins. So let's come to that. But what makes a join a many-to-many join? You should have duplicates in both probe and build tables. That is what makes a join many-to-many join. And why are these interesting, or like why are these any more difficult or different from PK-to-FK joins is, yeah, I said more like when I say PK-to-FK join, I mean primary key to foreign key joins, and they are one-to-many or many-to-one joins, and their size is bounded by whatever is the larger relation. So if you have two relations that you're joining, the size of that join is bounded by the cardinality of either probe or the build, whichever is larger. Yeah.
What do you mean the size of the join? Not the size of the output, do you?
Yeah, size of the output, yes. Because when you're joining a foreign key table, which is a foreign key table with a primary key table, each foreign key can only match with one primary key.
Oh, sorry. I thought you were talking about many-to-many joins.
No. I'm only talking about PK-to-FK joins. So yes, that is the bound of the size for PK-to-FK joins. And yeah. Well, why is this important for us is, many-to-many joins are not really worked on in the DB community just because the benchmarks don't want, the benchmarks don't deal with them. So a lot of research that is done for OLAP GPU is done for one-to-many, many-to-one joins, which have a nice bound on their size, and they are not many-to-many joins. So that is an interesting part of what we are working on, what we are all working on. So what is this many-to-many thing? What is happening here? So if you have a little fish-looking graph like this, and you have let's say, you have a node 4. So what is the incoming degree of 4 is 2? The outgoing degree of 4 is 2. So if I wanted to, if I did a self-join on this graph, what I'd get is all the 2 length paths. So let's count the paths and see what is happening here. So if I wanted to get the 2 length paths, and let's only look at the 4, I'll get 3, 4, 5, 3, 4, 6, 2, 4, 5. If I add another outgoing edge from 4, now what happens to the number of outputs? So it becomes 2 into 2, it becomes 2 into 3. If I add an edge here that is incoming, it becomes 3 into 2. So it's a multiplication. It's not a PK-to-FK join, and the size of the output you get depends basically is it's different from OLAP joins is all I want to say. Yeah, so duplicates lead to problems with join size and skew. Join sizes blow up, and what this means is all the OLAP GPU join research that is out there, which relies on the fact of it being a PK-FK join, goes out of the window. You have to start more or less from the scratch because, yeah. So this is the state of the art for GPU joins, for PK-FK OLAP joins called Crystal. It relies on the fact of the joins it is doing PK-to-FK to optimize. The whole paper is dependent on that fact. And that is all. So this is another paper which improves on Crystal, still relying on the PK-to-FK join. So I found this one paper which is published this year, which has a micro benchmark for many-to-many joins on the GPU. It's not addressed, and the benchmark, the comparison point they use is cuDF, which is NVIDIA's data frame library that is put out, and they compare it to cuDF for their many-to-many joins. So those are many-to-many joins. I'm just giving vocab so that we understand why the joins are harder for us than whatever the DB OLAP people are doing. So this, let's look at the join, how the join looks. I think we talked about this. So you get 4 tuples, it being 2 into 2, and this is how the edges look after the first iteration. And yeah. So the two problems is I don't have a bound on my size, and there is skew. There is always skew. There is too much skew. Those are the two problems, and these joins are again very different from OLAP benchmarks. So what do you need ideally for many-to-many joins? Ideally, I'd want to know the size of the join early so that I can do my nice buffer allocation and happily write to it. And the second one is I'd want less skew. Like somehow I want to avoid the skew and not have each thread doing a lot of work I'd want to be able to distribute that well. Those are the two things I need to do many-to-many joins well on the GPU. Then there is the question of n-way many-to-many joins, which are absolutely should not be done using binary join chains and should be done using worst-case optimal joins because they are better. But the problem of size and skew don't go away by using worst-case optimal joins. You're going to get better performance for sure, but the problem of having to know the size ahead and having a bunch of skew does not go away because you're using worst-case optimal join. Because these are execution characteristics, not characteristics of the physical operator. So the second thing, so the first thing we looked at is many-to-many joins, and the second thing we'll look at is fixed point iterations. Well, so I have to do this. I was told this is mandatory for in every Datalog presentation. So there you go. So I don't want to explain it. Yeah. So let's go back to a simple example. And so we have this nice graph. We wrote a little edge list out. And I'll just skip through the slides. It's basically like a visualization of how the TC is going to work. So I'll discover all my 2-hop paths. I'll discover in the next iteration all my 3-hop paths and then the largest one, and then I'll do another iteration to realize, oh, I've reached a fixed point and then stop. So this is my TC on the little graph I've got. So in terms of joins, how does this look? So what I want to do in this slide is to basically explain how the join works on the GPU and how it is different from whatever you can do on the CPU and whatever Souffle is doing. So Souffle or any other B-tree based join is doing. Not maybe any other, just Souffle.
The ones we know about.
The ones we know about, yes. So if you're joining these two columns, which is basically a self-join, the thing I notice first is if I'm doing this through a hash join, I'm matching this one with this range of tuples, this 1 and 1. Now this is a problem if you do a straightforward hash join because you have duplicates in your build table. That just means like you're going to probe longer and longer distances if you're doing a linear probing scheme. So that is one thing I notice here. And the second thing I notice is my path new, the join I generated has duplicates. And that is because so in Souffle, you would get your join tuple out. So you're taking each tuple, running it through the query tree. You get to tuple out, you try to insert into the B tree full, and it tells you, hey, I got this tuple already. Then you throw it away. If not, you also insert it into delta. So the two things happening there. One is deduplication. The other one is merging. They're all happening in the same step, which is a find and insert on the B tree. Whereas in the GPU, because we don't like thread divergence at all, we want our kernels to be simple and linear. What we do is we just generate all the output that is coming out and write it to a big buffer. We don't mind if it's duplicated or anything. So I'll call them intra-iteration duplicates. So that is another thing I noticed. Yeah. So now let's say I deduplicated them and then I get the new edges I discovered, which I'll call path delta or my frontier that I'm going to move forward. So
do you do the deduplication on the CPU then?
No. So we do the deduplication as a separate step after the tuples are generated. Yeah, that is the only difference. Like we still do everything on the GPU, just not as one complex step, but as smaller kernels that are separate. So yeah, this is a reminder. I have to mention thread divergence. I'll come to it again. So in this path delta again, I see duplicates that have to be thrown away. The way we do this is we just sort it. We just sort it and do a unique. So we do a thrust sort, which is the library that NVIDIA wants you to use, and you should. We do a thrust sort and do a thrust unique. So we get rid of our duplicates. And the next step is to merge take this nice delta that is unique and merge it into full. So there are again two steps happening here. I'm deduplicating my delta against the full path. I'm also merging it.
I assume you're also deduplicating in when you're doing the insertion.
Yes.
Is there a benefit to doing that as two different deduplication steps?
I'm not exactly sure if there is a benefit. I believe there is, because if you have a lot of intra-iteration duplicates, oh yeah, there is, because I have to, let's see. I'm not completely sure about the detail there. Yeah. Yeah, I'm not completely sure about the detail. Yeah. So how do we merge? So our full is expected to be sorted. Our delta is expected to be sorted. So we calculate the size of the big new buffer that has to be allocated, and then just write them with a merge, sorted merge. So that is what is happening on the GPU. So we have a merge, we have a deduplicate. The two things that we'd have to do if we want to do recursive queries. Join and merge, join and merge. Yeah, so what are the challenges or the things you would have to do to get to fixed pointers? Efficient deduplication and merge. To revise, the challenges with many-to-many joins are the size blob or the size blob, the skew, and the challenges on GPU with fixed point iterations is the deduplication and the merge. So these are the papers / engines that do Datalog on the GPU that are published. So GDlog, VFlog, and MNMG join. I'm not going to talk about them each individually because the general theme or the general insight that they all follow is very similar to each other. Just the methods change some. So what is the point? Like, we have some challenges we want to do. They all follow the same approach. So what is it? How are you supporting these operations efficiently on the GPU? If you remember, I was talking about how this one, when being joined with this, I need a range of tuples I need to join with. So you need a way to do efficient range querying. So many-to-many join can be looked at as a one to a range join to think about. Like, so each probe tuple gets a range of tuples it has to join with. And then there is the parallel insertion that you need. I think Tom or Kris mentioned a stat about how Souffle spends 70% of the time in insertion or something. Yeah, so we don't want that. We want truly parallel insertion without any issues. We want efficient deduplication. We already talked about how we sort and merge. So this is the data structure that the two of the three engines use, which is a unique hash map sitting on a sorted array, sitting on data array that is not sorted. So what this unique hash map gives me is, I've removed duplicates from my build hash table, is what has happened here. Then I'm able to do range queries by saying, hey, give me all the tuples that are 1. So I go here, follow the path down. Now I have these two tuples that I can basically join on, take as a range and use for the join. That is the first operation. And the second operation comes from having a sorted array, which supports our deduplication and merge. Mm-hmm.
So the hash map and the sorted array sort of have the obvious properties about them. The data array here, I guess, like, why is the data there? Are we sort of trying to not touch that as much as possible, sort of take that as a given? Like, what's the motivation behind having this additional layer of indirection?
So the additional layer of indirection is required because sorting data, if you have more columns, this was made for a row-based engine. So sorting data, the actual data in the VRAM is costly, the first thing. And the second thing is, whenever you materialize the delta, you always have a sorted array on top that you're merging. The data is still separate. It just has pointers into the sorted array, so that I am not moving a bunch of delta data that is generated every time into a bigger buffer.
Okay, so I think this is what I was getting at. Is
Mm-hmm.
Are these data arrays intended to be, I guess, like immutable or like append only, whereas the other things are sort of you're changing as you're updating your data?
Yes.
So just to double check, each of those arrows we should view as an indirection.
Yes. It's a pointer into the data array, wherever the data array is. Yeah, so example again. This again, I think I've explained it. Oh, I see. Datalog. So these are just numbers. These are good numbers. These are good numbers that, again, I'm doing the mandatory thing, dunk on souffle. So we do 10 to 20x better than souffle. This I'm showing the reachability query, and this is the other engine that is eHar's work. This is different from the first one. This uses columnar layout and has a hiss on every column that is there. And the interesting thing about this is not just a GPU thing. The same exact layout, because we use the Thrust libraries, and Thrust has a CPU mode to do all the algorithms we'd want. VFlog switch gives you a switch and says, hey, where do you want me to run this? So when you select CPU, it's still the state of the art, even on CPU and GPU. That is very interesting. Yeah.
When you run your system on CPU, is it multi-threaded?
Yes.
Okay.
Yes.
And
So,
also, I assume SIMD or something?
yeah, I think whatever the Thrust library gives us, we are all that. If the
Sure, I asked what is Thrust doing?
Thrust is written such that you would get, so they have two execution policies. One is obviously the CUDA, and the second one is, I think it relies on Intel TBB to do their parallel CPU work. So they have some,
Yeah, they're optimizing it pretty well.
Yeah. Oh yeah. So the third engine, which is the MNMG multi-node multi-GPU engine, what it did for its requirements is broke HISA down into principles. So it said, hey, I need a sorted array, I need a hash table. Because it wanted to break it, partition its hash table, I think a decision was made, hey, I'm going to have a different hash join and a separate sorted array, not just layered on top. And for that work, they got performance.
I'm curious, so I'm trying to understand if I'm taking away the right thing. The insight about the hash indirection is that with that hash table, since you have the unique join keys, now you're basically turning this many-to-many join into a
one to a range join. Yes.
Okay.
There is still a problem with that we'll get to, but it's a one to range join now.
Is the one to range meaning?
Yeah, one to range. Yeah. So when I have a one, the key one that I have to join, I'll come here, go down. Now I have two tuples that I have to join with.
Right, but you can do that symbolically. Then you can do it, or you've got two unique hash maps, and you're joining those together.
My probe relation does not have a hash map, or I don't use the probe relations hash map. It's still very much a hash join.
So you generate sort of for each match, you're matching it to one range.
Yep.
And then you expand the range.
Yes.
That's neat.
Yes. So I'm going to name the join. So once again, what the challenges we had with many-to-many joins is to size, blob, and skew. Challenges with GPU, challenge on GPU with fixed point iterations is reduplication and merge. I think HISA does a good job, so we're not going to look at them too hard. So size and skew, what is happening there? So how are we solving the size problem? If you don't know the size, well, what do you do? So the simplest thing is to do the join first, count all the tuples you need to materialize, and then do the join again and actually materialize. And it works out very well. So we have a 3-step join, which is to probe count. You count all the tuples that can be generated in the join. You do a prefix sum to calculate the offsets into the array that you have to write to, and then you do the probe rate. Yeah, I explained. All right, I think let's consider all that also. Let's go to skew. Sorry.
Maybe I misunderstood something here, but are you just doing the join twice?
Yes.
Okay. So I mean, you're literally just doing an aggregate count one time, and you're just doing the join again later.
Yeah.
Okay.
You should try it.
It's
great.
Okay.
HPC does the same thing for sorting an array. You figure out how big the target thing needs to be, and then you
look. It makes sense.
It turns out malloc actually hurts.
Yeah.
I think the problem really is to avoid dynamic allocations.
Right, yeah, the dynamic allocation kills you.
Yeah, and the OLAP people do it because they have a bound on the size of the join. They can go, hey, this is the size of the buffer, all I need, and then basically do what is called a local resolution and global propagation, which is every few warps group together and say, hey, these are the offsets we want to write to, and then make one call out with an atomic add to figure out. But because we don't know how big the buffer has to be, we can't do just larger and larger allocations. We have to figure out the size to be able to do it.
Is it just the allocations, or so like with the blanking on what the HPC sort is, but you also don't have to deal with contention on the target space.
The contention is more or less dealt with by this technique called local resolution and global propagation.
Oh, right, so you know exactly what
yes,
writing each results to.
But the problem is, like the OLAP people just materialize because it's either a present or an absent. If you're joining with a foreign key to a primary key, you'd know how many tuples at max you would have for each thread that is working on it. So they materialize them into shared memory and just write it out. Whereas for us, we'd have to materialize. We have to count and figure out and materialize.
But you know, for each element, you know exactly where to write it.
Yeah.
That's cool.
Yeah. Right. So, I think I have a few slides I want to really get to. So what are the problems again? Joins queue handling or the lack thereof. It's some. Oh yeah. Did I? Yeah. So what is happening with the works queue? Like if you give me a 1-to range query and you say every probe thread gets a range to join with, well, all the ranges are not same. All the threads are not doing the same work. You have thread divergence there. What is happening? That is a problem. So if you have, like, say, row ID is 0, 1, 2, 3, and these are the output counts you get after probe count 5, 2, 0, 53. Now the thread 3 is doing 53, materializing the 53 tuples, and well, what do? It's a straggler. Yeah, it's basically the same. In the COP DBLP TC graph, we measured what is the maximum tuples being generated across iterations, and one was doing 306, which is basically it's a straggler. It's stopping the kernel from completing. That is the join queue handling problem. What is the operator at a time? I think I don't have time, so I'll probably
just feel free to take a little bit longer.
Okay.
Don't you don't have to cut yourself off immediately, but be mindful of the time.
So operator at a time execution. So how is Datalogue, VFlog, and MNMG join are doing is they take a nice query tree and they take all the tuples, push it through one operation, materialize, and then basically do that up the tree. Why is that a problem? Because that what does operator at a time mean? So you take a bunch of tuples, push them through, and let's assume this is a join. So you push all the tuples at each step. And why is that a problem? Because if you have two joins, especially it's a problem because if you have two joins in a series, well, you're materializing all the intermediate outputs. That increases the peak memory requirements that you would have for the thing. Whereas Souffle would only do a tuple at a time. So it takes one tuple from whatever tuples it has to run through the query plan and basically runs it through. The problem with the tuple at a time is the function call overhead. So if you have 1 million tuples and you have to call 6 functions for the query, well, you have 6 million function calls. And then there is the nice balance of, I'm not going to do all of them. I'm not going to do one at a time. Let me pick how many tuples I'm pushing through the tree at a time and let me tune it so that I can do whatever I want and figure out where is my balance. What is my peak memory requirement, latency balance. That is what we want. And the operator at a time is a problem because of that. Yeah. And again, we'd want worst case optimal join for multi-way joins. There is no way of doing nicer pair. Any other way you do pairwise joins, it's a problem. Even if you're doing vectorization, even if you're only pushing one tuple through, it's just a problem that you have to deal with and you need a worst case optimal join for it. Yeah, I think this is just an explainer showing, this is the canonical worst case optimal join query. It's like TC for Datalog. Triangle is for worst case optimal join. So Yeah, it's a bad copy paste. Yeah, so we made this table by using our vector approach, and these are like for graph 22 from graph 500 benchmark, we had to materialize 75 billion tuples in the first join, and then it filtered down to 2 billion tuples in the second join. So all this is additional extra work that you should not be materializing, and you wouldn't with worst-case optimal join. Yeah. These are references. I thought people would be interested. I haven't read these two papers, but everything else, it's a wonderful thing to. It's terribly interesting. Yep. So those are the problems, and we have more problems. So GPU specific problems. These are, I think, in the weeds, which is both the engines bypass shared memory. They don't use the addressable cache. They use function pointers and kernels, which is terrible. You should not do that. You should write inlineable code. We have a bunch of non-coalesced loads, and we have a lot of warp stalls. Yeah, this is the problem. We don't use any addressable cache, and people should you should be able to use it. And we have something like we have hooks that you can write with however your join condition is, whatever your filter condition is, that are then called in the kernel in a tight loop, and that is a problem, that you should be writing functors that somehow are templated and inlineable. Yeah, this is the problem. So these hooks lead to redundant access to global memory. So we had about, of all the global excessive memories that accesses we had, the tuple gen that gets called the hook 2 times. One is for, I'm not sure why it's 2 times, but it's 2 times. They caused like 84% of our redundant global memory access, and that they should go away. And the other one is, because we have so many excessive memory accesses, it leads to warp stalls. At the very start, I told like the scheduler is an infrastructure that is shared between all the cores that are in the super streaming multiprocessor. Why is that important? Because you have a CUDA core, like say, so if there are 108 CUDA cores or something, you would only have 2 schedulers. What is happening there? Why do you not have 108 schedulers to push them all through? Why is because they do what is called latency hiding. So whenever a CUDA core makes a request to the memory, the scheduler can go pick up something else. Like it can go schedule another CUDA core rather than just waiting there. So it's almost like a free context switch that you can do. Yeah. And these are when the scheduler is not able to do that, then it's called a warp stall. And we should be actually scheduling 8 warps per cycle. We do about 0.1. And it's still state of that performance. It's very hard to get all 8 because it's a very irregular workload, but I think we can improve a little. Yeah, it's all problems. Do you have any solutions? I think we do. I think I'll run through. So we are dividing work based on probe tuples, which we should not. We should ideally have an indirection such that we are able to divide the work based on how many output tuples are being generated. So we should be able to distinguish if one probe tuple is generating 20, well, I should be able to say the first part of that probe tuple should generate 10 and the second part should generate 10. And I'd reduce the amount of stragglers that I have. And the second one is the vectorized execution that we need to tune memory usage for hardware for whatever purposes. It's an advancement that has given good results for us. So this is a very hand-wavy diagram of how the vectorization works. So if I have a join, B join, C join, D, which you should do with a worst-case optimal join, if you're doing it with pairwise binaries, what you do is, A join B is producing 3 vectors worth of tuples, which are then each run through the rest of the query on their own. And then you materialize and pull them into ABCD. This is the thing that we're still working on, which is to use the full as a queue and vectorize based on the number of amount of tuples in the queue rather than doing per iteration separately. I think that is interesting, but yeah. And then so the off-the-shelf option that we have for worst-case optimal join on the GPU is La et al. VLDB22. They did a accelerated leapfrog try join, which is the best implementation that there is, at least on the GPU that I'm aware of. So we either do that or we read more papers and figure out our own. And the general GPU tuning improvements is like more shared memory usage, more templated inlineable kernels, more vectorized access. Yep, is that all? Well, yes, but before the end, I'm looking for internships. If you have any, I'd love to work on anything relational, anything database, anything performance. Yeah, the point of the presentation is to introduce our GPU implementations. I think we did. I think we can. Yeah, okay. And motivate our current and future work to improve the existing implementations. Thank you.
So the last talk of the day is going to be by Dennis, and I have actually looked at the code for this tool. I was looking at it pretty like a few hours last week because I was hanging out with one of Dennis's, I guess, coworkers.
Yeah.
And he pointed me at this tool, said it was open source, and I think a year ago he maybe mentioned this tool is going to be made open source eventually. You can look at it.
Yep.
And I think maybe it just took a really long time for it to be made public.
Yeah.
And but it seems very cool, and I was very impressed by it. And so I think it's a cool benchmark for other folks who are interested in it here. But I'll let Dennis take it away. Thanks so much for coming up, Dennis.
Thanks, Chris. Yeah, so I'm Dennis. I work at Sandia. I've been working on this tool for a couple of years now. And I want to kind of give an overview of the problem it's trying to solve. How we solve it, and kind of the current state of things. So it's called Citadel. That's how it's pronounced. So if you hear me say that, then I'm probably talking about this. So like Arlen mentioned in his talk, I also support people who do code auditing, right? So they stare at code and they're trying to understand what it does, and what its security characteristics might be, for example. So this is a little fragment of code that is not real, that I wrote. But the idea is that some user input comes in to this code, and it flows through this transform record, and then it goes to H, which runs a command, right? And so if this code doesn't properly deal with the user input, sanitize it, then it might execute a command that's controllable directly by a user, which would be a bad thing for your software to do, right? It would make it insecure. So this is a kind of thing that I am hoping Citadel can help with. And so for the rest of this talk, I'm going to be talking about these things as sources and sinks. We're not going to look at code, which may be a relief to some of you. But we are going to talk about sources and sinks, and I might call them endpoints as well in the talk. But in general, this problem is known as like the taint analysis problem, sometimes called information flow analysis. I think information flow might be the oldest name for this kind of thing. But there's kind of two canonical examples of this. One is like the command injection kind of problem that I mentioned a minute ago. Another one is like, well, there's some sensitive data in my application, and I want to make sure it stays in the application and doesn't get leaked out into a log file or something like that, right? So in general, I want to be able to track data from sources of data that I'm interested in to sinks of data that I'm interested in them flowing to, across all kinds of interesting edges in the program, right? Across procedures in particular. And so one of the things that I'd really like to be able to do is have freedom to specify whatever sources I want, right? I don't want just canned sources. I want to be able to specify my own, as well as sinks. So this isn't really a new problem. There are tools for this that exist in the world. So Infer and Mariana Trench are two examples of tools that do this. So why would we want to build tools? Because they're pretty fast and good at what they do. So the main reason is customizability.
It's really hard to modify these tools in a way that you can kind of convince yourself is safe and is going to give you the right answers. It's hard just to navigate the code bases. There's a lot of code. It has a lot of indirection. It's somewhat hard to understand to me. So we wanted to build a tool that you could modify and that would interact with visualization tools. We kind of didn't want to solve the visualization problem. So we wanted to be able to hook into other tools to do that. Right. So the tools are hard to tailor for specific needs. That's really kind of the problem of why this exists. But we wanted to make something that also would scale. So
I had a question about that slide.
Yeah.
So is it not scalable?
Oh, I didn't even mention Duke. Sorry.
Is the scalability, does that relate to different features and modules being analyzed, or is it literally the actual context sensitivity is too high and enumerates too many points in the analysis?
Yeah, good question. So there's 2 points in there about dupe I didn't even mention. So the first is that the way dupe's analysis works is that it does call strings and context sensitive analysis, and the way it doesn't scale in the way we would like. That's point number one. The other is there's this kind of somewhat subtle point, which is...
Is that even with the so Dupe has a lot of different context sensitivities you can choose. Is that even with the insensitive analysis, or is that with the analysis? Oh, okay.
It's with the first sensitive analysis. Okay. I haven't run it in a while, but when you ratchet it up to the first thing you can get to, it doesn't scale enough. The other is that all of Dupe's analyses are formulated in terms of we're going to start at the main entry point of your program, and then we're going to go to the next things that it calls, and the next things that it calls, and so on. And this is exactly not how code auditors work, right? They want to go look at code and then ask the question, can I get here? What's actually going on? They're kind of working out from the inside out. So it's not useful if you your analysis needs to start at the beginning of the program and the people start in the middle and you can't meet, right? So we wanted to build something that would actually analyze all the code you gave it. Okay, good. So we developed Citadel, which is a taint analysis written entirely in Datalog, which is sort of a lie. There's a bunch of Python around it to do various things, to shuttle data in and out and that kind of stuff, discover, do all kinds of stuff. It's built around a couple of local analyses and global analyses, which we're going to talk about in detail. There's also a call graph construction algorithm built in, which is very neat because it's built into the same fixed point that discovers the data flow. So you can have your data flow inform your call graph and vice versa. Some other tools will phase those things. So you'll start with a call graph first, and then you do your data flow on top of it. The reference implementation, which I will show you, is 150 lines. And you can it works. You can give it real data and you can run with it. It doesn't cover how we do the fancy call graph construction. It's just direct calls. And with Citadel, you can kind of run it and just get a data flow graph, and you could just export that and use it if you wanted. You can also get a taint graph, and you can use that in flows. And then there's a visualization component, which I'll talk about briefly. The cool thing is the performant implementation is only 7,200 lines of Datalog. So a lot more than the reference, a lot less than 72,000 lines of C++, which is cool. Okay, this is it. This is the reference implementation. Are there any questions? Okay, so we're going to go through this in pieces. So the so Citadel is written around an input language called Citadel IR. So all of the target languages, the real languages that we deal with, get converted to that IR and then analyzed. So the IR is really simple. It's tailored for data flow analysis. It just has assignments and function calls and functions. That's it. That's what's in the IR. And then there's a little bit of tagging to actually set up the spec for when you want to do taint analysis. So some things here. So the assignments can use fields, right? So you can use actually access paths. So you can use sequences of field accesses in a single assignment. You can say x.foo.bar equals y.baz, for example. Also, you can do by value and by reference parameters to functions, right? So if you had a function in your program that took input on one parameter and the input ended up on another one, you can model that directly in Citadel. So on the left, the right, over there, is some code. And if you were to copy that and paste it into like your terminal, well, it might ask you to like paste the formatting, which would be terrible. But you could actually run this in one of our front ends. So this is source code that in our taint front end will be parsable, and you can actually run the analyzer on this, right? So if you have a question that's like, I wonder how it handles this particular scenario, you can just copy that, you can just write it and run it through the actual analyzer. That gets translated into the same IR as everything else. So that's kind of nice if you just have handwritten examples. That's how our test cases are written, for example, at least some of them. Okay, so I'm going to give an example, which is going to go over all the rules. And yes?
What about things like indirect calls and methods and things like that?
Right, yes. Good question. They're supported, they're right here. It turns out that if you do a call and this identifier is not defined, it's an indirect call. So we do support that. And we reason about those with Dataflow to resolve them. But I don't give like an example here of how that's done. But we do support them, and we reuse the Dataflow machinery to figure them out, at least in the default like mode for analyzing. Okay. So I'm going to give that code is an example we're going to go through. And so I just want to make sure everyone understands the example. So there is a path from source to sink. So source means that D is where the interesting data starts and enters the system, right? And sink means I want to know, does that data that flows into D end up in r.data? If you look through this, you'll see, I don't know if I can make my cursor do things. Oh.
Is there control flow? Do you do ifs?
Good question. The analysis is flow insensitive, so there are no ifs or anything in the way.
Branches and be like,
correct. Yeah, so there's a technical, like, what we actually do under the hood is we record those tests, so we have access to the tests themselves, but there's no sequencing and ordering in the statements. Does that make sense?
Sorry, so if the tainted data is in the condition.
Yes, so we can observe that because if it's in the condition, but we don't do like implicit taint where we transfer taint from a condition to the statements being guarded by it.
Don't you want to though? Or?
So it turns out that if you do that, in all but the most mundane cases, you get overwhelmed by statements that like, oh yeah, all this stuff is tainted, but none of it's tainted in an interesting way. So the auditors that look at the code will say, yeah, but I don't care, basically.
This is always the issue with information flow when you do this kind of analysis.
Right.
If you don't have an absurd amount of precision, then
right.
You have a lot of precision.
So yeah,
have a good time.
But that reminds me, I should have said on our previous slide, this is not a sound analysis. We're not trying to say, if this signs off on your program, it's safe. This is something that's supposed to assist people in understanding code. That's what it's supposed to do. Was there another question? I guess not. Okay. Right, so if you walk from the source, you see that it goes back into main, and then it goes down into call sync, and then it goes to sync. I mean, it's pretty simple. If there's questions, let me know. Okay, so the first thing that happens, this is Datalog, right? There's no first thing that happens, right? It's running rules, right? But I'm going to present them in some order. So kind of the first thing to think about is how do we analyze the data flow within a function, right? So these are the rules from the reference implementation. Don't squint a little bit at those right now. But they're going to gather their results in this locals relation. The way to read that locals relation is that some formal parameter, number n, flows to some variable. That's what's happening. All right? I'll explain the paths in a minute. So we're going to try to fill in that relation. The first thing that you see is this match prefix, which is how we handle access paths. So the access paths, remember, are field accesses. Match prefix just enumerates given a set of field accesses, sorry, not a set, a sequence, just splits them in all the possible ways so that we can say, okay, so that we can reason about fields. That's really all it's doing. Right, so the thing to remember is that fields are just represented as strings in our representation. So under the hood, in Soufflé, we're just using strings. We're not using any of their data types right now. So the first thing about the local data flow is that we're going to explode fields a little bit. So if you look at these, so these are the tuples that we add to the locals relation. In general, it's relating a formal to a variable. We're just going to initialize by saying everything's related to itself. Easy, right? That's this rule from the reference implementation. And it just applies to all three of those functions. So I'm going to highlight in green the things that it applies to, right? Okay, after we do field propagation, we get a new assignment that says, so before we had nothing there, right? B equals A, but now we get A.data equals B.data. So we're going to add a new assignment that has the field access in it. And now we have explicit data flow from the field in A to the field in B. And we're just going to keep doing this. And that's called field propagation. Questions? Okay. The next thing is, we actually use the same relation, but the next thing is to figure out reachability from formals. So we want to know, given if data comes in on some parameter, does it flow out to some other parameter, right? After we do reachability on this, there's basically two kinds of things that we discover, right? We figure out that for id, p flows out of the return value. And that is just a couple sequence of reachability tuples that we figure out. And we do the same thing for main, and we figure out that A.data flows to B.data. Okay, so far we're just running Datalog rules, right? This is super fun.
I'm sorry.
Yeah.
It also seems to be context insensitive. We're just going to again.
The reference implementation is context insensitive. Yes. The real one is context sensitive, but it uses something called hybrid inlining, which is kind of a different way of doing it versus, like, for example, dupes. But yes, it's context sensitive, especially for, well, everything's context sensitive in it. Yeah. But I'm just going to explain the insensitive version. Yeah. Yep. Okay. So. Right, reachability. We're just tracing the data flow now within each function, right, independently. And then finally, the reason why we trace that data flow, right, is that we want to create a summary of the function behavior. We want to say parameter 2 flows to the return value. That's really what we want to get to. So that is this rule. We've been populating locals with all this reachability information, and now we want to say, make a summary. And a summary is literally just that. So the summary for id is formal 0 flows to -1. -1 is a special parameter that just means the return parameter of the function. Okay. That is it for local data flow. So that's all localized within one function. But now we have summaries, so we can do things like instantiate them. So this is the rule for that. Basically says if there's a summary and a call to that function, we're going to then create a new assignment-like thing, which is a new assignment. So that's going to create this assignment down here. We used to have just A.data equals B.data, but now we can relate B and C. And it's because this is the action of calling id, the identity function, id. So this is kind of the rest of the story. After we make the summary, then we get a new assignment, we do field propagation, we get the field. We do local data flow, we get the connection to C, and then finally we can actually figure out this path from source to sink. Okay. Any questions so far? Okay, I'm gonna keep going, please interrupt. Okay, I just smacked the mic as hard as I could. Okay. So, right, so the way this is built, so there are some advantages to this, right? So one of them is we're doing local data flow, and none of that has anything to do really with other functions, right? So all the functions could be conceivably analyzed independently. And then the communication between them is just the summaries, right? If A calls B and we figure out a summary, we're going to have to update A because of the summary that we got for B, right? We also don't have to worry about like what the call string is right now. That's done a little bit later, but we're going to analyze all the code, right? It doesn't depend on where did we reach this from for most of the analysis, because a lot of the analysis is independent of that. And we can exploit that independence, which is nice. So the implementation basically does field propagation and reachability and stuff like that the way that I described. It's a bit more optimized, which means it's worse to look at. There's a bunch of souffle plans, which I'll talk about later, to optimize evaluation order and basically make things run faster. We have a few other features which you can read about in some of the docs if you want. We can do abstraction on the access paths, for example. We can also make them very expensive by inferring k-bounded ones, if you want that. I didn't cover it, but there's like a subtle point here, which is there is a set of all of the access paths that the system is allowed to reason about in the background, and that is what bounds the analysis and makes it kind of finite. So you could add things to that set and you would get a different analysis. You can also say like add things automatically, but k-bound them, and then you will get a different analysis. Okay, so here is a row of not 10 things that are actual apps. I just pulled the top 10 from like APK Pure or something. See, this is like an Android app site that you can download. And one of them didn't look like it had any code, so that was really cool, so I threw that one out. And another one, two of them timed out in the time that I was preparing for this talk after using about 300 gigs of RAM, so I just killed them. But you can see we can analyze like real apps in maybe not on your desktop computer. I think, yeah, our highest memory usage is 140 gigs of RAM. And the way Souffle works, right, all of this is resident. You have to get kind of up to that point and then it just drops it all when it's done, right? But these are large real programs, which is kind of the goal. And the times, where are the times? Yeah, so the times seem somewhat reasonable, right? Okay. I'm not going to talk about some of the things that are kind of hard to do in Datalog and hard to do in Souffle that we wish we could do. Yes?
Why not?
What, I'm sorry?
Why not?
Why not what?
I must have misheard you, sorry.
Oh, I'm going to transition.
You say I'm not going to talk.
Oh, no, sorry. I'm going to give you a number of things that I wish we could do.
Totally misheard.
Yeah, no worries. So, for example, when we're computing function summaries, for some functions you can figure out, hey, I've figured out all the data flow I'm going to figure out. So it'd be nice if you could deallocate that, right? And you could say, I'm done looking at that. Here are all the summaries. Don't ever use that function again. This is essentially saying, I want to say that I want to delete some tuples from my facts, basically, which is hard to do in Souffle. In other systems, it might not be hard to do, but it's hard to do in Souffle.
But this would be really nice because then you could release the memory for analyzing those. So the other thing, actually, I'm curious about this. In differential Datalog, for example, I don't think this is equivalent to deleting the facts because you're not retracting the facts. You're just saying, I already analyzed them and I would like to release them. So I'd be open to just talking about that, but yes.
So is this something that is it stratified in the sense that it happens in a previous, so you partition the program into strongly connected components. Mm-hmm. Is that the case that all these, the summarization happens in an SCC that depends on one of the SCC that does all of the actual F, let's say, the laborious stuff?
Yep.
Is it not the case? Does Souffle not just, I guess it doesn't just throw away SCCs when they're not useful anymore, but it seems like it could be a pretty simple optimization.
So here's the data you want strongly connected components over.
Yeah. The SCC here is the whole analysis, unfortunately.
I see.
Because you're just saying
everything's in a huge loop.
Right.
Sorry, but even then, you actually want to do this on like a per function basis, right? Which all those functions are represented in the same. All functions are represented in the same relation. So it's a question of like, function f, which I have completely analyzed the whole body of it and all of the things that it calls.
Yeah.
Right? You no longer need any of the local control flow information. You just need the summary at this point. And so you could drop that. You could get rid of that out of memory. But but that's part of the local control flows relation, which also has every other local control flow in the whole program, right?
Yeah.
Including the functions you're still analyzing. And
Fair enough. Yeah. Fair enough. Michael?
Yeah, I mean, I feel like this is something that you could kind of resolve by not having a single big Datalog program. Like the way people write a static analysis by hand, you say you can like spin off a bunch of threads that would say, okay, you analyze this function, you analyze that function, and yeah, who cares? You give me the results, and I'm gonna put them in some global store.
Yeah.
Like the fact that there's a single global store for all of these tuples is a coincidence of how you're doing Datalog here, but like. You could do it different. I mean, a souffle's costume, I think, work out perfectly for that.
Are you going to write like 3 versions of the program for the same problem?
Write 3 versions.
And then that's what you're suggesting. Like you have exact.
Which program are you talking about? The program being analyzed.
The analysis of
the program that's doing the analysis.
Yes, the program that's doing the analysis.
The analysis should be modular, right? You should have an analysis that says, you give me a function, I'll produce a summary. This is a local act that uses the common logic of the analysis to sort of do a bunch of stuff.
Well, but this thing will go in like when it's doing the field propagation. It'll go into functions and like add another field. You'll add more qualities.
Oh, then you can't do that.
You're going to have to continually reinvoke that whole sub thing.
Invalidate summaries and come up with new ones.
You don't invalidate summaries, but you might come up with new ones.
Oh, well, that's yeah.
That's a distinction. I don't understand that distinction, but then my plan is.
Summaries are grown. Basically, because you can add additional flows to an existing summary. So summary is not a static concept.
Okay.
Right. For each function, the set of summaries is kind of like growing a little bit over time.
Okay, well, then it seems like you wouldn't want to delete facts about F because you're going to need those facts when you add more.
At some point, you can realize that you will never do that. That is the point I'm trying to make.
I see.
At some point, you can say, I know I will never find something new for this function, therefore I'd like to jettison that memory. And I'd like that to propagate up the call graph, for example. And I can't easily do that without re-architecting the whole thing. Yeah.
I think this idea of like kind of garbage collecting parts of your data log based analysis is something that I know folks here have talked about, at a high level a bunch.
Yeah.
And it seems like this is a good motivator for that. So it's very cool.
Yeah.
If it's helpful, the idiom in differential data flow would be to have an additional set of, like an additional fact input that you would, whenever you reach this conclusion, you would say, oh, badass, I'll capture all of those summaries, drop them into this thing, and then delete the function.
Yeah.
Okay.
And you'll be surprised, okay, the function's going to unravel completely, all of its conclusions are going to go away, but the summaries will stick there. Like a human, or
sure,
programmer has to do this.
Yeah.
So it's supposed to be a little bit like, I don't know if people here do this, but just constraint handling rules are a thing from like the 90s, and they're a bunch of destructive productions. So rather than only adding facts, they trust, if you have A lesser equal to B and B lesser equal to A, you delete those 2 facts and replace them by A equals B. It is and I don't know how that works or where it went or anything like that. But,
okay. That's a good point. Yeah.
Stuff like that. Not as popular as Datalog for sure.
Yeah, sure. Okay, so you may have heard of plans. For those who don't know what those are, I'll explain. So Soufflé does something called semi-naive evaluation, right? And the idea is, so imagine you have this rule, A is derived if B and C hold, right? So what Soufflé does under the hood is it generates 2 versions of, and B and C also depend on A, sorry. That's what the dependency graph looks like. So what Soufflé does under the hood is it says, I'm going to generate 2 versions of A. One of them uses this special delta relation in the front, in the same order as BX-CX in the front, and then the other one uses the same another delta relation for C on the back end. And what these hold is kind of like, as it's doing its fixed point loop, it says, whatever is just the new stuff I generated in the last iteration goes into this delta, right? So there's this common thing that happens where if you write rules like this, which are super common,
then it'll generate versions like this, and this one is going to suck because this one is going to iterate, is going to scan all of B, and then it's going to figure out just the delta of C. And since Soufflé compiles to just for loops, this is what happens. You end up iterating potentially over a large relation and then just having something simple to do. So what's often the case that you want to do is you write a plan like this one, which is going to turn it into version 1 prime. It's going to say, take that delta relation, which is likely to be small compared to the big relation, and put it first, because it's more efficient if you iterate over something small first. And this is great, because you use these all the time to overcome this problem. The fact that you have this control is really nice. And it's actually really essential, because there's so many rules that have plans. In Citadel, there's 166 rules. And plans really turn things that are not tractable into way more tractable things. Yes?
So am I understanding correctly that if you don't say anything about plans,
yeah,
Soufflé's semi-native implementation will not iterate over the deltas first?
You are understanding correctly. Yes. Yes. So it gets worse, right?
But I don't know what it is.
Yeah. Like, I mean, is it just really want to do left to right for some sort of
Yes.
like?
Yep.
Yes.
It sure does.
Basically, it does. I mean, Yihao has said it basically just does left to right. Yeah, it's nothing special.
I mean, is it doing query planning? Like at all?
That's its plan.
For the .plan thing.
Yeah.
Basically, the answer is no.
I think it more adopts a strategy than does planning.
It's got some heuristics, but you know, basically no. Yeah, if you want, I mean, if you take these big programs and like Edasasm or other like Duke, you just perturb the query plan a little bit, they get like 1000x worse very quickly.
Oh yeah, super bad.
Okay.
Super bad. And it gets worse, of course, you know, the more recursive relations you've got, you know.
Sure, yeah.
And another bad thing happens, which is that you can break these plans very easily, right? Because you can affect which things have deltas or not with a change that's somewhere else in the code base. And this is very annoying. So I had an example of that, which is, you know, when I was playing around with the call graph analysis, there's something called call hierarchy analysis, which is a way of discovering the call graph that's type-based, type-directed. And then we were using, I implemented something called hybrid inlining, which is data-directed. It follows Dataflow to figure things out. If you substitute one for the other by changing the code, then a bunch of the relations that were recursive become not recursive, and all the plans that are involved in all those rules break, which means you have to go comment them out. Or write worse, if you really want to test the change at scale, is you have to go rewrite them with new numbers. Yeah?
How do people see the plan that Soufflé has chosen? Is there like some Soufflé explain?
Show equals transformed RAM is, so, okay, this is, you've now provoked a rant. Congratulations. So the rant is, when I was trying to learn this stuff, there is, this is exactly the example you get from the documentation. That. And it says we produce version 0 and version 1, and then it says you can write this plan to do this. And that's the end of the documentation. So if you want to know what happens in 3 rule, you know, a rule that has 3 things in it, there's nothing for you. So how do you know which version is which? Well, it turns out it's the first one it prints in the show equals transformed RAM output. So basically you do a debug dump and you count which version until you get to the one that's like in the yeah. That way, yeah. It's a lot of overhead. So like it has this beautiful like HTML report that's like a profile report, and it says version 0 takes 75% of the time, and you're like, or version 5 takes 70. You're like, wonderful. 0, 1, 2, 3, 4, and you have to count them. So yeah, so plans are great, except when they're not. So any solution to this problem would be welcome, because this is, yes?
I promise it's not like a sarcastic question or anything.
Okay.
Did you try a different Datalog?
Oh, yeah.
Or is that, are you using some like arcane Soufflé business that?
Oh yeah, so originally I went kind of whole hog on Soufflé, right? And I was like, I'm gonna have components and we're gonna use subsumption and we're gonna use all this stuff. And then it crashed a number of times. And there just seems to be some interactions between, especially like different forms of aggregation and stuff like that, along with the components and other things. That when you put them together, choice domains as well. When you put them together, it's not happy.
Yeah.
So I've since backed off that. I haven't looked at a bunch of other data logs yet. I was trying to get kind of the features and the stuff, working. There's been a lot of iteration on actually making this usable, and so kind of trying different data logs has been on the back burner for a little while.
Conceptually, you're no longer using any Soufflé specific features, or
just what is it? Components, which is like a set of rules you can instantiate in particular contexts. Basically, it's kind of like object oriented. So it's not a big deal. But there are things I'd like to use, like subsumption, for example, would be nice if it worked. But it doesn't work in all cases, and unfortunately, sometimes also. The failure mode isn't crashing, it's wrong answers. So, so here's another example. So we have a method for abstraction where, which I'm not going to describe, but I call it star abstraction. This is a different kind of abstraction where if you have expensive to maintain access paths, right? So you have a bunch of fields you're reasoning about, complicated objects. What you'd like to do is kind of replace all that stuff with a star and just abstract it, right? And maybe you decide this based on some heuristic, but it would be nice if you could do this because the alternative is just analyzing for way too much time in memory. Maybe you'd like to terminate instead with an answer. That makes sense. So I think this is perhaps an instance of the same kind of deletion problem. You want to be able to say, I come up with an abstraction, and I want to delete all the expensive stuff I was maintaining before I came up with that abstraction. But that's not something that we can do that we wish we could do.
I think a common name for this is like some kind of widening.
Sure. Yeah. Right. So we use strings, I mentioned before, for access paths. So Soufflé has algebraic data types. I mean, it has a way of saying, for example, here's a linked list, and here's the list of accesses that you want. Unfortunately, there's another common failure mode, which is you use a feature and then you can't round trip it through persisting that, right? So you write something in Soufflé, you compute an answer, it tries to write it or then read it again, and then it fails to do that. So that's not really an interesting, perhaps, failure, but I think this one is maybe a bit more, is just that reasoning about types in general is hard. I think some other data logs have a much better story about this than Soufflé does. Right. This has been touched on, I think, in a couple of ways, but basically being able to call out into external
is really useful, and I think people recognize this.
But this is an example that it is also useful. We'd like to be able to write a bunch of things in external code and have them produce multiple results rather than having to write absolutely everything in Datalog. There's a balance there of what might be the most comprehensible kind of code.
By multiple results, you mean like have it behave more like a relation?
Behave like a relation. Yeah, behave like a rule. Yep. Okay, so I'm just going to end by telling you how the tool itself works rather than just the architecture. And this is going to be really brief. So the tool has three phases. You import your code, which is going to create facts. So if you're interested in facts for real languages, you could use the import part alone, for example. And the distinction here is that we're going to be importing, so we can do things like binary code. So that's the, Ghidra is a reverse engineering tool, and we can use that to import code. Then you index the code, which is going to build the Dataflow graphs and the call graph and so on. And there's a whole modeling subsystem. So if you want to, say I have all this library code, I want to provide some models for what those functions do, you can do that here. And then there's the query engine, which actually does chain analysis. So that's a third phase that you could do, that you would do to use this. And there are exporters. So there's a graph export. So if you want to get a flow where you get some code, do a query, and then operate on the graph later, you can do that. You can just export the slices that we produce. Okay, so this is an example of, I've had a couple of conversations where people were curious about how do you actually visualize this stuff? So there's a format called SARIF, S-A-R-I-F, which stands for Static Analysis Results Interchange Format, which is what we use. So Citadel can emit serif, and then VS Code can load it. So can you see that
Sort of.
a little bit better?
Did you change your theme, or is this a picture?
It's a picture, yeah. I'll just explain it. So
be able to turn off some of the lights.
Oh, I see.
I think lights towards the front. Just start flipping the switches kind of randomly. Okay, there you go. Much better. That's what I do in class all the time.
Yeah. All right. So no apologies for the dark theme, but yeah. So when you load it into VS Code, what you get is something like this that says, here's a path from a particular place in code to some other place in code. And it basically says that the taint enters in this return parameter of get device ID, and you can follow all the variable names through the program, and you can click and it'll jump to that part of the code when you're looking at it. And then it'll finally go to like filewriter.write. Okay. There's nothing interesting about this. This is just some canned source, but it just shows how the results get shown. So you can actually see a Dataflow path from that the engine found. Okay, turn the lights back on. This is now something that is almost out, but this is a plugin for Ghidra. So if you use Ghidra, then you can run Citadel and you get like highlighted lines, but you also get highlighted variables, which is very cool because the integration is kind of tight, which is neat. And you get it both in the decompilation view, which is on the right, and what they call the listing, which is just the disassembly in the middle, or on the left there. And you can actually see the taint graph, although you're looking at machine code, which is horrifying generally. Okay, so this has been joint work with Arlen, who's right over there, and a team of a couple of other people at Sandia, Tim and Brennan. And I think there is, I haven't explained this. You might be wondering why in the hell this is here. So that is our official logo generated by AI. One of my friends at Sandia wrote a prompt, something about Citadel with many wires connected to it or something like that. And it generated this very metal looking logo that I love, which is back there. And I owe you, I think, one more thing, which is that. So do you have any more questions?
The source to sync was reachability.
Yeah.
What's that?
The source to sync is fundamentally reachability.
Yeah,
I think we can count
it is, yeah. And this code is in the database, or in the rules of Citadel, yeah. Yes?
The path abstraction thing that you're talking about?
Yes.
Is that a static optimization, or is that something you want to be able to do on the fly?
It is something, I want to be able to write rules that kind of efficiently compute that abstraction when it's appropriate inside
I don't understand.
Oh, okay. I don't understand your question then, sorry.
Okay, so you've got all these field paths, strings.
Yeah.
And are you making a decision that this is too many and you want to abstract them all into field star ahead of time, or based on the ongoing analysis?
Oh, I see. I think based on the ongoing analysis is the idea, if I understand the question.
Okay. Well, I'll ask you.
Okay, fair enough. Yes?
This is a question to you, but also sort of the ensemble classes, which is, it seems you have Datalog, you have data sets, things take a lot of time and use a lot of memory, and I'm trying to figure out what it will take to nerd snipe the 10 different Datalog implementers in here to just download your Datalog and try it, if only to punch souffle in the tum-tum.
Right, right.
It kind of feels, if we're all collectively building things here, and
Arlen already did that to me, so.
Punch through the tum-tum?
No, there's no.
Gotcha, okay. But it feels, unless I'm wrong, if the vibe here is we build Datalog things. Awesome, there's a real world, not just transitive closure, but real problem here to chase down with actual, it seemed like, annoying, irritating problems that and maybe more reality than. But no, it feels like a sweet opportunity to actually do that versus like a few simple queries on bibliometrics.
Well, whatever I can do to make that have less friction.
We're sold.
Is that link up? That just has the data log there, yeah.
So yeah, so the one point of friction that I can think of is that the way the tool works is depending on the language that you're analyzing and stuff like that, it has to make some choices. So it generates. So for example, if you import like a Java program and you say index this, the first thing it does is it writes a .dl file. So you could take that file and that's like your Java analysis, and it's whatever 7,000 lines or whatever of Datalog, and that it's souffle Datalog, so you have to translate it to whatever you want. But yeah.
So can you say a few words about? So I kind of have two questions. So you can answer however much of this connects with you. So first, I'm interested in hearing about the choices of context sensitivity that were necessary to scale this. Mm-hmm. Embedded in that question is the fact that this is a multi-language framework, and so does the multi-language stuff necessitate vastly simplified notions of context sensitivity? Is that a concern at all?
Is it all call sensitivity? I assume that's the hybrid inlining you're doing.
That is call context sensitivity. Yeah.
So you have to implement something else in a special way. I think this is sort of Chris's question. You have an object-oriented language, you want to do object sensitivity, or you just have to implement sensitivity in a different way.
You'd have to implement that in a different way. So I'm familiar with like some of the Yannis's Smaragdox's work on kind of trying to unify those in Datalog, right? Yeah. We don't actually implement it that way, but there's no reason that you couldn't, I don't think. So the special thing about hybrid inlining, I think, is that that applies to this problem is that you work backward from the call site rather than like outward from the program. So you're working back up, and then you're trying to figure out where are my resolvents that could resolve a particular virtual call, and you only work back a certain amount, But generally speaking, we can work back pretty far. So one of the things I didn't mention is that there's no limits in this engine. So like Mariana Trench, I think, has like the stack limit is 7, for example, by default. And we do have access path limits, but we don't have, like calling context limits in there. So yeah, did I answer your question?
I have a related question.
Yeah.
Do you vary the context depth per function then? Is that part of what makes it hybrid? Because like Smaragdox has some papers on hybrid sensitivity, which I think is different, right? Because he's varying the degree of context and the kind of context based on like pre-analyses.
No, the answer is no. So I can talk more details offline, I'd be happy to, but basically you find a virtual call site and you're working up, right? And generally that process will terminate because you're following data flow. You're not just following calls, you're following like actual data flow paths to things. Right. So how many functions are going to have direct data flow paths to a ton of places? Not that many, at least in my experience. So we don't limit that to K or anything like that.
If you were to move in that direction, then you might not want the stratification you have between what you call the indexing and then the source to sync.
Yeah.
Because discovering something was tainted that then an auditor says maybe shouldn't be tainted might be something that would inform what kind of sensitivity.
There's a lot of potential benefits of unifying those two phases, indexing and querying, and the main one is that. Right now, we have to pay the full cost of indexing because we don't have any incremental anything. So we don't do that because we want to index once, query many times.
I was just going to ask, how many context sensitivity strategies did we go through before you found hybrid inlining? It was a bunch.
How many? Yeah.
Yeah.
I mean, it felt like a bunch. Yeah. So I mean, CHA is one of them, right? Which is
there was RTA.
Right, which is a CHA variant. Yeah.
We tried just using doing context insensitive flow analysis.
Oh yeah.
To fill it in.
It all started because we were doing context insensitive stuff, and you get so many false positives from that it was very annoying. So.
Yeah.
A good handful, yeah.
And hybrid inlining works exceptionally well in this context. No pun intended.
Do you actually use the cross-language stuff? Like, have you used it for something that like you actually care about?
No.
That's fine answer.
Yeah, but
well, you could imagine Java to C++ with the Android stuff, for example, with like NDK and stuff like that.
Yeah, and you could do Java to like a shared library with the Ghidra stuff, but we haven't done that. Yeah.
That's cool.
Yeah.
I think it's kind of supported by the fact that it's trying to be sort of, you know, human-directed and stuff like that. Also kind of helps. You know,
yeah. Any other questions?
We got a bunch of questions during the talk.
Yep.
So
Thank you.